Understanding artificial intelligence and machine learning is essential for leveraging these technologies to drive innovation and data driven decision making. This course will provide you a conceptual foundation in AI and ML concepts, including the use of tools like Google Cloud's Vertex AI, AutoML, pre trained APIs, BigQuery ML, and TensorFlow for building effective machine learning models. In this course, you will learn the foundational concepts of AI and ML, including key terms such as features, models, and training. You will contrast AI and ML with business analytics, understanding their distinct purposes and how they complement each other in data driven decision making. Next, you will explore generative AI, discovering its capabilities in creating new content and potential applications. You will discuss the attributes of good data, emphasizing quality, diversity, and relevance for effective machine learning. Additionally, you will dive into responsible AI, considering ethical factors and best practices for developing fair, transparent, and accountable AI systems. Finally, you will explore Google Cloud's Vertex AI platform for machine learning. You will learn to perform machine learning on Google Cloud using tools like AutoML for automated training and custom training for tailored solutions. You will cover TensorFlow, BigQuery ML for SQL based model building, and pre trained APIs for common use cases such as vision, video, and speech, which enable you to leverage AI even without extensive training data. Google believes that we are in the era of the transformation cloud. This is where cloud technologies can help an enterprise transform every aspect of their business and its culture. Because of the tremendous importance of artificial intelligence and machine learning in this particular phase, it's critically important for all aspiring cloud leaders to understand what AI and ML really are. Let's try and define these terms and also understand some of the differences and similarities across them. Let's start with artificial intelligence. What is artificial intelligence? One way of defining it is an activity that is devoted to making machines intelligent. And intelligence is that quality which enables an entity to function appropriately and with foresight in its environment. If we really think about what this definition is getting at, it is mimicking human cognition. That's a very ambitious aim, and that is what sets apart artificial intelligence from machine learning. Artificial intelligence can be thought of as an umbrella term for software which mimics human cognition, such as understanding language, interpreting information in a human like manner, and displaying judgment. The whole thrust of artificial intelligence is on performing very complex, almost human like tasks of cognition. In order to achieve artificial intelligence, a whole host of different techniques might be employed. One of those, which is very closely related to artificial intelligence, is machine learning. We can think of this as a subfield of artificial intelligence in which algorithms are trained on data in order to produce models that can perform predictive reasoning. So, machine learning is all about building models which solve problems by looking at past examples of solved problems. So, if AI is all about mimicking human cognition, then machine learning is all about learning from data without being explicitly programmed to do so. When we imply that ML models are not explicitly programmed to learn from data, that's because they are rather trained to look at a vast body of past data and then identify patterns from that vast body. This process is known as training. Models improve their performance over time as they are exposed to more and better data. ML techniques include supervised learning, in which models are trained on labeled data, and unsupervised learning, where models find hidden patterns in unlabeled data. There are also other subdomains of machine learning, such as reinforcement learning, in which models learn to make decisions through trial and error. Applications of machine learning are vast, and these include recommendation systems, fraud detection, image and speech recognition, and predictive analytics. Despite all of these impressive capabilities, this is a less ambitious goal than that of artificial intelligence, which seeks to mimic human cognition. Machine learning has played a starring role in a lot of the advances in artificial intelligence. Another term worth discussing here is deep learning. We can think of deep learning as a subset of machine learning that uses advanced models built using neural networks in order to perform some of the most complex tasks in the world of machine learning. Deep learning involves training large scale models, often referred to as deep neural networks, on very large amounts of data in order to perform tasks such as image and speech recognition, natural language processing, and so on. Because these tasks are often present in human cognition as well, deep learning has an even more special place in the development of AI systems. Researchers have found that deep learning models have especially great results when working with hierarchical representations of data. Different layers of the neural networks capture different levels of abstraction amongst the features. Deep learning has been especially successful in fields where large data sets are available, and it has led to significant advancements in artificial intelligence. These range from autonomous vehicles and medical diagnosis to personalized recommendations and fraud detection. Google uses the analogy of an umbrella for artificial intelligence, and it posits that under this umbrella, there are different types of systems, which might include machine learning and deep learning. In addition to these, other examples of systems under the AI umbrella include robotics, expert systems, and natural language processing. These are not disjoint. For instance, there is a fair amount of overlap between natural language processing techniques, machine learning, and deep learning. Here are some examples of AI. An autonomous vehicle or a self driving car that can navigate traffic and routes on its own. Such a vehicle might be said to be successful if other skilled human drivers are unable to distinguish between an autonomous vehicle and a vehicle driven by a skilled human driver. Consider a conversational chatbot that can interact with customers or other humans and answer questions and respond to queries. Such a chatbot might be said to be successful if customers are unable to tell that they are interacting with a non human agent. Voice assistants like Alexa or Siri, which can understand and respond to voice queries. You can see that in each of these examples, a measure of the success of the artificial intelligence system is whether it is able to successfully mimic human cognition and is indistinguishable from a human. Every one of these examples is powered by machine learning. The self driving car, for instance, uses computer vision algorithms to recognize stop signs, signals, and cope with other systems that arise during driving and navigation. The conversational chatbot has learned to recognize patterns in queries, and it has learned how to use those patterns in order to produce intelligent responses. The voice assistant uses speech to text and text to speech models in order to interact with users. The use cases of artificial intelligence built atop of machine learning are everywhere these days. There are four broad categories that Google has identified. Let's talk about these in turn. The first is in simplifying rule based systems. Traditional rule based systems can be thought of as giant aggregations of if then else blocks. If a certain situation arises, then a certain action has to be undertaken, else some other action has to be undertaken. These are rule based systems, and AI and ML can help these systems scale and stay relevant because they can adapt to new patterns without the rules needing to be manually updated. For instance, in email spam filtering, traditional systems relied on predefined rules to identify spammers. However, because spammers constantly evolved their tactics, this made it very challenging to keep the rules in sync. In this arms race, ML models can be trained on large datasets of emails to automatically detect spam based on patterns and features such as keywords, sender reputation, and email structure. These models will continuously improve as they process more data, providing a more robust and adaptive solution. The automation of processes is a second broad category of business problems that AI and ML can help to solve. They can automate repetitive, time consuming processes, improve efficiency, and reduce human error. Consider, for example, maintaining safety inspections in an operationally intensive business such as a manufacturing plant. Here, sensors might be emitting readings of temperature, pressure, and other environmental variables, and those readings need to be constantly monitored. Anomalies need to be detected and flagged early before they lead to breakdowns, accidents, or worse. A third very common use case has to do with analyzing and understanding unstructured data such as text, images, videos, and audios. For instance, in the context of document processing, ML models can be used to extract information from unstructured data such as images or PDF documents containing invoices or vouchers to extract invoice numbers, dates, payment terms, and payment information. This automation can streamline accounts payable and accounts receivable processes and allow businesses to focus on their core competence. A fourth very common use case is the personalization of user experiences. AI and machine learning are essential for delivering highly personalized experiences on giant platforms such as YouTube. ML algorithms analyze user behavior such as watch history, search queries, and engagement metrics to recommend videos that match individual preferences. For instance, YouTube's recommendation system uses collaborative filtering and content based filtering to suggest videos that users are likely to enjoy based on their past interactions and based on the behavior of other similar users. This personalized approach keeps users engaged, it provides relevant content, increases watch time, and enhances user satisfaction. These are four broad categories of business problems that AI and ML are applied. Now, in any individual use case, you'll probably see a combination of these problems being solved. Consider predictive maintenance in manufacturing. Here, AI and ML can help to analyze data from sensors and machinery to predict machine failures before they occur. The models can analyze patterns and anomalies in real time data of environmental variables such as vibration, temperature, and pressure to identify signs of potential problems. By predicting when equipment is likely to fail, the manufacturers can schedule maintenance during non peak times, reduce downtime, and keep maintenance costs in check. This will also help to extend the lifespan of the machinery, improve operational efficiency, and minimize production interruptions and safety accidents. Personalization is also being applied to a variety of domains, such as healthcare. In healthcare, AI and ML are being leveraged to provide personalized treatment plans for patients. These will analyze each patient's history, genetic information, and lifestyle factors, and then identify the most effective treatment options for each patient. For instance, AI might assist in tailoring cancer treatment plans based on the genetic profile of both the patient and the tumor. Such approaches can go beyond treatment and also help in early disease detection and monitoring. A third example is fraud detection in financial services. Financial institutions looking to deter fraud were among the early adopters of AI and ML. ML models can analyze vast amounts of transaction data to identify unusual patterns and behaviors that might indicate fraudulent activity. Such systems are especially valuable when they act in real time. These can alert institutions to suspicious transactions and enable them to prevent money from going to bad actors in the first place. Finally, consider the use of natural language processing for customer support. Driven by advances in NLP as well as generative AI, systems are now able to both analyze and interpret customer messages and also generate intelligent human like responses. These responses might take the form of text or even speech. Now that we have a good high level idea of what artificial intelligence and machine learning are, let's turn our attention to machine learning and familiarize ourselves with a number of terms which arise again and again in this domain. As we've discussed, a machine learning system is one that learns from data. So, any algorithm that learns from data is an ML algorithm. Essentially, these algorithms improve automatically through being exposed to more and more past data, i.e., they improve with experience. There are two distinct phases in the development of most ML algorithms. The first is where the algorithm is trained on data to recognize patterns, and the second is where that algorithm is now shown new, unseen data and asked for predictions. The first step is usually referred to as training, and the second as prediction or inference. Let's say that we'd like to build a machine learning model and use it to try and improve some aspect of our enterprise. How would we go about this? Well, to begin with, we would choose a machine learning algorithm. The process for doing so is relatively well defined. There are some common problem types such as classification, regression, clustering, and so on. And then for each of these problem types, there is a host of well defined solution types. These are optimized for different problem cases. We then take one of these algorithms and feed in a large quantity of training data to allow the algorithm to learn from the patterns in this particular dataset. This training dataset is often referred to as the corpus. The training process is technically complex and it involves correcting the algorithm iteratively so that its understanding of the training data improves over time. Please note that so far the algorithm has not been shown any new unseen data. It's merely being exposed to that same training dataset in a predefined iterative fashion. Finally, once we think that the algorithm has done its best at extracting information and patterns from the training dataset, we then move to a stage known as validation, where we give the model some new unseen data and validate the model on that. This validation step is still a precursor to the actual deployment of the model, where it's used for prediction or inference on entirely new data where the actual or right answer is still unknown. It is worth reiterating that there are essentially two phases in the process of building the ML model: training, which is where we take a known dataset and train the model on it, and then prediction or inference, where the model is effectively used out in the wild, as it were. Let's consider one of the oldest problems that ML was applied to, and that was distinguishing between spam and ham emails. A couple of decades ago, identifying and classifying spam emails was a very important problem. It was observed over time that spam emails tended to have certain characteristics. They tended to originate from certain sources, they tended to use language of a certain type. The term ham emails was used for emails which are not spam, and these also tended to share certain characteristics. They typically originated from known email IDs and contained clear, simple personal language. Now, the process of training can be visualized as follows. We start with the training data, which is a large corpus or repository of emails where we have both spam and ham emails, and where all emails are labeled or pre classified as spam or ham. We pass that training data corpus into a classification algorithm whose output is a prediction, that is a label, either spam or ham. The algorithm is going to try and observe the attributes or characteristics of all of the emails and use those to predict whether the email is spam or ham. Those characteristics or attributes are all called the X variables. There are several terms for such X variables. Other terms include features or explanatory variables. The algorithm outputs a prediction, which in this instance is a label spam or ham. Now, the output might not always be a discrete label, it might also be just a number, but in any event, the output is referred to as the target or the Y variable. How does the training process actually work? Well, the classification algorithm is fed the training corpus, and it is also fed the correct labels for each email in that corpus. The model will on its own try and make predictions. It will base these predictions off of the X variables. Very likely those predictions will be wrong, especially initially. Those predictions will then be compared to the actual labels associated with the emails, and the difference, which is referred to as the loss, is then fed back into the algorithm so that the algorithm can observe where it got things wrong. The beauty of the machine learning algorithm training process is that the parameters of these models are tweaked on the basis of this loss. This process is repeated iteratively until we converge on the best model parameters given the training data. And at this point, we have a trained classifier. The training stage is complete. Now we move to prediction or inference. At this point, a new email reaches our inbox, and the trained classifier kicks into action and tries to decide whether this email is spam or ham. Then, some system will take action based on that classification. Now, of course, a lot can and does go wrong in this process. Notably, we have the problem of garbage in, garbage out. The ML models are only as good as the data that was used to train the model. If the model was trained on poor data, then even a model with a very good architecture will perform poorly when presented with new, unseen data. By the way, here it's important to note that the success or failure of a model is measured during the prediction or inference phase. It doesn't matter much how well the model does in predicting the outputs on the training data. It's the prediction out in the wild that really matters. At this point, it's worth calling out three common categories of machine learning algorithms. These are those meant to perform classification, that is, to predict categorical values such as ham or spam, and to produce yes no answers or answers which have labels. Another common category is used in regression problems. These are used to predict continuous values, such as the height or weight of an individual. And a third very common category of ML algorithms is used in clustering. This is where we are presented with a large quantity of data and the algorithm tries to find logical groups within that data, such as elements within the same group are all similar to each other and they are all collectively different from elements of other groups. We've discussed the differences between artificial intelligence and machine learning in some detail. It's now time for us to understand the differences between artificial intelligence and machine learning on the one hand and business analytics on the other. This is especially important in the transformation cloud era because users of data warehouses often tend to be very focused on business analytics. A subtle change in perspective might help business analysts and data analysts to get the most out of AI and ML. Business analytics tends to focus primarily on analyzing historical data in order to understand past performance and trends. This involves examining, for instance, past sales, past customer behavior, past financial transaction records, and other relevant data to identify patterns and insights. By studying what has happened in the past, of course, businesses can calculate key metrics such as growth, customer churn, operational efficiencies, and more. Business analytics is thus essentially backward looking. There's nothing wrong with this. It helps organizations to understand their historical performance and identify areas for improvement. Historical data analysis is, of course, essential for creating accurate reports, dashboards, and performance reviews. Business analytics also tends to focus heavily on identifying trends. Analysts will use statistical techniques in order to detect patterns and trends in the historical data of seasonal sales fluctuations, market shifts, and changes in consumer behavior. Recognizing these trends helps businesses forecast future performance and make informed strategic decisions. If an enterprise can identify a trend early, that might also highlight emerging opportunities or even emerging potential risks. A third attribute of business analytics use cases is a heavy emphasis on calculating metrics and reporting. Business analytics involves calculating and reporting these metrics to measure organizational performance. These metrics will include KPIs or key performance indicators such as net profit margin, return on investment, customer satisfaction scores, and more. Accurate metric calculation allows businesses to track their progress towards goals and objectives, and it provides a good, clear picture of overall current and past performance. Reporting these metrics in a structured format using dashboards and reports helps with decision making. Data can be presented in a format that is accessible and understandable to everyone from an executive audience down to relatively lower levels of the organization. Lastly, business analytics tend to be focused on describing and diagnosing issues. Descriptive analytics focuses on summarizing historical data to describe what has happened in the organization. Diagnostic analytics go a step further by investigating the reasons behind past performance, such as root cause analysis. Both of these sets of analytics techniques help organizations gain a deeper understanding of their operations. They can help to uncover underlying issues and drivers of performance. All of these aspects of business analytics make perfect logical sense in the context of an enterprise. However, they are also quite different from characteristics of AI ML use cases. To begin with, AI and ML typically tend to be forward looking, predictive, and prescriptive. That makes them different from a lot of analytics use cases, which, as we just described, tend to be primarily backward looking and descriptive. Predictive analytics use machine learning algorithms to analyze current and historical data, but the emphasis is on forecasting future outcomes. For instance, AI models will look to predict customer churn, sales trends, and demand fluctuations rather than to explain the causes of past phenomena. Prescriptive analytics go a step further beyond predictive analytics because they also recommend actions in order to achieve those desired outcomes. This forward looking approach enables organizations to proactively shape their future rather than focusing on understanding the past. Another attribute of AI and ML systems is automated learning and adaptation. These systems will automatically learn from data and improve over time even without explicit reprogramming. ML models continuously adapt as they are exposed to new data, refining their predictions and decisions. This capability allows AI systems to handle complex, dynamic environments where traditional business analytics methods might fall short. Automated learning enables businesses to respond more quickly to changes and optimize processes in real time, enhancing their agility and competitiveness. A third difference is that AI and ML techniques tend to focus on large datasets, in fact, very complex datasets beyond even their size, which are often out of scope in traditional business analytics. This is becoming even more true in recent years because a lot of advances in artificial intelligence have come in the field of dealing with unstructured data such as text, images, audio, and video. Now, these techniques are able to extract meaningful insights that were very difficult to obtain through any traditional methods. For instance, NLP or natural language processing is being used to analyze customer feedback from social media. Image recognition algorithms are being used to process visual data from surveillance cameras. Enterprises have become a lot more successful at unlocking the value from their unstructured data in recent years, and a lot of that success has come from AI and ML techniques. The intelligent automation of business processes is one of the core use cases of AI. This has reduced the need for human intervention in repetitive and time consuming tasks, for instance, AI powered chatbots that handle customer inquiries, ML algorithms that automate fraud detection, AI driven predictive maintenance to optimize equipment uptime. To drive home these differences in a real world setting, let's consider the example of a firm in the airline industry. We'll then see how such a firm might make use of business analytics and how it might differently leverage AI and ML. An airline might rely on business analytics to carry out revenue management, that is, to use historical flight booking data, seasonal demand patterns, and competitor pricing in order to estimate revenue. And then going a step beyond estimation, the firm might also use this data in order to optimize ticket pricing and try and maximize revenue. A favorable outcome would be to adjust ticket prices based on historical trends, seasonal demands, and competitor pricing. However, the same firm might make use of AI and ML techniques in very different fashions. It would rely on dynamic pricing and personalized offers using both historical data as well as real time data as it came in. This real time data might include customer profiles, social media sentiment, web browsing behavior, fast changing economic indicators, and weather forecasts. This would allow our airline to analyze real time booking conditions and implement dynamic pricing models. The outcome would be to adjust prices on a real time basis, based on predicted demand and also with personalized offers for customers. A couple of keywords summarize the differences between these two approaches. The AI ML approach is a lot more real time and it depends heavily on personalization. So, in summary, traditional BI based approaches have focused on historical data to identify trends and to optimize pricing. More modern AI ML based approaches leverage both historical and real time data and attempt to carry out dynamic pricing with personalization. Traditional BI based approaches have focused on descriptive and diagnostic analytics that focus on understanding past performance. More modern AI ML based approaches focus on predictive and prescriptive analytics to forecast and recommend actions. Traditional BI applications have focused on generating reports, which are often static, and dashboards that are then used for decision making. More modern approaches tend to focus on automating decision making and personalizing customer interactions. Generative AI, or Gen AI as it's more popularly known, is taking the world by storm. Let's spend some time understanding what generative AI is and how it differs from other more traditional approaches to AI. Most AI models, other than Gen AI models, are discriminative models. These are models that classify or categorize data. For instance, schematically, you can imagine that such a model might take in the images of a variety of animals during their training phase. All of those images would be labeled. So, here, during the training phase, we'd pass in images of cats, dogs, elephants, cows, and so on. That would give us a trained discriminative model, which could then be used for prediction or inference. During prediction, we would pass in a new unlabeled image, and then the output would tell us what kind of animal it is, along with an associated probability score. There's a lot going on here, so let's break this down. To begin with, we had a corpus of training data with a large number of observations. Here, each observation consists of an image along with the associated label. So taken together, the corpus has all of the entities that the model has to classify. And every observation has a label or category associated with it. This is then passed in during the training phase into the discriminative model. And the trained model is now going to take in a new observation as the input. That observation is going to be an unlabeled image. The output of this model is a new label along with a corresponding probability. Generative models work in a very different fashion. As their name would suggest, they focus on generating or creating new data instances. So the generative model is effectively sampling data and generating new data that did not previously exist. Of the words on screen now, perhaps the most important are that data is generated with a probabilistic model. It's not deterministic. This is why there's no guarantee that giving the same input or prompt to a generative model will result in the same output. It's also important to note that generative models generate new data that did not previously exist. Here is a conceptual representation of how a generative model might work. You can see over on the left that we have a number of faces. And then in the center, we have the generative model, which is then given a prompt of some sort, and the output is going to be an entirely new face. Let's break this down. Like discriminative models, generative models also need to be trained, and in fact, their thirst for training data can be even greater than that of discriminative models. So the training data needs to contain a very large number of samples. All of that training data ought to be relevant, i.e., it should be observations of the type of entity that needs to be generated. A trained generative model will be created from this training data. It will learn the features of the real data. Then, at prediction time or inference time, the trained model will accept an input or prompt of some sort, and it will use all of the learned features to generate a sample. Please note that it is not picking one of the input images that was fed in during the training. Rather, the generated sample is most likely to be unique. By their very nature, generative models are probabilistic rather than deterministic. A deterministic model would apply the same computations on the input and always produce the same result. But that's not how probabilistic models work. These must incorporate a random element because it is that randomness that leads to the creation of new entities. As a general statement, generative modeling is harder than discriminative modeling. Generative models need to be able to model and understand more complex relationships than those in discriminative models. Generative AI, or Gen AI as it's commonly known, is AI that's capable of generating text, images, or other media using generative models. You can use Gen AI offerings on the Google Cloud from Vertex AI, which is the flagship AI offering on the Google Cloud. Gen AI has exploded in popularity over the last year or so, and Gen AI applications tend to be powered by very large and complex models called foundation models that are trained on huge datasets. These models seem to have achieved astonishing success in mimicking human cognition. They're able to perform out of the box tasks such as question answering, summarization, and classification. Of these generative AI models, there's one type in particular that has attracted a lot of interest, and that is LLMs, or large language models. These are models that process natural language inputs and predict the next word based on what has come before. The name LLM comes from the fact that they deal with language and also because they are extremely large. These models have billions of parameters, all of which need to be trained to optimal values during the training process. When there are so many parameters that need to be set, the training process also has to be equally intense, and that's why a very large corpus of data is needed in the training of these models. In the last 18 to 24 months, everyone seems to be coming up with use cases for Gen AI. One of these is conversational bots. Gen AI improves conversational bots by enabling them to understand human language and also to generate human like responses. These bots can engage in much more natural and coherent dialogues, and this improves user interactions and customer support experiences. By leveraging LLMs, these bots can handle very complex queries. They can personalize their responses and even carry on multi turn conversations. This makes them suitable for a range of applications, including customer service, virtual assistants, and interactive entertainment. Another important use case is in content generation. GenAI is capable of producing very high quality text, images, and multimedia content. It can assist writers with the drafting of articles, the creation of marketing materials, and with generating creative content such as stories or poems. In the realm of digital marketing, GenAI can automate the creation of social media posts, blog posts, and ad copy. This ensures consistency and saves time and money. This technology can also help designers and artists by providing inspiration and generating visual content that aligns with their creative vision. Gen AI is excellent at document synthesis. It can generate comprehensive and coherent documents from various data sources. This includes summarizing lengthy reports, creating detailed financial analyses, and compiling research papers. By automating this synthesis process, Gen AI helps professionals save time and focus on higher level tasks. It ensures that documents are standardized, well structured, accurate, and relevant, and this makes it a valuable tool in fields such as the legal, medical, and academic professions. Generative AI is playing a surprising role in product discovery. It has helped in identifying and recommending products that match user preferences and needs. Retailers and e commerce platforms can use Gen AI to create dynamic and interactive product catalogs, tailored marketing campaigns, and real time recommendations, all of which ultimately boost customer engagement and loyalty. Let's now switch gears and talk about the importance of data in machine learning. As we've already discussed, machine learning is effectively any algorithm that learns from data. And that in turn means that the garbage in, garbage out principle is as true for machine learning models as for any software. ML models will only be as good as the data that they are trained on. Intuitively, of course, this makes sense, but even so, it's worth studying why exactly data is so important in machine learning. ML models can only deal with new, unseen data on the basis of old data which they have seen previously. This means that data is the foundation on which ML models are built, and high quality data is the only way in which a model can learn patterns, relationships, and features within the dataset. Without sufficient and relevant data, a model cannot accurately identify trends or make reliable predictions. For instance, training a model to recognize images of animals requires a diverse and comprehensive set of labeled images to make sure that the model understands the variations and characteristics of different animals. Models trained on inadequate or poor quality data will underperform or produce biased results. That leads us to the second factor to consider here, which is that the quality of the data influences model accuracy. Just to be clear, here we are talking about the accuracy of the model during prediction or inference. That is, how accurately it is able to cope with out of sample data that is out in the wild. The accuracy of an ML model is heavily dependent on the quality and quantity of the training data. If the training data was accurate, complete, and free of errors, then the model could learn effectively, and that in turn would allow it to make precise predictions when confronted with new, previously unseen data. All models after training will do a good job on in sample data. The real question is, how well does the model generalize? And it's here that the quality of the training data drastically affects the capability of the model to generalize. The ability of an ML model to generalize from the training data to new and previously unseen data is influenced by the diversity and the representativeness of the training dataset. A diverse dataset will cover a wide range of scenarios, and these will help the model learn how to deal with different situations and variations in the input. For instance, a speech recognition model trained on a diverse dataset that includes various accents, dialects, and colloquial language speaking styles will perform better across different speakers. If the training data is too narrow or too biased, the model may perform well on the training data. It may also perform well on a specific subset of new and previously unseen data, but it still might perform very poorly on certain subsets of the unseen data, and for all we know, those subsets might be the most critical in determining model performance. High quality training data allows for something known as feature engineering. Feature engineering is the process of selecting, modifying, and creating new features, that is, attributes of the input data. These attributes might help to uncover new patterns and thereby improve model performance. If the training data is of high quality, then data scientists will be able to tease out meaningful features by feature engineering, and this will enhance the model's ability to learn and make accurate predictions. Put differently, when the training data is of high quality, skilled data scientists will be able to combine and cut aspects of that data in order to perform feature engineering and build an even better model. Next, let's talk about 6 different attributes of good data. We can think of each of these as a dimension along which we can evaluate the quality of data. The first is completeness. Is all of the required data present and available? The second is uniqueness. Is each record in the dataset distinct, or is there a high level of duplication in the training data? A third positive attribute is timeliness. This refers to the relevance of the data at the time of use. Validity, which means that the data is within the expected range and follows the correct formats. Accuracy, that is, how closely the data reflects reality or truth. And finally, consistency. Consistency implies that different parts of the data tell the same story. There are no mutual contradictions within the data itself. Let's talk about each one of these, starting with completeness. As we noted, completeness refers to the extent to which all required data is present and available. High quality data must be complete in order to ensure that ML models have all the necessary information to learn patterns and make predictions. Incomplete data can lead to biased models and inaccurate results because the model might miss out critical information needed for making predictions. Completeness of data is required for informed decision making. It ensures that all relevant information is available for the model. Say, for instance, we had a model which tried to classify images as to whether they contain birds or not. If we trained such a model without ever showing it a picture of an ostrich, informed decision making would be difficult. Another factor here is bias reduction. Incomplete data can introduce bias and skew the model's predictions. For instance, missing demographic information in a health dataset can lead to biased treatment recommendations. Completeness enhances model performance. Complete datasets give a comprehensive view of the problem. For instance, in marketing analytics, having complete customer interaction data is very important in creating effectively targeted campaigns. Let's move on to the next important attribute, which is uniqueness. This ensures that every record in the dataset is distinct and the dataset as a whole does not contain too many duplicates. Duplicate data can distort ML models, leading to overfitting or biased results. Ensuring data uniqueness is very important for maintaining the integrity and reliability of the training data. Uniqueness is an important attribute of datasets because the less the redundancy in a dataset, the more the information content within it, and therefore the more accurate the insights that can be obtained by training on it. In customer segmentation, for instance, unique records ensure that each customer is only counted once. This attribute also helps with efficient resource utilization. Avoiding duplicates saves computational resources and storage and optimizes the training process. This is why deduplicating data during preprocessing is an important step. A third benefit is improved model generalization. More unique data helps models generalize better to new and unseen data by preventing overfitting. In fraud detection, for instance, unique transaction records ensure that the model learns diverse patterns of fraudulent activity. The third positive attribute of good data is timeliness. This refers to the relevance of the data when it is used. Data must be up to date and it should reflect the current state of the environment that it represents. Using outdated data can result in models that are not accurate or relevant to current conditions, and this can impact the decision making process. Timeliness can be absolutely critical in some use cases. Consider, for instance, an air traffic control system or even a hurricane forecasting system. Timeliness is important for current insights. Timely data ensures that models make predictions based on the latest information. In particular, in a fast changing environment, timeliness of the data can be of paramount importance. Responsiveness of the model to changing conditions also depends on timeliness. Up to date data allows the model to come up with quick changes, quick responses to changing conditions, and can enhance the operational efficiency of an enterprise. For instance, real time traffic data can help in dynamic route planning for logistics. Timely data is also necessary for correct and accurate trend identification. In healthcare, for instance, absolutely current patient data is essential for accurate diagnosis and treatment planning. A fifth important attribute is validity. This ensures that the data is within the expected range and follows the correct formats. Invalid data can lead to incorrect model training and unreliable predictions. In fact, it can even lead to crashes during the execution of the training process. Validity might be relevant in a dataset of consumer ages. These values need to fall within a realistic range, say between 0 and 120. Negative or excessively high values indicate invalid data. Likewise, email addresses need to follow the correct format as well. Transaction amounts in a financial dataset ought to be positive numbers where necessary. There are a number of reasons why validity is important. Reliable predictions will only be made from valid data. Invalid data is inherently unreliable, and predictions that are made on the basis of unreliable data are going to be unreliable as well. Invalid data tends to cause errors in programs and software systems. Valid data minimizes the chance of errors and anomalies that can distort model outcomes. For instance, in a sensor network, invalid readings might be a sign of inaccurate monitoring or measurement. Data validity is also a sign of healthy compliance and adherence to standards. In a healthcare scenario, for instance, if a reading of some vital sign of a patient, such as a temperature, was entirely invalid, then that might be a larger sign showing problems of compliance and adherence to healthcare standards. Next, let's talk about accuracy. This measures how closely the data reflects truth or reality. Inaccurate data might include incorrect addresses on shipments or deliveries, incorrect customer satisfaction scores, or incorrect patient diagnostic information. Highly accurate data is essential for building reliable ML models that can make precise and informed decisions. We previously discussed that invalid data is a sign that we cannot rely on the model. This is also true with inaccurate data. If the data is inaccurate, then that's a sign that there's a deeper problem with the system, and any model built on top of this flawed representation of reality is not going to be trustworthy. Again, like invalid data, inaccurate data leads to errors and misjudgments in decision making. And that's why having accurate data reduces costs and drives operational efficiencies. In a supply chain management model, for instance, inaccurate inventory data would always cause the system to be either overstocking or understocking. Overstocking blocks up precious working capital, and understocking can lead to stockouts and lost sales. Accurate data drives enhanced decision making. It provides a solid foundation on the basis of which informed and effective decisions can be made quickly. The last positive attribute that we'd like to talk about is consistency. This ensures that the data is uniform across datasets and systems and that it is free of internal contradictions. Inconsistent data can lead to confusion, errors in ML models, and problems with analyzing data from multiple or contradictory sources. For examples of failures of consistency, consider a multi branch retail chain where each store outlet has differing product names or product codes. Or imagine different sources of information about the same consumer where there is no unique ID that can be used to join these data sources and where the naming of the consumers is inconsistent. Data consistency is very important for seamless integration of data across multiple sources. And this seamless integration is very important because it allows an organization to build a holistic view of its data. In business intelligence use cases, for instance, consistent sales data and measurement consistently across regions is very important in enabling accurate global sales analysis. Consistency is also very important for error prevention. Even seemingly innocuous inconsistencies, such as in time zone or in the formats in which dates and times are stored, could lead to nasty and hard to track errors when we join on date columns, for instance. Finally, data consistency is a must for reliable comparisons. If we need to compare and benchmark across different data sets or different divisions of an enterprise, data consistency is absolutely paramount. AI is clearly shaping up to be an incredibly powerful technology. And as the line goes, with great power goes great responsibility. Let's now talk about what responsible AI is and some of the principles that lie beneath it. Responsible AI refers to the development and deployment of AI systems in a manner that is ethical, transparent, and aligned with societal values. This includes principles such as fairness, accountability, and transparency, and it ensures that AI technologies do not perpetuate biases, discriminate against individuals, or operate without oversight. Responsible AI is important because it builds trust in AI systems, and that in turn drives acceptance and confidence amongst users and stakeholders. Responsible AI proactively seeks to prevent harmful consequences such as reinforcing social inequalities or making unfair decisions that can affect people's lives. By prioritizing responsible AI practices, organizations can ensure that their AI initiatives are not only innovative but also ethically sound and socially beneficial. Let's enumerate 6 tenets of socially responsible AI and then talk about each one of them in detail. AI should be socially beneficial. It should avoid creating or reinforcing bias. AI systems should be built and tested for safety. AI should be accountable to people rather than to other AI systems. AI should incorporate privacy design principles, and AI should uphold high standards of scientific excellence. Let's talk through each one of these in turn, starting with the first. AI technologies should be developed with the aim of benefiting society as a whole, addressing important social challenges, and improving the quality of life of people. This involves ensuring that AI applications contribute positively to areas such as healthcare, education, and environmental sustainability. By focusing on social good, AI can help to bridge gaps in access to resources. It can enhance public services and drive inclusive economic growth. The goal is to use AI to solve real world problems in ways that are equitable and accessible to all. An AI based system can be said to be meeting this particular tenet if it addresses social challenges, if it drives inclusive economic growth, and if it enhances public services. For instance, AI in healthcare might be used to develop advanced diagnostic tools to improve the early detection of diseases such as cancer. AI algorithms may be able to analyze medical images to identify early signs of tumor with high accuracy and drive timely intervention and treatment. This kind of application not only improves patient outcomes but also reduces healthcare costs and prevents the progression of disease. The second tenet is that AI should avoid creating or reinforcing bias. AI systems should be designed in order to avoid perpetuating existing biases or creating new ones. It should ensure fair treatment of all individuals. This requires careful attention to the data that's used to train AI models because biased data can even inadvertently lead to biased outcomes. Developers must implement strategies to identify and mitigate biases throughout the AI lifecycle, right from data collection down to model deployment. Ensuring unbiased AI helps to promote equality and prevents discrimination based on race, gender, age, or any other characteristic. To be consistent with this tenet, AI systems should be built using diverse and representative data. This involves ensuring that the data used to train AI models is diverse and representative of the entire population. This helps to prevent the model from learning and perpetuating existing biases. Data collection processes also need to be aligned to include a wide range of demographic, geographic, and socioeconomic factors. Where appropriate, AI systems should incorporate bias detection and mitigation techniques. Implementing such techniques during the AI development lifecycle is essential. There is a host of statistical methods to identify bias in training data and model outputs. These methods need to be systematically applied. Regular audits and updates of the AI models can also help to maintain fairness over time. Design and testing need to be inclusive, ideally involving diverse teams of developers and stakeholders. This helps to ensure that different perspectives are considered and reduces the risk of embedding biased assumptions into the AI system. User testing should include participants from various backgrounds to identify and address potential biases. It is important for AI to be as transparent and explainable as possible. Providing clear explanations of how AI models make their decisions will allow stakeholders to understand and trust the system. This transparency will also enable users to challenge and correct biased outcomes. Let's turn to the third tenet, which is that AI should be built and tested for safety. AI systems need to be rigorously tested to ensure that they operate safely and reliably under a variety of conditions. This involves conducting thorough testing and validation to identify and mitigate potential risks. Safety protocols need to be in place in order to address unexpected behavior or failures and to minimize harm to users and the environment. Some practical aspects of ensuring that this tenet is satisfied include rigorous testing and validation of all AI based systems. This should include stress testing, edge case testing, and simulation based evaluations to identify potential failure points. Ensuring that the system behaves as expected in all scenarios will help to prevent accidents and malfunctions. AI systems should be built with plenty of fail safes and redundancies in place. These mechanisms ensure that even if one part of the system fails, alternative processes can take over to prevent harm. For example, in autonomous vehicles, redundant sensors and decision making pathways can ensure that the vehicle continues to operate safely even if one component fails. It's important for AI systems to be subject to continuous monitoring and maintenance. This will help to address any emerging safety issues at an early stage. AI systems should have regular updates, performance checks, and real time monitoring to ensure that the system remains safe over its operational lifespan. Proactive maintenance and timely updates can prevent potential safety hazards from becoming critical issues. Let's move on to the next tenet. AI should be accountable to people. So, AI systems should be designed with mechanisms for accountability, ensuring that their decisions and actions can be traced and understood by humans. This involves providing transparency in how AI models operate and the rationale behind their decisions. There should be a clear path for stakeholders to find developers and operators accountable. Clear lines of responsibility need to be established to ensure that humans remain in control and can intervene when necessary. Aspects of this point include the need for transparency and explainability, and the need for human oversight and control. The next tenet emphasizes that AI systems should prioritize the protection of user privacy. They should incorporate principles such as data minimization, anonymization, and secure data handling. This means designing AI applications to only collect the lowest amount of data necessary. They should ensure that personal information is protected, redacted wherever required, and not misused. Privacy considerations should be integrated into every stage of AI development from design to deployment. In order to adhere to this tenet, AI systems should incorporate data minimization. They should only collect the data that is strictly necessary for their operation. This reduces the risk of exposing sensitive information and limits potential for misuse. By minimizing the amount of data collected, these systems can also protect user privacy while still performing effectively. AI systems should incorporate anonymization and encryption. Anonymization will remove personally identifiable information from datasets and ensure that individuals cannot be easily identified. Encryption protects data both in transit and at rest. It prevents unauthorized access and ensures that sensitive information remains secure. Lastly, AI systems should give users control over their own data, allowing them to manage permissions and understand how the data is being used. This includes giving users the ability to opt in or out of data collection and processing and providing clear, accessible information about data usage policies. Transparency in data handling builds trust over time and empowers users to make informed decisions about their privacy. The last tenet that we are going to discuss here is that AI development should adhere to rigorous scientific standards. It should ensure that models are built on sound methodologies and are validated through peer review as well as empirical testing. This involves using robust and transparent research practices, maintaining integrity in data collection and analysis, and continuously improving the AI models based on latest scientific knowledge. Two key ways in which this tenet can be met: AI systems should be subject to rigorous testing and validation. This should test their accuracy, reliability, and robustness. Along the way, scientifically sound methodologies should be used to evaluate performance of the model across various scenarios and datasets. Secondly, a robust system of peer review and transparency is very important in developing AI systems. Sharing research findings, datasets, and algorithms with the scientific community allows for scrutiny, replication of results, and further improvements. All of these are important aspects of transparency. A final overarching tenet is that AI should be made available for users that accord with these principles. And going one step further, AI should not be made available for cases that do not accord with these principles. We will now switch our emphasis to discussing the products and services offered on the Google Cloud for enterprises looking to leverage artificial intelligence and machine learning. The flagship product for this on the Google Cloud is Vertex AI. This is a managed ML platform provided on the Google Cloud that allows developers and data scientists to build, deploy, and scale ML models seamlessly. It combines data engineering, data science, and ML engineering workflows, and thus enables your teams to collaborate using a common toolset and to scale your applications using the benefits of the Google Cloud. Vertex AI is a unified platform where you can manage all aspects of your ML projects. It combines the capabilities of AutoML and custom training with a wide range of ML frameworks, including TensorFlow, PyTorch, and Scikit-learn. It also ensures compatibility across different model architectures. Additionally, it provides built-in support for hyperparameter tuning and integrates tightly with other GCP services such as BigQuery and the AI platform for model development. Vertex AI has several options for model training and development. Let's talk about some of these in detail. AutoML on Vertex AI allows you to train models using tabular image, text, or video data without the need to write any code or manually prepare data splits. So, AutoML is a no code solution which is ideal for users who want to build ML models but lack extensive coding expertise and also don't have the time to build custom models. AutoML will automate the entire ML pipeline, including data preprocessing, model training, and hyperparameter tuning. Where AutoML is the no-code solution, custom training on Vertex AI is at the other end, in that it gives you complete control over the model training process. This allows you to pick your preferred ML framework such as TensorFlow, PyTorch, or Scikit-learn. This option is best suited for experienced data scientists and developers who need to implement specific training logic, custom algorithms, or unique model architectures. You can write your own training code, fine-tune hyperparameters, and manage the entire training workflow to meet your own precise requirements. Custom training also supports distributed training and GPU acceleration. This enables you to scale up and speed up the training process. A third option is Model Garden on Vertex AI. This is a curated repository where you can discover, test, customize, and deploy pre-built Vertex AI and select open source models. This feature is designed to accelerate the development process by giving access to a wide range of ready-to-use models for various applications, which range from natural language processing to computer vision. You can evaluate these models using your own data, modify them to better fit your specific needs, and then deploy them directly on Vertex AI. Model Garden simplifies the experimentation and prototyping phases. It reduces the time and effort needed to bring ML solutions to production. If there's one keyword that you need to keep in mind about Model Garden, it is pre-trained models. Finally, generative AI on Vertex AI grants access to Google's large Gen AI models. These are multimodal, called so because they support multiple modalities such as text, code, images, and speech. This option is particularly powerful for apps that need creative or complex content generation, such as text summarization, code completion, image synthesis, or speech generation. You can fine-tune these LLMs to align with your specific needs. Once tuned, these models can be deployed with your AI-powered apps and provide advanced generative capabilities. Expressed in terms of the machine learning workflow, Vertex AI has tools and technologies to help us with every step of that workflow, starting from data prep, moving to model training, then model evaluation and iteration, then deploying that model and using it in inference, and finally, monitoring model performance. Let's talk about each of these steps in turn and see how Vertex AI can help. Let's start with data preparation. Here, we extract and clean our dataset and perform EDA or exploratory data analysis to understand the data schema and characteristics that are expected by the ML model. Once that's done, we can then apply data transformations and feature engineering and split the data into training, validation, and test sets. A few options available under the Vertex AI umbrella include exploring and visualizing data with the Vertex AI Workbench, which supports notebooks and integrates with both cloud storage and BigQuery. We can also collaborate with the team to develop our model in Colab Enterprise. This is a version of Colab which is integrated with Vertex AI. For large datasets, we might want to consider using Dataproc Serverless Spark from a Vertex AI Workbench notebook. This will allow us to run Spark workloads without having to manage our own Dataproc clusters. Let's move to the next step in the ML workflow, which is model training. Once again, Vertex AI has us covered. If it's a no-code solution that we are looking for, AutoML is our choice. If we'd like to write our own training code and use custom models, then custom training is the way to go. We can perform hyperparameter tuning and optimize the hyperparameters of our models using custom tuning jobs. Vertex AI Vizier helps us to tune hyperparameters in complex ML models. Vertex AI experiments can be used to train our model using different ML techniques and then compare the results. And finally, we can register trained models in the Vertex AI model registry for versioning and handoff to production. Next, let's turn to Vertex support for model evaluation and iteration. Here, we can evaluate our trained model and make adjustments based on evaluation metrics. These might be precision, recall, or other similar metrics in order to evaluate and compare the performance of our models. These evaluations can be created through the Vertex AI model registry or by including evaluations in Vertex AI pipelines. Next, we move to the model serving and deployment stage. Here, Vertex AI has a number of formidable capabilities. We can perform online, that is, real-time predictions using pre-built or custom containers. The term online prediction here refers to predictions that are made using the HTTP protocol. Pre-built containers offer an easy-to-use environment which is optimized for server predictions. Custom containers give you more flexibility for dealing with specific dependencies and custom code. Vertex AI also supports asynchronous batch predictions. These allow us to generate predictions without deploying our model to an endpoint. This is ideal for processing large datasets where real-time predictions are not required. The batch predictions are executed as jobs and thus provide a cost-effective and scalable solution. If your model is a TensorFlow-based model, then Vertex AI has some special capabilities. It includes an optimized TensorFlow runtime that serves TensorFlow models more efficiently than open-source TensorFlow serving containers. Vertex AI also allows you to store features in a central repository known as the Vertex AI Feature Store. This can be particularly useful in the online serving of tabular models. This service will allow you to maintain consistent and up-to-date feature data across multiple models, ensuring high-quality predictions. Also, the feature store has tools for monitoring feature health, and this enables you to detect and address issues that might start to impact model performance. In keeping with Google's focus on explainability, Vertex Explainable AI helps you to understand how each feature contributed to your model's predictions. This feature attribution capability provides insights into the decision-making process of your models, and it improves transparency and trust. Also, Vertex Explainable AI can identify mislabeled data in your training dataset using example-based explanations. This can help you improve data quality and model accuracy. We've previously discussed how BigQuery has a feature known as BigQuery ML that allows you to build ML models using SQL. BigQuery ML integrates with Vertex AI, which supports deploying and obtaining online predictions for models trained with BQML. Once a model has been deployed and it's being used for inference, the next step is model monitoring. This is a never ending continuous process. Thankfully, Vertex AI model monitoring helps us to monitor models for issues such as training serving skew and prediction drift, and it can send us alerts when the incoming prediction data skews too far from the training baseline. Across every step of the machine learning workflow, Vertex AI has something to offer. It also supports ML ops or machine learning operations. This is a set of practices and tools that aim to streamline and automate the life cycle of ML models, right from development and training through deployment and monitoring. MLOps combines principles from DevOps, data engineering, and ML to ensure that models are reliable, reproducible, and scalable. You can think of MLOps as aiming to deliver CI/CD, that is, continuous integration and continuous delivery of ML models. So let's wrap up this discussion by talking about Vertex AI's support for ML ops. First, we can orchestrate workflows using Vertex AI pipelines to monitor, automate, and govern our workflows. Second, Vertex ML metadata lets us record the metadata, parameters, and artifacts that are used in our ML system. We can also query that metadata to help analyze, debug, and audit the performance of our ML models. Vertex AI experiments will allow us to track and analyze different model architectures, hyperparameters, and training environments to identify the best model for our use case. And Vertex AI TensorBoard will help us to track, visualize, and compare ML experiments to see how well those models are performing. The Vertex AI Model Registry serves as a central repository so that we can keep track of model versions. These provide an overview so that we can better organize, track, and train new versions. From the model registry, we can evaluate models, deploy them to an endpoint, create batch predictions, and view details about specific models and model versions. The Vertex AI Feature Store allows us to reuse ML features across multiple teams and multiple models. It's a centralized repository for organizing, storing, and serving ML features. This central feature store enables your enterprise to reuse ML features at scale, and this can increase the velocity of developing and deploying new ML apps in your organization. And finally, Vertex AI Model Monitoring helps us to monitor models for training serving skew and prediction drift and can send us alerts when our incoming prediction data is too far away from the training baseline. Now that we have a good sense of the capabilities of Vertex AI, let's turn our attention to some of the important machine learning offerings on the Google Cloud. If you are looking to build machine learning applications on the cloud, broadly speaking, you have four options. The first of these is BigQuery ML. This allows you to build and deploy ML models directly from within BigQuery, and you can do this using SQL queries. That means that you do not need a programming language such as Python or Java. This integration simplifies the process of creating ML models, and it makes ML modeling accessible to data analysts who use SQL day in and day out but are not that familiar with Python or Java. BigQuery ML is ideal if your use case needs models with large datasets that are already stored in BigQuery. Google also offers a host of easy to use pre trained APIs. These can help you with common machine learning problems for tasks such as image recognition, natural language processing, translation, and speech recognition. As the name would suggest, these are pre trained, which means that you can use them even if you do not have any training data in your organization. Also, these are extremely quick to deploy into production. You should look through all of the pre-trained APIs and check whether your use case is already covered by them, and if so, this is an excellent choice. A third option is AutoML, which can be thought of as no-code ML on the Google Cloud. AutoML is integrated with Vertex AI, and it allows you to carry out model training, hyperparameter tuning, and evaluation all without writing any code and just using a drag and drop point and click UI. AutoML will support a variety of data types including tabular data, images, text, and video without any prior ML or development experience. And finally, Also, within the ambit of Vertex AI is the custom training option. This allows you to build and deploy ML models using your own preferred frameworks and custom code. This gives you complete control over every step of the process. It allows for the implementation of the most complex algorithms and specialized models. You can also make use of distributed computing and GPU acceleration. So, if you are trying to choose the right ML solution, you can start out by asking whether pre trained models are fine or whether you'd like to build your own custom models. If you do not happen to have enough training data in your organization, then the choice is made. You almost have no choice other than to go with pre trained models. On the other hand, if it's custom models that you're interested in, then you can go with building models in SQL, using a no code solution, or by writing all of your code from scratch. As we can see, the Google Cloud has support for all of these. BigQuery ML allows us to write the ML models using SQL. AutoML is the no code solution, and custom training, of course, gives us complete control. Let's take a double click into the pre-trained ML APIs available. These include speech to text, text to speech, computer vision, the video intelligence APIs, natural language processing APIs, and APIs for translation and working with documents. It's also worth mentioning that of all of these offerings and services, AutoML and custom training are a part of the Vertex AI platform. BigQuery ML is on BigQuery, so it's not a part of Vertex AI, but it integrates closely with it. Let's cycle through these offerings, starting with BigQuery ML. As we've already discussed, BigQuery ML helps us to build ML models using SQL. And in this way, it democratizes machine learning because it allows data analysts and SQL practitioners to build, evaluate, and deploy ML models using their familiar Google SQL queries. This eliminates the need for extensive programming knowledge or expertise in ML frameworks. You don't need to program an ML or AI solution in Python or Java, and you can just do it in SQL instead. BQML integrates seamlessly with Vertex AI, so you can access and leverage all of the features on that platform. What this means in practice is that you can perform even sophisticated AI tasks such as text generation or machine translation directly from within BigQuery, and all of this still using SQL queries. Also, you can use models that were trained in Vertex AI, and these can be deployed and used for predictions in BigQuery. Google has also integrated Gemini with BigQuery. This allows AI powered assistance for BigQuery tasks, which means that Gemini will effectively help you with tasks like extracting insights or getting assisted SQL and Python data analysis. All of this from within BigQuery. Finally, it's also worth understanding how BigQuery ML is moving machine learning to the data rather than the other way around. Traditionally, performing ML tasks on large datasets required moving data between different systems. This is time consuming, resource intensive, and error prone. BigQuery ML brings machine learning directly to the data by enabling model creation and execution within the BigQuery environment. This streamlines the workflow, reduces data transfer overhead, and leverages BigQuery's powerful capabilities. You should strongly consider using BigQuery ML if you would like to make ML accessible to SQL practitioners who don't have broad programming skills in traditional languages like Python or Java, or if you would like to perform ML directly from within the BigQuery environment. Finally, you can also use BigQuery ML for custom model building based on your own organization's data. This data will most likely reside in BigQuery, which is a data warehouse offering on the Google Cloud. Finally, BigQuery ML is also a good choice if you would like to make use of integrations with Vertex AI and other AI services such as Gemini. Next, let's turn to the other branch of our use case tree. This is where we'd like to go with pre-trained models, maybe because we do not have sufficient quantity or quality of training data in our enterprise. Google supports a host of pre-trained ML APIs that we can leverage. Let's talk about some of the benefits of using these pre-trained APIs. The first is ease of integration. The pre-trained APIs are very easy to use. They are designed to be easily integrated into existing systems and apps through very straightforward API calls. Also, the pre-trained APIs deal with extremely practical use cases. Developers can typically make API requests for applications such as identifying objects or extracting text from images. That would be done using the Vision API. Likewise, you could use the Natural Language Processing API to analyze customer feedback by sending text data and receiving sentiment scores or identified entities. These APIs can be quickly incorporated into different workflows, such as automating customer support using chatbots, enhancing search functionality using image recognition, or transcribing and analyzing audio recordings with speech to text services. An important advantage of these pre trained APIs is the rapidity of deployment. Because pre trained APIs are so simple to use, your business can get new capabilities out to market faster with this option than probably with any of the other ML building options on the Google Cloud. Finally, these pre trained APIs are managed and maintained by the Google Cloud Platform providers, and that ensures that the models are continuously updated and improved. This ongoing maintenance ensures that the APIs remain robust and up to date. Also, these are built to scale. They are designed to handle very large volumes of requests efficiently, and that could be important for your use case as your applications scale. Let's quickly cycle through some of these APIs and their use cases. The Natural Language API analyzes and understands text. It performs sentiment analysis, entity recognition, syntax analysis, and content classification. Example use cases might be customer support analysis, where we can analyze customer feedback from reviews, emails, and support tickets. Another might be content moderation. We can automatically classify and flag inappropriate or harmful content in user generated text on social media, forums, or comment sections. The Vision API has capabilities like object detection, face detection, landmark detection, logo detection, and text extraction from images. It can be used to analyze visual content for various purposes. For instance, we might use object detection to automatically identify and count products on store shelves from images using this Vision API in retail inventory management. Another possible use case, automated image tagging. We can use image search functionality on a photo sharing platform by automatically tagging images with relevant keywords and descriptions. This particular use case would be leveraging a specialized Vision API known as the Vision API Product Search. There is also a visual inspection AI, which can help with visual inspection tasks in manufacturing and industrial settings. The feature Imagine on Vertex AI, that's spelled IMAGEN, can help you generate automated image descriptions. We can count on Google Cloud to keep expanding this list of Vision API capabilities. The Video Intelligence API allows for the analysis of video content with features such as short change detection, label detection, explicit content detection, and transcription of spoken content. This can support features such as contextual advertising. Here, we can identify appropriate locations in videos to insert ads that are contextually relevant to the video content. This is done by matching the time frame specific labels of the video content with the contents of the advertisements. Sports analytics might be another use case. This API can be used to analyze sports footage to detect and label key movements such as goals, fouls, or player movements. It can also be used to generate highlight reels, provide insights for coaches, and enhance the viewing experience for fans with real time statistics and replays. Google Cloud has a Document AI API that can be used to automate the processing of documents containing unstructured data. It can handle a variety of document types, including invoices, receipts, contracts, and forms. We can use this API for invoice processing to extract relevant data such as invoice numbers, dates, and amounts from scanned invoices. We can also use it for legal document management. It can help us to extract key terms, clauses, and metadata from contracts and legal documents, and to streamline document management and review processes. Next, the Translate API, which supports real-time translation of text between multiple languages. This can be used in multilingual customer support or in content localization. For instance, in order to automatically translate website content, create product descriptions, and marketing materials in new languages. Finally, the pre-trained APIs include support for both speech-to-text and text-to-speech. We can imagine applications in fields such as transcription services. The speech-to-text API can automatically transcribe audio recordings of meetings, interviews, and podcasts. Or voice assistants. These will leverage the text-to-speech API so that virtual assistants and interactive voice response or IVR systems can provide spoken responses and information to users. Let's now turn our attention to some of the ways of building custom models on the Google Cloud, starting with AutoML. It's worth noting that AutoML as well as custom training are both offered as a part of the Vertex AI platform. BQML is not a part of Vertex AI, it's integrated with BigQuery, but of course, it works very closely with Vertex AI. Remember that AutoML is the no code offering that we can use for custom model training. AutoML is a part of Vertex AI and it's a suite of ML tools that allows users to train high quality models with minimal effort and with the use of a point and click interface. You do not need deep expertise in machine learning to use AutoML. You can train your models on your own data. So, this is a crucial difference between AutoML and the pre trained APIs, which you should consider if you do not have training data. With AutoML, you train your models on your own data, but you do not write any code. Organizationally, AutoML is designed for data analysts, business professionals, all of whom are people who may not have much experience with development. It's also suitable for developers who may not have extensive backgrounds in machine learning or data science. Taken altogether, it's very beneficial for seasoned data scientists who are looking to expedite their model development process. Because of its intuitive interface and automated workflows, AutoML allows users with varying levels of technical expertise to work together and build and deploy ML models. This democratization of AI is an important driver of the cloud transformation era. AutoML can address a wide range of ML problems, including classification, regression, object detection, and natural language processing. For instance, you might use it to build a customer churn prediction model, or to classify images, or to detect objects in photographs, or to analyze the sentiment in text data. AutoML is very versatile, and this makes it suitable for industries such as retail, healthcare, finance, and manufacturing, because these industries tend to have fairly large proprietary datasets, which means they would be looking to train their own custom models. While discussing the pre trained APIs, we had mentioned that they are probably the fastest in terms of going to market with a new ML solution. Of course, there, the downside was that we could not make use of our own training data. AutoML is also very fast. It's not quite as fast from a go to market perspective as the pre trained APIs, but if we'd like to build custom models with our own data, then AutoML is certainly a lot faster than many alternatives. Also, because AutoML has been designed by Google Cloud professionals, the models are optimized for performance, and so you might be surprised by the results that you get even with a no code solution. These are often comparable to those obtained by expert data scientists working with custom models. Let's quickly run through the steps in building and training an AutoML model. First comes data preparation, and here we typically have our data in a structured format such as a CSV file. We'll ensure that it has all of the relevant features and labels for the ML task that we wish to perform. We might also need to clean the data, handle missing values, and so on. Once all of that is done, we'll upload that file to Google Cloud Storage or directly to the AutoML service. Next, we can use AutoML to split our dataset into training, validation, and test datasets. We can either let AutoML automatically handle the split, or we can manually specify the proportions for each dataset. This is also where we specify the target variable, for instance, the label that we wish to predict, and configure any additional settings, such as choosing the type of problem, maybe classification, regression, object detection, and so on. We can also select specific features to include in the model. Next, we can initiate the model training process. AutoML uses advanced algorithms to automatically select the best model architecture and hyperparameters for our data. The training process involves running multiple iterations to optimize that model's performance, and AutoML will abstract us away from all of the complexity. It will evaluate different models and hyperparameter combinations to find the most effective solution. This step might take some time depending on the size of the dataset and the complexity of the problem, but again, AutoML handles all of the heavy lifting. After model training, it's time for model evaluation and deployment. AutoML will evaluate the model performance using the validation and test datasets. It will then return detailed metrics and visualizations to help you, the end user, understand the model's accuracy, precision, recall, or any other relevant performance indicators. If the model meets your requirements, you can then proceed to deploy it directly from the AutoML platform. Deployment involves making the model available as an API endpoint that can then be integrated into your apps. You can use this endpoint to invoke the model for inference, that is, to make predictions on new data as that new data becomes available either in real time or in batch mode. AutoML works with various types of structured and unstructured data. Let's quickly examine these capabilities. AutoML can handle tabular data, which consists of structured data in rows and columns, such as data in spreadsheets or databases. This typically includes various features or X variables in the form of different columns. One of those columns will likely also be the target variable or the label that the model is trying to predict. For tabular data, AutoML can perform classification, regression, and clustering. AutoML also works with image data. Here, the tasks that we can use AutoML for include image classification, object detection, and image segmentation. Image classification involves identifying the main objects or scene in an image, for instance, distinguishing between cats and dogs. Object detection goes a step further by locating and identifying multiple objects within an image, for instance, detecting pedestrians and vehicles in a street scene. Image segmentation involves dividing an image into segments and labeling each segment, such as separating different parts of a medical image. AutoML has capabilities to analyze and extract meaningful information from video content as well. This includes tasks such as video classification, object tracking, and activity recognition. Video classification could be categorizing videos into genres. Object tracking might involve following the movement of a specific object across frames, and activity recognition might involve identifying actions such as running or jumping. This means that AutoML can be used in applications in security, entertainment, and sports analytics where video content is critical. Finally, AutoML can also work with text data. It has NLP tasks such as sentiment analysis, entity recognition, text classification, and translation, all readily supported. Sentiment analysis determines the sentiment expressed in a piece of text, such as positive or negative customer reviews. Entity recognition involves identifying and categorizing key entities such as the names of people, organizations, or locations. Text classification will assign predefined categories to text, for instance, in sorting emails to different folders. This gives us a good sense of the capabilities of AutoML. Let's now turn to talking about custom training. The Google Cloud allows custom training of models via a managed service that allows us to train our ML models using popular frameworks such as PyTorch, TensorFlow, and Scikit-learn. This managed service will provide the necessary infrastructure and resources to run complex training jobs efficiently and handle tasks such as provisioning the compute, managing the data, and monitoring the training. Despite all of this platform support, custom training definitely needs programming and model training experience. A solid understanding of both of these skills is very important. Users will need to write their own training scripts, define model architectures, and implement data pre-processing steps. Additionally, you need to be skilled in hyperparameter tuning and model evaluation in order to optimize the performance of your models. Given this high level of expertise that's needed for custom training, you probably should only use this option for models that are designed to meet very specific requirements and that need to achieve high levels of accuracy and efficiency. The flip side of all this complexity is maximum control and maximum customization. As its name would indicate, custom training gives us the highest level of customization so we can build models tailored to our unique needs. We have complete control over the entire machine learning pipeline, right from data pre-processing and model architecture through training algorithms and evaluation metrics. So this flexibility can be used to implement very complex models. Custom training is a driver of differentiation and innovation. It can be used to help your enterprise build models that no one else is building, and so can potentially lead to some spectacular breakthroughs. Custom training, like AutoML, is a part of the Vertex AI platform. Let's talk about some of its features. To begin with, infrastructure is fully managed for us. We never have to worry about provisioning resources for compute or managing servers. The Google Cloud will take care of all of that. We also only pay for compute resources that we actually consume during the training process. Vertex AI will take care of essential operational tasks such as job logging, queuing, and monitoring. The training jobs themselves are highly optimized for high performance. So, for instance, you should expect far better performance using custom training than if you were running your own training applications directly on a Google Kubernetes engine cluster. The platform helps to handle intensive ML workflows efficiently and provides tools like TensorBoard Profiler to identify and debug performance bottlenecks. The training process is carried out in a distributed fashion using a reduction server. This is an all reduce algorithm that increases the throughput and reduces the latency of multi node training on NVIDIA GPUs. This capability is crucial for handling large scale training jobs that require a lot of computational power. The Vertex AI platform also provides automated hyperparameter tuning so that we can run multiple trials of our training application with different sets of hyperparameter values. We define a range of values to test, and the Vertex AI platform will automatically discover the optimal choice of the hyperparameters within that range. Vertex AI ensures that we have a robust enterprise grade security. These include features such as VPC peering to limit network access and VPC service controls to mitigate the risk of data exfiltration. All of the usual features of Google Cloud Security, such as customer managed encryption keys and role based access control via the Identity and Access Management or IAM service, remain available as well. Let's talk a little bit about TensorFlow and the compute infrastructure which underpin Vertex AI. Let's start with TensorFlow. This is an open source machine learning framework. It was developed quite some time ago by the Google Brain team. It's designed to make it easy to develop, train, and deploy machine learning models. TensorFlow started out as a framework, and indeed it's still a framework at heart, but over the years it's grown to become a comprehensive ecosystem of tools, libraries, and community resources. It allows developers and researchers to build and deploy ML models very efficiently and supports a wide range of tasks, including deep learning, reinforcement learning, and other machine learning techniques. Let's discuss some of TensorFlow's formidable features. The first is flexibility and scalability. TensorFlow is designed to handle a very wide range of ML tasks, from simple predictions to more complex models. It can scale from running on a single laptop all the way to large distributed systems and mobile devices. TensorFlow is designed to perform massively parallel operations using basic units known as tensors. These are multi-dimensional arrays that represent the data which is processed by the models. These tensors enable TensorFlow to perform operations on massive amounts of data in parallel, and this leads to significant speed up of computation. The name TensorFlow originates from the manner in which data flows through these tensors in a computational graph. As we've already discussed, it has extensive library support. TensorFlow now supports a rich ecosystem of libraries and modules to cater to different ML needs. TensorFlow Lite is designed for mobile and embedded devices, and TensorFlow Extended or TFX gives full production pipelines for developing ML models at scale. In the early years, TensorFlow APIs were somewhat intimidating to use. That has largely been mitigated via integration with Keras. TensorFlow integrates with Keras, which is an easy to use higher level API that simplifies the creation and training of ML models. This Keras integration significantly lowered the level of technical expertise required in order to get the best out of TensorFlow. Keras has an intuitive interface, and that's combined with the very powerful backend of TensorFlow. TensorFlow has a technology stack where, at the lowest level, it takes full advantage of GPU acceleration. This is done via an infrastructure that's written in C++. The core of TensorFlow is written in C++. However, as a developer, you do not work with C++ at all. You'll just use Python for development, ideally via the Keras interface. On the subject of hardware, let's quickly understand what role CPUs, GPUs, and TPUs play in this process. CPUs, or central processing units, are the primary processors in a computer for general purpose tasks. They are designed to handle a wide variety of computing tasks, including running operating system jobs, managing input-output, and executing applications. CPUs typically consist only of a few powerful cores optimized for sequential processing. This makes them very good at performing single-threaded tasks quickly. However, they can become a bottleneck for more specific applications such as complex numeric computations or large scale data processing. In the context of machine learning, CPUs may handle model inference and smaller scale training, but will likely struggle when it comes for training large deep neural networks with large training datasets. And that's where GPUs come in. GPUs or graphics processing units are specialized processors designed to deal with parallel processing, specifically those related to rendering graphics. That was their original use case, but they have now become exceptionally popular in the world of ML training because their architecture, which relies on thousands of smaller, efficient cores, can be optimized to perform many operations simultaneously. While training complex machine learning models, there is an extremely large number of matrix multiplications and other operations that can be executed easily in parallel. By leveraging GPUs, ML practitioners can reduce training times significantly from days to hours or even minutes. This in turn enables faster experimentation and iteration. The Google Cloud also heavily leverages something known as a TPU or Tensor Processing Unit. This is a specialized hardware accelerator designed by Google specifically for machine learning workloads. Unlike either CPUs or GPUs, TPUs are optimized for performing tensor operations and possess specialized features such as a matrix multiply unit MXU and proprietary interconnect technology. This makes them ideal for accelerated AI training and inference. As their name would suggest, TPUs are specifically optimized to run TensorFlow. Now, users of TensorFlow can easily switch back and forth from CPUs or GPUs to TPUs with minimal code modifications. When you do use TPUs, however, you will get accelerated training and inference. What's more, when you are using TensorFlow on the Google Cloud, you likely are leveraging TPUs because they are integrated into the Google Cloud infrastructure. This makes them easily accessible for scaling ML workloads. At this point, let's pause and take stock and make sure that we can choose the right training solution for our specific use case. Let's start with BigQuery ML. This is a part of BigQuery. It's not a part of Vertex AI, but it integrates tightly with it. Use BigQuery if you would like to construct your ML models using SQL and if your data already resides in BigQuery. BQML models do have a training step, and the training data most conveniently should be taken from BigQuery. Next come the pre-trained APIs, which dispense with the training step altogether. There is no training here, the models have already been trained by Google. There's also no customization at all to your specific dataset. The benefit of the pre-trained APIs is that you skip the training step and can go to market with your ML model very quickly. That leaves the two offerings that come under Vertex AI. AutoML is the no-code offering. This allows us to create and train a model using a point-and-click UI and very little technical effort. We can use AutoML to quickly prototype models and explore new datasets. Finally, we have custom training, which is always an option when we'd like to create a training application optimized for our dataset and our targeted outcome. We have complete control over the entire end-to-end machine learning lifecycle. Let's set up a horse race of all of these different techniques. Let's begin with the dimension of data science expertise. Of these, custom training most definitely requires data science training and expertise. BigQuery ML, pre-trained APIs, and AutoML do not, and they all democratize ML in different ways. BigQuery ML makes ML available to data analysts who've been using SQL. Pre-trained APIs democratize ML access for organizations that are too small to have their own large training datasets, and AutoML democratizes ML access to those who have no technical or programming background. That leads nicely to our next dimension of programming ability. To use BigQuery ML, you need to know SQL quite well. For custom training, of course, we need extensive programming expertise. For AutoML, we need none. The use of pre-trained APIs lies somewhere in between. We need to have enough programming expertise to access those pre-trained APIs as clients, but we do not need to do anything too substantial in terms of programming. Next, in terms of time needed to train a model, pre-trained APIs score the best. No training is involved in these at all. In BigQuery ML and AutoML, training is relatively lightweight. Custom training involves the most heavyweight training process. Next, let's talk about how limited or not limited these techniques are. Of these, custom training has no limits at all on what you can try and achieve. However, the other technologies are all somewhat limited based on the types of ML problem that you can solve using them. Can we manually optimize our models? The answer with AutoML is no, and the answer with custom training and BigQuery ML is unambiguously yes. With pre-trained APIs, this is not applicable because the model is actually built and maintained by the Google Cloud and not by us. In terms of how much control we have over the training environment, we have complete control in the case of custom training. AutoML gives us some limited control, BigQuery ML gives us no control at all, and pre-trained APIs once again do not feature a training environment at all because the models do not have a training step. Finally, in terms of limits on the training data size, there are limits in BigQuery ML and AutoML. There are no limits when it comes to custom training. And again, pre-trained APIs feature an NA because there is no training step here at all. Finally, there are also additional AI solutions available on Vertex AI. This is a grab bag listing some of them: Dialogflow, Contact Center AI, Gemini Code Assist, Vertex AI Search for Retail, and Cloud Talent Solution. These are relatively niche, as their names would suggest. Dialogflow, for instance, is used to build AI powered chatbots and can help to transform your contact center. CCAI, or Contact Center AI, is an end to end contact center as a service solution. It has its own call center solution and a set of Google AI services for contact center use cases. Gemini Code Assist offers code recommendations in real time. It will suggest functions and code blocks, identify vulnerabilities and errors, and also suggest fixes. It also interoperates with Cloud Shell or Cloud Code IDE extensions for VS Code and JetBrains. Vertex AI Search used to be called Discovery AI, and it helps enterprises get Google quality search, browsing, and recommendations on their digital properties. Cloud Talent Solution is meant to match high quality job results to job seekers and aims to go far beyond the limitations of typical keyword based methods. Generative AI has become incredibly popular in the last year or so. Let's now take a quick look at the workflow for generative AI on Vertex AI. Here is the full architecture for a Gen AI use case on the Vertex AI platform. Obviously, this is a fairly complex architecture, but as end users, we are focused only on specific aspects of it. The workflow is typically kicked off with a prompt. Platform support for prompt design and engineering is obtained from the tool Vertex AI Studio UI. The prompt is a request that's sent to a Gen AI model in order to elicit a response. Depending on the model, the prompt might contain text, images, videos, audios, documents, or other modalities. When a model allows you to interact with it using different modalities, that model is said to be multimodal. Creating a prompt to get the desired response from the model is a practice known as prompt design. Prompt design is a process of trial and error, but there are good design principles and strategies that you can use in order to nudge the model to behave in a desired manner. Vertex AI Studio offers a prompt management tool to help you manage your prompts. The prompt will then be sent to a Gen AI model for response generation. Vertex AI has a variety of Gen AI foundation models. These are accessible via a managed API, and these include Gemini for advanced reasoning, multi-turn chat, code generation, and multimodal prompts. Imagen, that's spelled IMAGEN, that's for image generation, image editing, and visual captioning. MedLM, which is a medical question answering and summarization model. MedLM is not yet available in public GA status. We can customize the behavior of Google's foundation models so that they consistently generate the desired results that we want without complex prompts. This customization process is called model tuning, and it allows you to reduce the cost and latency of your requests by simplifying your prompts. Vertex AI also offers model evaluation tools to help you evaluate the performance of your tuned model. Once that tuned model is production ready, you can deploy it to an endpoint and monitor performance as in any standard MLOps workflow. At this point, there might also be some request augmentation. In AI, this refers to the process of enhancing or modifying the initial user request to improve its relevance, accuracy, or completeness. Request augmentation might take the form of contextual enhancement, where we give more information to the model than the user's query contained. It might also take the form of disambiguation or expansion. Vertex AI has multiple request augmentation methods to give the model access to external APIs and real time information. Grounding is a way to connect the model response to a source of truth, such as your own data or web search. This serves to reduce hallucinations. RAG is a second technique here. This connects models to external knowledge sources such as documents and databases. And finally, function calling is a way in which the model can interact with external APIs to get real time information in order to give real time answers to user queries. Once the response has been generated, Vertex AI will check whether citations ought to be included with that response. This will typically occur if a significant amount of text in that response came from a single source. Then that source will be added to the citation metadata in the response. The last layer before the response goes back out into the wild, that is back to the user, is a layer of responsible AI and safety. Vertex AI will check both the prompt and the response for how much the prompt or response belong to a safety category. If the threshold is exceeded for one or more of these safety categories, the response may be blocked and Vertex AI might return a fallback response. We started this course off by defining artificial intelligence (AI) and machine learning (ML), establishing a clear understanding of these foundational concepts. We introduced common terms in machine learning such as features, models, and training. We also contrasted AI ML with business analytics, highlighting their distinct purposes and how they complement each other in driving data driven decision making. Next, we learned about generative AI, exploring its capabilities in creating new content and its potential applications. We discussed the attributes of good data, emphasizing the importance of data quality, diversity, and relevance for effective machine learning. Additionally, we delved into responsible AI, understanding the ethical considerations and best practices for developing and deploying AI systems that are fair, transparent, and accountable. Finally, we explored Google's Cloud Vertex AI, a comprehensive platform for machine learning. We learned how to perform machine learning on Google Cloud, leveraging tools like AutoML for automated model training and custom training for more tailored solutions. We also covered TensorFlow and the compute infrastructure necessary for running machine learning workloads efficiently. We also saw how BigQuery ML is suitable for building ML models in SQL, eliminating the need for Python or Java expertise, as well as how pre-trained APIs for common use cases such as vision, video, and speech allow organizations to leverage AI even if they lack training data themselves. In conclusion, we built a solid foundation in AI and machine learning as supported on the Google Cloud. We're ready to move on to the next course in this journey: infrastructure and application modernization. Digital transformation with the cloud involves using cloud technologies to drive profound and positive organizational change. Getting onto the cloud is the first step. By learning about migration strategies, virtual machines, and containerized environments, organizations can achieve better scalability, cost savings, and performance. In this course, you will learn about different migration strategies such as lift and shift migration and improve and move migration. You will become familiar with essential Google Cloud migration terms and follow the cloud migration path. Additionally, you will explore various migration tools for compute and data to move workloads to the cloud efficiently. Next, you will discover the numerous benefits of running workloads on the cloud, including scalability, cost efficiency, and enhanced performance. You will dive into running compute on virtual machines and explore Google Compute Engine. Finally, you will explore running compute on containers and learn the principles of the microservices architecture. You will manage containers using Kubernetes and study the architecture of a Kubernetes cluster. You will work with Google Kubernetes Engine, learning how to deploy, manage, and scale containerized applications efficiently. We are now going to talk about infrastructure and application modernization. In practical terms, what this comes down to is figuring out how to move in the correct fashion to the cloud. That in turn comes down to a choice between migrating to the cloud and starting from scratch on the cloud. Let's begin by introducing those two terms, and then we will set about seeing how we can achieve these objectives on the Google Cloud. Infrastructure modernization can be thought of as updating and optimizing the underlying IT framework to leverage cloud native technologies, enhancing performance, scalability, and resilience. Note the emphasis on those three attributes: performance, scalability, and resilience, which of course are a primary attraction of moving to the cloud. Next, focus on the term cloud native. So, infrastructure modernization is about transforming and optimizing the IT of an enterprise to make use of the cloud. This process might include migrating from on prem data centers to cloud environments, adopting virtualization and containerization, and implementing advanced management and orchestration tools. The goal is to achieve improved performance, scalability, and resilience, enabling your enterprise to respond more effectively to changing demands. For all of this to work on the cloud, we will also need to integrate resource provisioning, monitoring, and maintenance in an automated fashion. Once the infra has been modernized, the next step is to modernize the apps. Application modernization focuses on updating and enhancing your software apps by refactoring, re architecting, or if necessary, rebuilding from scratch in order to take full advantage of cloud capabilities. The cloud has great support for the incorporation of microservices architectures, APIs, and serverless computing. And so, by modernizing your apps, your enterprise can make use of these features. And in doing so, it can reduce costs, enhance user experience, and accelerate time to market for new features and services. Going from the abstract to the practical, application modernization really comes down to a choice. We can either migrate existing apps to the cloud, or we can start from scratch on the cloud. Migrating to the cloud involves moving existing on prem applications, data, and infrastructure to a cloud environment. This is needed when organizations would like to get the benefits of the cloud, such as scalability, cost savings, and improved disaster recovery, but without completely overhauling their current systems. The characteristics of cloud migration include careful planning, data transfer, rehosting or replatforming applications, and ensuring compatibility with other cloud services. On the other hand, starting from scratch on the cloud involves designing and building new apps and using cloud native infrastructure. This approach is often better when you're launching new projects or when legacy systems are simply too outdated to justify migrating them. This approach will better enable us to make use of cloud native architectures such as microservices, serverless computing, and the use of managed cloud services. This method is ideal for organizations that are looking to fully exploit cloud capabilities and are focused on rapid innovation, seamless scalability, and optimized performance from the outset. Google has its own lexicon of specific cloud migration terms such as retire, retain, rehost, replatform, and so on. But in colloquial usage, there are three broad types of migrations: lift and shift, improve and move, and rip and replace. Lift and shift migration involves moving apps to the cloud with little or no modification. Most likely, you will simply port your existing application over to a VM instance on the cloud. This approach takes the least advantage of cloud capabilities, but it's the fastest migration strategy. It's the easiest to implement and suitable for organizations that want a quick transition with minimal disruption to operations. The second approach, colloquially known as improve and move, involves refactoring existing apps to better leverage cloud offerings. This process is more involved than a lift and shift, and the term refactor often implies that you are changing the code. This leads to a slower migration process, but on the other hand, it enables your enterprise to benefit more substantially from cloud native features. This method is suitable for organizations looking to optimize their applications for better cloud utilization. A third option is rip and replace. This involves rebuilding your app from scratch in order to fully exploit cloud benefits. This approach is labor intensive and takes a lot of time. However, it also offers the greatest possible upside. That upside can come from truly transformational improvements in performance, scalability, and flexibility. This method is ideal for enterprises that are really looking to modernize their IT infrastructure and are totally bought into the idea of the transformation cloud. Let's talk a little bit more about each of these, starting with lift and shift. Some of the reasons why your enterprise might go with this approach: quick implementation. As we've discussed, this is the fastest migration strategy. It involves moving workloads to the cloud with minor or no modifications, usually taking use of infra as a service offerings like GCE VM instances. The speed of implementation could be an important factor if your organization is looking to meet immediate goals or immediately get into compliance with some regulation. As you might imagine, this will likely lead to minimal changes. The workload can operate largely as is in the target environment without significant refactoring. This allows your enterprise to maintain your existing applications and infrastructure, ensuring continuity and reducing the risk associated with the migration. This approach makes sense for stable apps where you do not want to carry out extensive optimization or enhancement. A third, more cultural and organizational reason has to do with the preservation of existing skills and tools. Teams will be able to continue using largely the same set of tools and skills that they were utilizing before the migration. This reduces the need for extensive retraining and allows your IT staff to maintain productivity during the transition. It also simplifies that migration process by leveraging their existing knowledge, and it minimizes the learning curve associated with new cloud native technologies. All of this might make lift and shift sound simple and easy, but it rarely is. There still is a lot of planning and hard work required. To begin with, we still have to ensure the compatibility of the target environment and that we get adequate performance on it. Hopefully, the migration will require minimal refactoring, but it's still essential to ensure that apps are compatible with the new target cloud environment. The planning should include thorough testing to verify that performance levels are maintained or improved post migration. Assessing cloud infra capabilities and then aligning them with your app's requirements can help to prevent unpleasant surprises and potential recriminations. A second consideration is cost management. Although lift and shift ought to be quick and straightforward, this might not fully exploit all of the cost efficiency benefits of the cloud. Your enterprise should plan for the potential cost implications, such as the inefficient resource utilization and higher operational costs that we might end up with because our application is not making use of the best of the cloud. Implementing cloud cost management practices, such as monitoring and optimizing resource usage, can help mitigate these concerns. A third factor to keep an eye on, as always, is security and compliance of workloads. So, the migration phase must include a comprehensive review of the cloud provider's security features and compliance certifications. Organizations must also implement the necessary security controls and monitoring mechanisms to safeguard data and apps in the cloud environment. So, to tie all of this together, here are the benefits and downsides of lift and shift. The first benefit is the speed of migration. The second is the lower initial cost because it requires minimal changes to your existing apps. And the third is operational continuity. On the other hand, we don't get the best of the cloud. We are only going to derive limited benefits from the move. We might end up with potential inefficiencies, the worst of both worlds in terms both of cost and performance. And finally, a lift and shift migration almost always incurs technical debt. This is going to lead to issues that will have to be resolved later on down the road, and the cost and complexity of those are currently unknown. From lift and shift, let's move on to the next model, which is known as improve and move. Here, the existing applications are usually refactored in order to better leverage features of the cloud. Why might your organization choose the improve and move approach? One reason is to better leverage cloud native capabilities. This approach is pretty much ideal when your app architecture or infra are simply not supported in the target cloud environment. So you can take this opportunity to modernize your workload during the migration, and in that way get the full advantage of features like auto scaling, managed services, and enhanced security. So the move to the cloud might take more time, but once the move is done, you've got better performance on all those attributes. Another would be to carry out major workload updates. Let's say that your workload needs to be changed in any case. The migration is now a great opportunity to refactor and optimize your apps and ensure that they are up to date with the latest technological advancements. Finally, even though the lift and shift might seem to be the quickest and even the cheapest in the short run, in the longer term, This approach, that is the improve and move, might work out to be more efficient. As we already discussed, the lift and shift often incurs a significant amount of technical debt, so it's only postponing the need for a refactoring. You might decide that it's worthwhile taking the hit right now. Now, any migration is going to require a lot of planning, and improve and move migrations take longer and are more complex. So, this requires a greater time and effort. The product roadmap, operational requirements, regulatory compliance, all of these aspects need to factor in this extra time and effort. Secondly, in this approach, we typically are going to refactor our apps. The term refactor usually involves significant changes to the code base and architecture, and that in turn will require careful analysis of the existing system, identifying the correct modifications to make, and then implementing those changes. Finally, your teams will probably need to do a lot of work to get the best out of the integration with the cloud services. Your enterprise will need to evaluate different cloud provider offerings, select the appropriate offering, then select the appropriate services on that offering, and then design the applications in order to leverage those services. Proper integration is essential if you are to realize the desired level of performance, scalability, and cost efficiency. It's also worth remembering that with an improve and move migration, expectations within the organization are also going to be high. The cost and performance attributes after the move better live up to these expectations. So, this approach, like any other, has its own upsides and downsides. The first upside is the hope of enhanced performance and scalability because we are now making use of cloud native capabilities like auto scaling and load balancing. Secondly, almost certainly, this move will reduce the technical debt of your enterprise. Refactoring the applications is going to make future updates and maintenance easier. It will also ensure that your apps are built using modern best practices and technologies, which will hopefully simplify and reduce future development efforts. Thirdly, this approach will very likely lead to better resource utilization. The refactored app will hopefully be able to take care of cloud features like fine grained pricing, pay for what you go, and so on. This in turn will lead to more efficient use of cloud resources and reduce operational costs and improve cost effectiveness. To balance this, a clear downside is the longer migration time. Improve and move strategies take time, and all stakeholders at all levels of your enterprise need to be on board with this. In terms of initial upfront costs, this approach is likely to be more expensive because there are going to be significant upfront efforts in terms of development time, expertise, and resource allocation. Your organization will also likely need to invest in skilled personnel who can make use of the new tools and technologies. All of this comes with a price tag that has to be paid before all of the benefits start to accrue. Finally, this approach has complexity and risk. Refactoring an application doesn't always go as planned. There might be bugs, performance issues, and other unforeseen developments. Ensuring that those refactored apps function correctly in that cloud environment will require meticulous planning, testing, and risk management. The third and most ambitious of the types of migrations colloquially are referred to as rip and replace. As the name would suggest, this is where you decide to rebuild your apps from scratch in order to fully exploit benefits of the cloud and also along the way thoroughly modernize and future proof your applications. Rip and replace represents the opportunity for a fresh start, and so it's often an attractive option. This is particularly true if you are struggling with the limitations of your current apps. If the current application isn't meeting your goals or performance expectations, then rip and replace allows you to get rid of it and completely redesign and rewrite it as cloud native. So, again, if you're struggling with your current apps and drastically need to improve them and leapfrog, as it were, rip and replace might be a good option. Secondly, this approach almost eliminates technical debt from legacy apps. This leads to a maintainable and adaptable code base, and it also allows you to get rid of all of the mistakes that had been made over time in creating the old apps. And even more than an improve and move approach, this allows you to truly maximize the benefits of the move to the cloud. Here, you can take full advantage of all of the cloud's most advanced features and services, unconstrained by your current application architecture. There's no need to refactor or change that architecture. You can fully commit to technologies like serverless computing, microservices architectures, and automated DevOps. This approach requires the most planning and should be carefully thought through before it's adopted. To begin with, it has very significant development time. The entire software development life cycle will have to be gone through from requirements gathering all the way through to testing and deploying. This extensive process will ensure that the new system meets all of its business requirements and performs optimally in the new cloud environment. It's also worth noting that the expectations are likely to be sky high when that transformation actually takes place. This approach calls for extensive relearning and adaptation. Teams will need to understand and adopt cloud native principles and technologies. These might be very new to them. Your enterprise should plan for comprehensive training for the development and the ops teams in order to equip them with the correct skills. Also, the cloud environment is relatively fast changing, and so your organization will need to stay updated with those cloud advances as they happen. Rip and replace approaches call for very significant resource allocation, and you'll need management buy in your enterprise. This level of resource allocation usually can only be guaranteed if there is a true champion of this approach, and that champion better be as high up in the corporate ladder as possible. Botched rip and replace operations can be severely career limiting for large numbers of people. So, to summarize, a rip and replace approach has many benefits, starting with full cloud optimization. It also leads to a great modernization, in fact, a future proofing of your enterprise IT infrastructure and apps. And it also leads to much better maintainability. A completely redesigned and rebuilt application is easier to maintain and update. You are eliminating all of the legacy code and technical debt. There are the corresponding downsides, the first of which is the high initial costs. This is because of all of the upfront investment in terms of time, resources, and financial costs. You also need to plan for an extended development timeline. This takes the longest of the three approaches to migration. And finally, always keep an eye on the increased risk. Completely redesigning and rewriting all of your applications, or even one of your applications, introduces great risk in terms of potential project delays, budget overruns, and unforeseen technical challenges. You'll need to have very good risk management and contingency planning in order to undertake this successfully. Next, we will turn to understanding the specific concepts and terms that Google uses while talking about migrations or moves to the cloud. The terms that we discussed so far, such as lift and shift, were colloquial, which meant that they are commonly used without any standard definition. The terms that we will now talk about have very specific meanings when employed in the context of the Google Cloud. Let's start with the term workload. In the context of cloud migration, and specifically in the context of the Google Cloud, a workload refers to a specific application, service, or capability that is executing within a computing environment. This could be either on prem or on the cloud. Workloads can include a variety of components such as containers, databases, VM instances, each of which serves distinct functions within the IT infrastructure. During the cloud migration, workloads are going to be transferred from on prem data centers to cloud environments, the aim being to leverage cloud benefits such as scalability, performance, and cost efficiency. Given a workload, there are a number of different options that an enterprise could use in terms of migration. The first is to retire the workload, which is to remove it from a platform because it's unnecessary, not cost effective, out of date, insecure, or incompatible with the new current environment. The term retire is pretty intuitive. However, the next term, which is retain, can be a little hard to pin down. In the context of the Google Cloud, retaining a workload means intentionally keeping it in its current environment, whether that's on prem or in a hybrid cloud setup. This decision is typically made when the workload is essential, but it is better managed outside the cloud provider's full control. So, again, if a workload is retained, then it's typically not going to be on the Google Cloud. Workloads that are going to be moved to the Google Cloud might be rehosted, replatformed, refactored, or reimagined. Let's define each of these terms in turn. Rehosting, as used in the Google Cloud lexicon, is pretty much our lift and shift. This involves migrating a workload to the cloud without changing the code or architecture. Next comes replatforming. This corresponds to the improve and move that we discussed. This involves migrating a workload to the cloud with some changes to the code or architecture. This approach will enhance performance, scalability, and cost effectiveness. Depending on how extensive the changes to the workload are, it might qualify as a refactoring. This involves changing the code of the workload in order to take full advantage of cloud native features like microservices or serverless architectures. The difference between refactoring and replatforming is a matter of degree. We'll discuss both of these in more detail. And finally, the most dramatic option is reimagining. This corresponds to the rip and replace. This is usually accompanied by a comprehensive overhaul of cloud strategy and the integration of advanced technologies like AI and ML. Let's talk about each of these cloud migration terms in detail. Let's start with the first, which is retire. Security considerations are very often behind decisions to retire a workload. You might want to remove outdated and potentially vulnerable workloads. This will improve the overall security posture of your enterprise and reduce the attack surface. You ought to ensure that only necessary and secure workloads are active, and this minimizes the risk of a breach. When your enterprise retires a workload, you free up IT resources, including storage and computing power, which may be reallocated to more critical tasks. It also helps with resource reallocation in terms of people and headcount and reduces operational costs. Why might your enterprise decide to retire a workload? Well, because it's obsolete, costly to maintain, or if better alternatives are available. Outdated software that no longer meets business needs or security standards can and should be decommissioned. Let's move on to the next term, which is retain. Retaining a workload means intentionally keeping that workload in its current environment, which could be either on prem or in a hybrid cloud. What is implied here is that the workload is not moved to the Google Cloud. Why might we choose to retain a workload? Well, that workload might be critical to business operations and it might be better managed on prem with direct oversight and full control. This might be the best option for applications which have very specific performance or security requirements. It's also worth keeping in mind that retained operations might well be operating in a hybrid cloud environment. So, our statement that retained workloads are not typically moved to the Google Cloud might not necessarily be true, in that the retained workload might be in a hybrid multi cloud environment. One of the clouds supported might be the Google Cloud. However, the primary locus of control will probably reside outside the Google Cloud. That brings us to the next option, which is rehosting. This is pretty much synonymous with the lift and shift, which we've discussed in detail. Here, we are going to migrate the workload without changing its code or architecture. Rehosting is going to be the simplest and quickest migration method, but it may not fully use all of the cloud benefits. For instance, let's say that you are running a MySQL server on-prem. A rehosting approach would not make use of Google Cloud SQL. Rather, you would choose to run MySQL on a Compute Engine VM instance of your own. You can see that this is obviously a suboptimal approach, but that's because Google happens to have Google Cloud SQL, which is a managed service for MySQL. Now think of the same scenario where you are making the transformation from a local Oracle server. Now, a lift and shift approach might seem the most realistic. However, as that same example shows, we probably should think of a rehost as a first step in the cloud migration process. It enables your enterprise to get started quickly with cloud adoption before making a lot of optimizations. And at least some of the benefits of the cloud, like scalability, disaster recovery, and compliance with many standards of encryption, for instance, will become immediately available on day one. Clearly, there are drawbacks, as we've discussed. Rehosting will not optimize your workload for the cloud, and this will likely lead to management and scaling challenges over time. If you decide that you'd rather confront those challenges right here and now, then replatforming might be a better option. This is the move and improve. Here, we migrate the workload to the cloud with some changes to the code or architecture. Again, the keyword here is some, because these changes are not going to be as extensive as in the case of refactoring. Continuing with the example of our on-prem MySQL server, if we chose to replatform, we would be making use of the Cloud SQL managed service, which has offerings for MySQL as well as Postgres and SQL Server. Replatforming will involve migrating the workload to the cloud with some changes, but these will enhance performance, scalability, and cost effectiveness. You can imagine, for instance, that once we switch to Cloud SQL, you will immediately get the benefits of features like high availability or read replicas. Of course, this approach is more complex and requires more planning and testing in order to ensure that modifications improve workload functionality and don't subtract from it. When you choose to replatform, you are taking a middle path. It's a balance. At one extreme is the rehost, which is the lift and shift, and at the other extreme lie options like refactor and reimagine. The next option, and one step up in terms of ambition, is the refactor option. When we refactor a workload, we are going to make changes to the code and the architecture, and these changes are going to be quite extensive. The aim is to take full advantage of cloud native features like microservices or serverless architectures. If you go back to our example of the on prem MySQL server, then when we refactor the workload, we might decide to switch away from Google Cloud SQL and instead go with something like Cloud Spanner if Cloud SQL was not living up to our performance requirements, or maybe even a document database like Firestore if we decide that unstructured or semi structured data is more important to us. Again, the difference between refactor and reimagine is also a matter of degree. For instance, a move to Cloud Spanner probably lies somewhere between the two. A move to Firestore is probably squarely a refactor operation. Refactoring our workload gives us the chance to switch to more efficient and scalable options. Imagine recoding your application to use Firestore or Spanner instead of MySQL. As you can imagine, that's complex and it's going to lead to deep changes in the code base. However, over the long run, it's very likely to lead to some great benefits, despite all of its complexity. The final and most sweeping change possible is to reimagine the workload. In our example of the on prem MySQL, reimagining might involve a move to Cloud Spanner, or maybe something even more disruptive. You might decide that you don't need transaction processing support at all. What you really need is an enterprise data warehouse, and you might move from MySQL to BigQuery, or depending on the use case, even Bigtable. Reimagine is a good choice when you'd like to go in for a big strategic shift in how your enterprise uses technology. Because it's effectively a blue sky approach, it leads to a great deal of innovation. Finally, it's very likely to lead to better customer focus. Why is that, you ask? Well, because in the absence of a reimagine, you are constrained by all of the legacy and the changes that need to be made. Going with the reimagine option allows you to take a fresh look at the needs of your customers and partners. For an enterprise that is not currently on the cloud, the path to getting onto the cloud can seem quite daunting. And that's why it makes sense for us to talk about this path, the migration path, as well as various migration related services that are offered on the Google Cloud platform. It can be helpful to think of the migration path as consisting of four phases: assess, plan, deploy, and optimize. Let's talk about the assess phase first. Here, your enterprise will perform a thorough assessment and discovery of your existing environment in order to understand your existing applications and infrastructure. This involves creating an environment inventory, identifying application dependencies and requirements, measuring your current total cost of ownership so that you have a good baseline, and establishing performance benchmarks. The idea here is to get detailed insights in order to form the migration plan effectively. Next comes the plan phase, where you'll create the basic cloud infrastructure for your workloads and develop a comprehensive migration strategy. This phase will include planning identity management, organizing the project structures, networking, and sorting applications. You will prepare a prioritized migration strategy in order to ensure that the transition to the cloud is smooth and that all logistical and technical considerations are thought of beforehand. Next, we get to the deploy phase. Here, we will design, implement, and execute the actual deployment process to move the workloads to Google Cloud. This phase might also involve refining the cloud infra in order to address new needs and ensure that the applications run efficiently in the new cloud environment. This phase better include rigorous testing in order to validate that all components function as expected after the migration. Finally, once things are working again in the new environment, we can optimize. Here, we can start to fully leverage cloud native technologies and capabilities to enhance our enterprise operations. This will lead to improving performance, scalability, disaster recovery, and cost management. This optimization phase will also incorporate advanced features like machine learning and AI integrations in order to get the best out of your cloud-based apps. Let's talk through each of these stages in detail, starting with the assessment phase. Here, to begin with, we will take inventory and build a comprehensive list of all machines, other hardware assets, hardware specs, OS and OS licenses in our current environment. This inventory will help us to understand the scope of the assets that need to be migrated, and it will also identify any hardware or software that may not be compatible with the cloud environment. Accurate inventory management ensures that no critical components are overlooked during the migration. Next, we do something similar for our applications. We'll effectively compile a catalog of our applications. This will be a matrix based on their complexity and risk. The risk here involves the risk associated with moving to the cloud. Apps will now need to be categorized and prioritized in their migration order, starting with the less complex and lower risk applications and then moving on to the more challenging ones. By systematically cataloging applications, you can create a strategic migration plan that minimizes disruptions and ensures smoother transitions. This is also the right time to create awareness and to educate our organization. This is also the time to train or certify our software and network engineers on how the Google Cloud works and also on the specific products that it offers. This knowledge will come in handy in the steps that lie ahead. This will build internal expertise and confidence. This will be required in dealing with all of the challenges and steps that lie ahead. This is also the right time to calculate the current total cost of ownership or TCO. Comparing the cost of running your workloads on the cloud with your current costs using tools like the Google Cloud Calculator. Calculating the TCO will provide a clear financial picture and help in justifying the migration by highlighting potential cost savings. Understanding the total cost of ownership allows for informed decision making and budget planning, ensuring that the migration is financially viable. Next, we move to the planning phase where we create the comprehensive migration strategy. We will start by establishing the user and service account identities. So we'll need to provision and configure Google accounts, service accounts, Google groups, Google Workspace domains, and cloud identity domains to manage access and authentication. This step will ensure that all users and services have the appropriate credentials and permissions to interact with Google Cloud resources securely. Then we design the resource hierarchy. We need to organize our resources using Google's resource hierarchy, which includes organizations, folders, and projects. This structure will help in maintaining isolation and management across different teams and departments. Implementing environment oriented, function oriented, or granular access oriented architectures will improve your enterprise resource management and security. Then we will define groups and roles for the resource access. This will ensure that users have the appropriate permissions based on their responsibilities. This step will involve creating roles and assigning those roles to users and groups, leveraging Google's role based access control. While doing so, we want to keep in mind various principles of access and security, such as the principle of least privilege. One of the big changes which occurs when moving to the cloud is in terms of networks and network topology. In the planning phase, we will design our network topology and set up our connectivity. The building blocks for network building on the cloud are very different from those in on-prem environments. So we will make use of technologies such as network peering, VPNs, and cloud interconnects in order to ensure seamless communication and data transfer between the on-prem and the cloud environments. Proper network design is crucial for ensuring low latency, high availability, and secure connections throughout the migration process. This step will ensure that infra is ready to support the workloads and their performance requirements once they are migrated to the cloud. We are now ready for the deploy step. This is where we can design, implement, and execute the deployment process to move our workloads to the cloud. We can make use of configuration management tools in order to automate, repeat, and control environment configurations. These tools will help with operations such as running remote commands on VMs, and these will ensure that environments are consistently and repeatably set up and maintained according to the desired end state. Automation will reduce manual errors and ensure that environments are reliably configured. One of the big potential wins of moving to the cloud is that we can leverage managed versions of container orchestration technologies like Kubernetes. For instance, on the Google Cloud, GKE, that's the Google Kubernetes engine, can be used to manage the deployment of containers efficiently. This will abstract us from the underlying infrastructure, allow for scalable and automated application deployment and management. Using Kubernetes will streamline the deployment processes and enhance application reliability. This is also the phase where we carry out deployment automation. This can be done by implementing continuous integration and continuous delivery, that is CI/CD pipelines. CI/CD pipelines will allow rapid and reliable delivery of app updates by automating the build, test, and deployment stages. During the deployment phase, we also should be looking to leverage IAC, that is Infra as Code. Practices from the Infra as Code paradigm can help to define and manage infrastructure using declarative tools such as Google Deployment Manager or Terraform to build scripts for resource creation and updates. Using Infra as Code promotes version control, reproducibility, and easy sharing of entire workflows and environments, and really enhances collaboration and efficiency. Once we are done with the deploy phase, it's time to optimize. Now that you have real clarity on what the workflows are going to be like on the cloud, it's time once again to build and train your team to fully leverage the new cloud environment. Comprehensive training while on the cloud is always a good idea. It'll help your organization keep current with changes. The cloud is quite a fast moving target. In this phase, it's also a good idea to monitor and automate everything. Comprehensive monitoring tools such as Prometheus, Google Cloud Logging, and Google Cloud Monitoring can all be used in this phase. Additionally, you should be looking to automate processes using tools like Google Cloud Composer and Spinnaker to reduce manual errors and save time. Now is also the time to really start looking for big wins in terms of performance and scalability. Utilizing horizontal scaling in order to add or remove machines elastically, vertical scaling in order to adjust the capacity of individual machines. All of these techniques are available on the cloud. These can be used for compute, storage, and databases. This will help your enterprise handle varying levels of workload efficiently and cost effectively. And as things settle down in the new cloud environment and a new steady state emerges, this is also a good time to be looking to reduce costs and use more managed services. Examples might include the use of sustained use discounts or committed use discounts, flat rate pricing options like those offered on BigQuery, managed services like Cloud SQL, AutoML, or the GKE. Next, let's turn our attention to some cloud migration tools that are provided for our benefit by the Google Cloud. Let's break broadly. The categories are compute, databases, data warehouses, and data and images, that is, unstructured data. Let's talk about these in turn, starting with compute. Now, within compute, we have a broad choice. If we would like to rehost, then we can go for a lift and shift option where we have on-prem bare metal or on-prem VMs, which we then lift and shift onto the Google Cloud, or we can re-platform our VMs into containers on the Google Cloud. Let's talk about each of those in turn. As far as lift and shift goes, one option is making use of a service called Migrate to Virtual Machines. Just to be clear, this is the name of a Google service. So it's actually Google Migrate to Virtual Machines. Now, the story behind this name is so complicated that it's hard not to laugh while describing it. The current name of the service is Google Migrate to Virtual Machines. This represents version 5. This used to be Migrate for Compute Engine. So once that service reached version 5, it was renamed Migrate to Virtual Machines. That's the latest name. Previously, it was called Migrate for Compute Engine. To make things even more confusing, even before that, this service was known as Velostrata. In any case, despite its complicated history, this particular service, let me say it again, Migrate to Virtual Machines, is something that you can consider if your source is an on-prem VMware VM, or if it is a VM on any other cloud, and if your destination is the Google Compute Engine. The other option here is very simple in contrast. This is the VMware HCX. You can make use of the VMware HCX if your source is either an on-prem VMware VM or if it is a VMware VM running on any alternate cloud. But the destination here has got to be the Google Cloud VMware engine. And in case you're wondering what that is, Well, the Google Cloud VMware engine is simply the managed service for VMware on the Google Cloud. Now, you might also decide to re-platform your VMs containers when you move to the Google Cloud. Replatforming is a form of move and improve, and it involves migrating a workload to the cloud with some changes to the code or architecture. In the context of virtual machines which are running on premise, replatforming would take the form of migrating to containers. The tools here that are available are GKE, Autopilot, GKE Enterprise, and Cloud Run. GKE, of course, is the Google Kubernetes engine. That's the managed Kubernetes service on the Google Cloud. Autopilot is a mode within GKE that automates cluster management, scaling, and security. GKE Enterprise has various additional features on top of GKE Standard, and it caters to enterprise needs like multi-cluster management and more robust security. And finally, Cloud Run is a serverless platform. This will let you deploy containerized apps without managing the server infra. The Google Cloud has a specific service which is called Migrate to Containers. It's a rather ungainly title but very descriptive. Migrate to Containers is a service which will help you to assess, analyze, and migrate workloads from VMs into containerized apps running on GKE or Anthos clusters. It will automate much of the conversion process. Next, let's move on from compute to databases. Here, there are two choices, both of which involve re-platforming databases to the Google Cloud. The first of these is DataStream. The second is the Database Migration Service. DataStream is what is known as a CDC and replication service. CDC stands for Change Data Capture. DataStream is serverless. It will synchronize data with minimal latency. It will support Postgres, and that includes AlloyDB for Postgres and AlloyDB Omni. It will also support MySQL, SQL Server, and Oracle databases. It will replicate data into cloud storage and BigQuery. DataStream enables seamless data replication from operational databases into BigQuery, and it can write change event streams into Google Cloud Storage. Additionally, DataStream can be integrated with Dataflow templates in order to build custom workflows for loading data into Cloud SQL, Spanner, and other destinations. It ensures reliable and real-time data synchronization across different cloud services. The other choice here is the database migration service. This is also serverless, and it is also designed to help migrate databases. It works with Postgres, MySQL, SQL Server, and Oracle. It will support migrating Postgres workloads into Cloud SQL and AlloyDB, MySQL and SQL Server workloads into Cloud SQL. If it's Oracle that you have on-prem or off the Google Cloud, then you'll need to migrate into Cloud SQL for Postgres or AlloyDB for Postgres. The service will streamline networking workflows and manage the initial snapshot and ongoing replication. It will also send detailed status updates on the migration. If you decide to use the database migration service with Oracle, remember that this is a re-platforming solution. If you're looking to do a lift and shift and you use Oracle off the Google Cloud, then you have two choices, a bare metal solution or using a GCE VM. Let's move on from databases to data warehouses. And the service that we are looking for here is the BigQuery Data Transfer Service. This will automate the scheduled and managed movement of data from SaaS applications to BigQuery. It supports refactoring data from sources like Teradata or Amazon Redshift. And what's more, it will do so on a continuous basis. This will allow your enterprise to maintain up-to-date datasets within BigQuery for your analytics and reporting. Finally, let's talk about tools for moving data and images. This could be unstructured data. And here, when we talk about images, we are actually talking about VM images or software images, not the multimedia variety of images, although the first two of the three services that we are going to talk about will handle those as well. The first is the storage transfer service. This will help with the transfer of data to Google Cloud Storage from various sources, including other cloud providers, online resources, or local data stores like S3, Blob, Data Lake, as well as on-prem file systems. The transfer service is specifically designed to deal with large-scale data transfers efficiently and securely. It also offers features like scheduling, monitoring, and error handling. The next item here we're talking about is the transfer appliance. This is a physical device that is provided by the Google Cloud to migrate large volumes of data, typically exceeding 20 terabytes and up to 1 petabyte. This hardware appliance will be shipped to your location where you load your data onto it before sending it back to Google for secure upload to the cloud. The transfer appliance is ideal for scenarios where network bandwidth limitations make online data transfer impractical. It's fast, secure, and efficient, and it minimizes disruption to business operations. Your large datasets will be safely and reliably transferred to Google Cloud. Finally, let's talk about image import. This is a service that allows us to import virtual disks from our on prem environment onto Google Cloud. This will include all of the necessary software and configurations. So, for instance, these could be golden disks or golden images. This tool will support most virtual disk formats such as VMDK and VHD, and it will allow you to create VM instances using those imported images. By using the image import service, you can ensure that your VMs on Google Cloud have the same configurations and software environments as your on prem systems. All this talk of migration might have made it seem so daunting to move to the cloud that you might now be questioning the benefits of moving at all. That's why it's probably a good idea for us to once again talk about the benefits of moving workflows to the cloud. We shall see what practical benefits we actually get in return for all of that trouble. The first is all of the savings that accrue in terms of total cost of ownership or TCO. Running compute workloads on the cloud will significantly reduce the total cost of ownership because it eliminates the need for large upfront investments in the form of capital expenditure in hardware and infrastructure. TCO needs to include the cost of the initial purchase, maintenance, and operation, along with any other associated costs. Cloud providers offer a pay as you go model, and that means that organizations will largely only pay for the resources that they actually use, provided their configuration of the cloud resources is correct. In addition, cloud providers offer discounts for long term commitments, and that further reduces the TCO for businesses that are planning to use cloud services over an extended period of time. The second big benefit is in terms of scalability. Cloud computing will provide unparalleled scalability so that your enterprise can quickly and easily adjust your computing resources based on demand. It's worth remembering that that's where the elastic in the elastic cloud compute came about, and that, of course, was one of the original cloud offerings. Your enterprise can scale up your capability so that your apps can meet varying workloads without performance degradation. You can scale up during peak times and scale down during periods of low demand and thereby optimize your resource allocation. More and more cloud offerings these days offer advanced failover mechanisms, and that's one of the ways in which cloud computing increases the reliability of your enterprise. Cloud providers make it their business to ensure high availability through redundant systems and automatic failover. They also offer SLAs, that is, service level agreements, which guarantee certain levels of uptime and performance. This reliability is crucial for businesses that need continuous availability and cannot afford interruptions. Security considerations are becoming more and more important, and cloud providers invest heavily in security measures to protect data and apps. They offer advanced security features such as encryption, identity and access management, and regular security audits. These also play a big role in helping with the compliance of your enterprise if you happen to be in a regulated sector. For instance, being compliant with regulations like GDPR or HIPAA or PCI DSS all become significantly easier if you correctly leverage all of Google's resources on these regulations. Moving to the cloud offers a great deal of flexibility. You can experiment with a wide variety of development frameworks and programming languages, and that in turn will lead to a wide range of applications. Different teams within your enterprise can choose the best tools and technologies for their specific needs. The cloud platforms will also support deployment models such as public, private, and hybrid clouds, and this will give enterprises the flexibility to choose the most suitable environment for their workloads. Finally, moving to the cloud provides a level of abstraction from the underlying infrastructure. It allows your enterprise to focus on developing and deploying apps without having to worry about hardware management. This abstraction layer simplifies deployment, and it also reduces the complexity of managing all of the physical servers and storage devices and networking. Each of these benefits has its own different aspects. Let's quickly go through them, starting with the lower total cost of ownership. Moving to the cloud leads to reduced capex or capital expenditure. No need for the big upfront investments in physical hardware and data centers. It increases operational efficiency as well as focus because now organizations can streamline their IT ops and reduce the size of their large in house IT teams and their associated costs. Another effect here is that costs become more predictable. Cloud providers have a pay as you go pricing model, and they also provide predictable and transparent billing and other tools for you to manage your cloud costs. Next, under the category of scalability, we have various benefits which begin with the elasticity of resource allocation. That in turn leads to more cost efficiency because you only pay for resources that you use and you scale those resources based on the condition of the business. Another benefit here is that of global reach. Cloud providers have a global network of data centers, and this allows businesses to deploy their apps closer to their users. This reduces latency and improves performance and can provide a significant improvement in user experience. Moving on to the category of reliability, cloud providers have more and more redundancy, more and more cloud services offer redundant systems and data replication. Also, as they build more and more data centers, it also becomes easier to ensure high availability. Another aspect that we don't usually think about is disaster recovery. The hyperscalers have built in disaster recovery solutions. These will enable businesses to quickly recover from unexpected events and ensure business continuity. The cloud platforms also provide a very high level of monitoring and maintenance support. They continuously monitor all of their infra and perform regular maintenance to prevent issues. The next category of benefits come under security. This is increasingly becoming a driver of cloud adoption. Data encryption is a given on any of the major cloud platforms. The cloud services have data encryption both in transit and at rest, and often in use as well. In terms of the famous CIA triad of information security, that's confidentiality, integrity, and availability, encryption safeguards data integrity as well as confidentiality. Cloud platforms have robust solutions for access control, usually in the form of role based access control. Google's offering here is called IAM, that's Identity and Access Management. It allows businesses to control who has access to individual resources at a fine level of granularity in terms of permissions. This minimizes the risk of unauthorized access and data breaches. The cloud providers adhere to strict compliance standards and regulations such as GDPR, HIPAA, and standards like ISO 27001. This compliance on the part of the hyperscalers ensures that their customers are able to meet regulatory requirements relatively easily. Cloud deployment provides flexibility along a number of different dimensions. For instance, multi cloud support. Cloud platforms allow businesses to use multiple cloud providers because they know that cloud lock in is something that customers will not stand for. As a result, your enterprise can optimize your workload across different environments. This multi cloud strategy increases flexibility and reduces your dependence on a single provider. Even if you are within the context of a single cloud platform, cloud services offer customizable solutions that can be tailored to meet specific business requirements of different teams and organizations. You should expect less turf battles and a lot less pressure to go with the enterprise wide solution after cloud has been adopted. Flexibility also comes in the form of rapid deployment. This is deployment of code as well as infrastructure. For instance, we discussed infra as code, where it's possible to spin up very complex architectures of cloud resources using a specification like a YAML file. So, across all kinds of resources, whether they are code or infra, the hyperscalers support rapid development, and this accelerates time to market and it allows your organization to innovate faster. The feedback loop is much tighter. Abstraction is yet another very real benefit of the cloud. Managed services will help with all of the operational aspects of IT infra. The hyperscalers are very proactive about coming up with managed services for any service or product that is very popular in an on prem setting. For instance, we've already discussed how Cloud SQL is a managed service for MySQL, Postgres, or SQL Server. And for that matter, how the Google Cloud VMware engine is a great managed service for VMware on the Google Cloud. Managed services greatly reduce the need for specialized IT skills which might only be relevant to a particular organization every now and then. And this in turn allows businesses to allocate resources more effectively. This abstraction also leads to greater developer productivity. With all the time that's saved from all of those installs and infra management, developers can focus on creating more innovative applications. Let's now talk a little more in detail about running compute on virtual machines on the Google Cloud. This is a topic that we've already covered. However, the Google Cloud Digital Leader materials circle back to this topic in order to emphasize some new aspects, so we'll do the same. Let's start with a quick refresher of traditional compute on bare metal. This term refers to physical servers that run apps directly on the OS without a virtualization layer. This setup allows applications to fully make use of hardware resources and leads to improved performance and lower latency as compared to virtualized environments. In a bare metal configuration, the OS is installed directly on the server's hardware. It provides direct access to the CPU, memory, storage, and network resources. This is particularly beneficial for high performance computing, database workloads, and other apps that really need every last bit of performance from the system. One downside of this is that organizations which go with this option end up with tight binding between hardware resources and their apps. This tight binding ensures that the applications can leverage the full capabilities of the hardware. On the other hand, this also leads to inefficiencies because the hardware resources will remain underutilized when those apps do not require full capacity. All of the downsides of bare metal gave rise to virtualization and more modern workloads which run on virtual machines. VMs or virtual machines are software based emulations of physical computers. Effectively, they run an operating system and applications just like a physical server. However, unlike bare metal, VMs have a layer in between. This is a virtualization layer called a hypervisor, which abstracts the underlying hardware, and this allows multiple VMs to run on a single physical server. This setup allows greater flexibility, scalability, and more resource utilization because the resources can be dynamically allocated and adjusted. However, in return, VMs have slightly lower performance than bare metal because of the overhead introduced by the hypervisor. The hypervisor is also often referred to as a VMM or a virtual machine monitor. It's the hypervisor which allows the creation and management of multiple VMs on a single physical hardware host. The hypervisor abstracts away the underlying physical hardware, and so all of those VMs can run concurrently on the same host and share resources such as CPU, memory, and storage. The hypervisor ensures that each VM operates independently and securely. This is very important. The hypervisor needs to provide isolation as well as resource allocation. There are two types of hypervisors: type 1, that's bare metal, which runs directly on the physical hardware, and type 2, or hosted, which runs on top of a host operating system. This particular diagram shows a type 2 hypervisor in action. Virtualization has many benefits, starting with resource optimization. Virtualization technologies relieve the pressure of the tight binding between specific hardware and apps by allowing multiple systems to run on the same hardware. This enables organizations to maximize utilization. By running multiple VMs on a single physical server, enterprises can significantly lower their hardware costs. Virtualization also leads to efficient and manageable multi-application hosting. VMs allow organizations to run multiple apps simultaneously on a single server. This is both efficient and manageable. This capability allows businesses to host diverse workloads on the same hardware, optimizing performance and resource use. Each VM operates as an independent environment, and that ensures that these apps still remain isolated and secure, though they run on the same underlying physical hardware. This separation also simplifies management because admins can easily monitor and control resource allocation for each virtual machine. Another advantage is scalability and flexibility. VMs can be quickly provisioned, configured, and scaled up or down based on demand. Of course, here, quick is relative. We are talking about the speed of provisioning a VM relative to the speed of provisioning a bare metal instance. If you were to compare VMs to containers, well, then containers are going to make VMs seem rather slow. But relative to what was available when virtualization first came on the scene, VMs are very fast. Google Cloud's Compute Engine, for instance, will allow users to create and run VMs without upfront investments, potentially leveraging thousands of virtual CPUs or vCPUs as they are known, and these might be designed for fast and consistent performance. Another great benefit of virtualization is how customizable the environment becomes. Each VM has the power and functionality of a full fledged OS. This allows it to be configured much like a physical server. Users can specify the amount of CPU and memory that they need, the type and amount of storage needed, as well as the OS. This customization ensures that VMs can meet very specific needs of different applications, providing tailored niche environments to optimize performance and resource use. Let's do a quick head-to-head comparison of bare metal and virtual machines. Bare metal typically gives higher performance because of the direct access to the hardware resources. VMs typically have slightly lower performance because of the overhead of the hypervisor. Bare metal instances are dedicated resources for each application. There's no sharing mechanism. VMs, on the other hand, are shared resources, so there are multiple VMs running on a single physical server. Scaling is quite hard with bare metal compute because we are limited by the physical hardware capabilities. Scaling will require the addition of more servers. VMs are highly scalable because they are easy to create, clone, and manage, and so we can have dynamic resource allocation. In terms of flexibility, bare metal is less flexible because the hardware and configurations are fixed after deployment. VMs are more flexible. We can easily change around resource allocations as well as configuration parameters. Management overhead is far higher with bare metal because of all of the physical hardware maintenance and the need for OS maintenance and patching as well. VMs have far lower management overhead. Centralized VM management tools and automated provisioning make all of this much easier. Bare metal is a lot slower to deploy because this involves setting up physical servers. VMs are a lot faster in terms of deployment. When compared to bare metal, VMs can be spun up very quickly. Now, again, that's relative. For instance, the last few Cloud SQL instances that I have spun up have taken up between 10 and 30 minutes to provision. That might seem like a lot when compared to some other kinds of solutions, but it's probably lightning fast if you change your perspective and think about setting up a MySQL server from scratch on bare metal. With all of that context about virtual machines and bare metal fresh in our minds, let's return to the Google Compute Engine. This is the Google service to create and provision VM instances, and it's worth mentioning here that the terms Compute Engine instance, virtual machine instance, VM instance, and VM are all synonymous. An individual VM is a zonal resource and is provisioned in a single zone. Roughly speaking, you can think of a zone as a data center. Let's now talk about some aspects of the billing of VM instances. Broadly speaking, we are charged for compute resources, persistent storage, and network usage. On compute, the Google Cloud will charge us for the vCPUs, that is virtual CPUs, as well as the memory allocated to our VM instances. The cost depends on the type and configuration of the VM instance, such as, for instance, the number of vCPUs and the amount of memory. VMs usually make use of persistent disks for storage, and the persistent disk storage of a VM is one of the rare cases where you pay for what you allocate and not for what you use. There are many dimensions for the billing of persistent storage. These include the type, such as standard, SSD, or balanced, the capacity, and the duration of the storage use. Google Cloud offers different types of persistent disks to cater to different performance needs and budget considerations. We also incur billing for network usage. Charges will apply for data egress, that is, data transferred out of the Google Cloud over the internet or to other Google Cloud regions, as well as for inter-region data transfer. Ingress, that is, incoming data transfer, is typically free. Finally, VM instances are subject to per second billing with a 1 minute minimum, and there might be additional costs for some services such as premium OS licenses, external IP addresses, or network features like Cloud NAT or VPN. NAT is short for Network Address Translation, and VPN, of course, is a virtual private network. In this context, it's also very important for us to talk about discounts, specifically sustained and committed use discounts. Let's start with sustained use discounts, or SUDs as these are known. The idea here is that Google Cloud will automatically reduce the cost of VM instances that run for a significant portion of the billing month. The discounts are progressive, meaning that the longer an instance runs within the month, the greater the discount received. The discount structure starts after running the instance for more than 25% of the month. Whenever you use an applicable resource for more than a fourth of a billing month, Compute Engine will automatically give you the sustained use discount for every incremental hour that you continue to use that resource. The discount increases with further usage, and you can get up to a 30% net discount of the resource cost for the VM instance for the entire month. This pricing model rewards continuous usage without requiring any upfront commitment or complex calculations, and this makes it pretty suitable for workloads with consistent and predictable usage patterns. The discounts are automatically applied so that customers can benefit from lower prices without needing to take any further actions. You don't need to apply for the discount. Compute Engine offers a maximum monthly SUD percentage of either 20 or 30%, depending on the resource or the machine type. Sustained use discounts automatically apply to VMs created both by GCE and GKE, that is Google Kubernetes Engine. These may only apply to certain machine types, not all machine types will offer them. A closely related concept is that of the committed use discount or CUD. This is something that Google Cloud offers in return for purchasing committed use contracts. These are known as commitments. When you purchase a commitment, you commit either to a minimum amount of resource usage or to a minimum spend amount for a specified term of 1 to 3 years. For Compute Engine, you receive deeply discounted prices for your VM instance in return for these 1 or 3 year commitments. It turns out that there are actually two flavors of CUD, so let's talk about those really quickly. The committed use discounts might be either resource based or flexible. Resource based CUDs are ideal for predictable and steady resource usage. You can receive these CUDs when you purchase a resource-based commitment and commit to a minimum level of compute engine resources in a particular region. These commitments are available for vCPUs, memory, GPUs, local SSDs, sole tenant nodes, and software licenses. Alternatively, you could go with flexible CUDs, which are effectively spend-based. So to avail of flexible commitment use discounts, you need to purchase a spend-based or flexible commitment for Compute Engine and commit to a minimum amount of hourly spend. In cases where your spend needs are more unpredictable, these are preferable to the resource-based CUDs. They eliminate the need to restrict your commitments to a single project, region, or machine series. You can purchase flexible commitments for your cloud billing account. In return, you will receive CUDs for your vCPU and memory usage in any of the projects within that cloud billing account across any region and belonging to any general purpose or compute optimized machine type. So again, unlike resource-based CUDs, these are not specific to any machine type or region. We've now spoken a fair bit about individual VM instances. Let's talk about running data processing workloads on a cluster of VM instances. This particular setting inherently provides fault tolerance, and the system can continue to operate even if some of the machines fail. How is this fault tolerance achieved? Well, through a combination of data replication, distributed computing frameworks, and redundant configurations. In a cluster, data is usually replicated across multiple nodes, so if one node fails, that data can still be accessed from other nodes. Distributed computing frameworks such as Apache Hadoop and Apache Spark divide tasks into smaller subtasks that are distributed across the cluster. If a machine fails, these frameworks will pick up on that and automatically reassign the task to other machines, and thereby ensure continuous processing without data loss or significant downtime. Now, because of the architecture of a cluster, it would be really handy if you could provision and pay for instances only when you need them. And it is exactly for this use case that the GCP offers something known as the on-demand VM. As its name would suggest, an on-demand VM is a computing instance that you provision and pay for only when you use. On-demand VMs have scalability, cost-effectiveness, and simplicity of management. On-demand VMs provide guaranteed availability and consistent performance without the risk of being terminated by the platform. These VMs will be billed at a fixed rate based on the resources used, and they are suitable for running critical workloads that require continuous operation and cannot tolerate interruptions. On-demand VMs ensure reliability and stability. This makes them ideal for applications with steady, predictable usage patterns and those that need to remain operational 24/7. On-demand VMs are not always necessary for a cluster because clusters are designed to handle fault tolerance and scalability through distributed computing. However, it's often a good idea to have clusters which have a mix of on demand and regular VMs in order to deal with spiky workloads. That way, unpredictable traffic surges can be handled by quickly scaling up the VMs to meet peak demand and then scaling them back down. However, please be warned that on demand VMs can end up being more expensive if you're going to have sustained use. In those situations, you probably want to make use of committed use discounts that are offered by the GCP. For cluster workloads where we are looking for cheaper VM options, the GCP has a couple: preemptible VMs and spot VMs. Preemptible VMs will run for a maximum of 24 hours and will be terminated within this period. These are cost effective short term instances. These are available at a much lower price than regular VMs on the Google Cloud. The downside is that we don't know when the VM will be terminated. The cloud might do this at any time if the resources are needed elsewhere. This makes them totally suitable for fault tolerant and flexible workloads. They offer 60 to 90% savings relative to standard VMs. That's a significant cost reduction for batch processing, data analysis, and other transient tasks. Remember that distributed computing technologies such as Apache Hadoop or Spark are in any case equipped to deal with nodes going down. And so, even if one of the VMs on the cluster is preempted, that's not a huge loss as far as the workload is concerned. So preemptible VMs are a great and very cost-effective choice for large-scale parallelizable workloads that can tolerate interruptions. A variant of preemptible VMs are spot VMs. These can be thought of as the newest version. There's no maximum runtime limit and they have the same price as preemptible VMs. That makes spot VMs better than preemptible VMs because you pay the same and there's no runtime limit. While designing your deployment strategy for VMs on the Google Cloud, you definitely should pay attention to the concepts we just discussed here, which included committed use and sustained use discounts, on demand VMs, preemptible VMs, and spot VMs. When going from bare metal to VM instances, we added one layer of abstraction. What if we added another layer of abstraction? Well, that's basically what running compute on containers is all about. This takes things to the next level in terms of virtualization and offers significant advantages in terms of efficiency, scalability, and resource optimization. Containers are lightweight and they share the host OS kernel. This allows for faster startup times and better utilization of system resources than VMs, which require separate operating systems. Containers provide a lightweight, portable, and consistent environment for apps that makes them a great platform agnostic compute solution. Containers encapsulate an app as well as all of its dependencies into one single lightweight portable unit that can run consistently across various environments, whether it be the developer's laptop or a production server on the cloud. As the name would suggest, a container is self contained. It has everything needed to run that piece of software. That includes the code, runtime, system tools, libraries, and settings. Containers are so powerful and popular that architectures end up using very large numbers of them, and that in turn gives rise to the need for a tool like Kubernetes, which is a container orchestration tool. Here on screen is a schematic diagram of running workloads on containers. As we can see at the very bottom, we have the hardware. That includes the physical servers and the infrastructure. Just above the hardware, we have the host OS. This provides the foundational system resources and services. What is important to note here is that the individual containers do not contain an operating system. If we compare this image with a similar image for virtual machine instances, you'll notice that there is no guest OS within the container. What's also new here is the container engine, something like Docker. So again, at the very bottom, we have the hardware. Above that sits the host OS. Above the host OS sits the container engine, that's Docker. This is responsible for managing the containers, and that includes their creation, execution, and destruction. The container engine abstracts away the complexities of the underlying OS, and it provides a unified interface to manage the containers. As far as the code within each container is concerned, all that it needs to know is how to communicate with Docker. The container engine, something like Docker, is a crucial layer in this container architecture. It has some similarities to the role of the hypervisor in the VM architecture. It provides isolation of each container from all of the others. By abstracting away the underlying host OS, the container engine provides a consistent and unified interface that can be used to manage containers. It also handles essential tasks like resource allocation, networking, storage management, and so on. So again, each of the apps within the containers will know of storage abstractions as represented by Docker. They are not going to deal with the actual underlying file system as represented by the host OS. So each container does not contain a guest OS. What it does contain is a set of all of the libraries and dependencies needed for one particular app to run. By including all necessary dependencies within that container, apps can avoid conflicts and compatibility issues that might arise from differing environments. Just like we could have and probably will have multiple VM instances running on top of the same bare metal, in a similar fashion, we will tend to have multiple containers running on the same host system. Each container will operate independently. This isolation is achieved through virtualization at the OS level, where the containers share the same OS kernel but have different user spaces. As a result, the containers will not interfere with each other, and this allows multiple applications to run on the same host without affecting each other's performance or stability. This isolation also increases security because a breach or a failure in one container will not impact the others. In addition, it greatly simplifies deployment and management of apps because each container can be independently managed, it can be consistently taken up or brought down, and also deployed consistently across environments from development to production. Containers have many advantages over VM instances, starting with portability. Containers encapsulate the application along with all of its dependencies, libraries, and config files, and this in turn means that that app can run across different environments. Just as VMs were more efficient than bare metal, in similar fashion, containers are more efficient than VMs. They share the host OS kernel that makes them more lightweight than VMs and means that multiple containers can run on the same hardware with minimal overhead. The utilization of system resources improves, as does the startup time. Also, more granular scaling is now possible. This allows organizations to run more apps on the same infrastructure and respond more quickly to changes in demand. Containers provide strong isolation between apps and they ensure that each container operates independently with its own file system, processes, and network stack. This also prevents conflicts between apps and improves security because vulnerabilities or failures in one container will not affect others. Because of their lightweight nature, containers can be easily scaled up or down to match changing workload demands. This is particularly advantageous in cloud environments because containers can be orchestrated using tools like Kubernetes in order to automate the deployment, scaling, and management of containerized apps. Containers are particularly suitable to a hybrid multi cloud environment, and this is a use case that has exploded in popularity in recent years. As cloud adoption increases, more and more firms start to get onto the cloud, which means that they have a need for the hybrid support, and more enterprises are worried about vendor lock in. They are worried about being tied to one of the hyperscalers, and so they go with a multi cloud environment. And for this particular use case, container clusters are extremely attractive. A quick word about Docker and how it plays into Kubernetes. Docker is an open source platform which allows developers to automate the deployment, scaling, and management of apps within lightweight and portable containers. Additionally, Docker integrates with different orchestration tools, the most popular and important one of which is Kubernetes. So, Docker is a platform that provides a containerization solution. This allows it to work with tools like Kubernetes, which are orchestration solutions. Docker containers have a number of benefits that we've just discussed. They are lightweight and efficient. Docker provides the isolation and the security of each one of those containers. Docker plays very well with DevOps and CI CD integration use cases, and this solution offers portability, scalability, and cross platform OS compatibility. Let's do a quick comparison of virtual machines and containers. Each virtual machine includes a full OS, that's the guest OS, that's in addition to all of the applications and their dependencies. VM instances run on a hypervisor, which manages multiple VMs on a single physical host. Containers do not have the guest OS included within them and they run as isolated processes. This makes containers very lightweight because, as you can imagine, the guest OS is often significantly larger than the app payload. That in turn means that a VM instance consumes far greater system resources. The full OS will consume CPU, memory, and storage. Containers do not have the guest OS, and that in turn leads to lower resource utilization. VMs were, of course, far faster to start up than bare metal instances, but they still take a lot longer than containers because they need to boot the full OS. This could take from several seconds to a few minutes. Containers can start almost instantly, as measured in seconds or milliseconds, because they do not need the full OS boot. Both VMs and containers offer great isolation properties, but these are slightly different from each other. VMs have strong isolation because each VM operates independently with its own operating system. This isolation is at the hardware level, which makes it very robust. Containers, on the other hand, have process level isolation using namespaces and control groups. This is effective, but it is definitely less robust than that which is provided by VMs because the containers share the same OS kernel. Moving on to portability, though, here containers come out on top. VMs are portable across different physical machines and environments, but the process of porting a VM can be quite cumbersome because of the size and complexity of the VM images. Think about the complexity of a lift and shift. Containers, on the other hand, are highly portable. They run much more consistently across different environments, as well as different platforms, such as on premise or different cloud environments. Relative to bare metal, VMs are, of course, low maintenance, but when we contrast them to containers, well, they don't quite measure up. Managing VMs involves handling the underlying hypervisor, OS updates, as well as VM specific configurations. Containers make management and maintenance a lot simpler because of the container orchestration platforms like the Google Kubernetes engine. These will automate deployment, scaling, and management of containerized applications and reduce the overhead and complexity a great deal. Finally, it's worth talking about images and containers. The image can be thought of as a blueprint for the creation of multiple containers. So the image includes the application code, runtime, libraries, and the dependencies in order to run the application. Once the image is created, it will be stored in a repository, and that repository can then be used to spin up multiple containers, each of which has the exact same setup. The repository that is supported on the Google Cloud is called Google Cloud Artifact Registry. This is a fully managed service that allows you to store, manage, and secure your container images, language packages, and other artifacts. You can use the artifact registry for Docker images as well as artifacts with Maven, NPM, and other formats. Containers clearly have a higher level of abstraction than VM instances. If you look at the continuum of compute choices, where bare metal is at the lowest end and is the closest to the hardware, then container clusters come somewhere in the middle. They offer more abstraction than bare metal or VM instances, but less so than platform as a service or serverless offerings. Mapping this to the Google Cloud, we see that there are two offerings if we'd like to run containers. One of these is GKE and the other is Google Cloud Run. As this continuum shows us, the Google Kubernetes engine is rather more low level than Google Cloud Run, but in any case, we will talk about each of these in more detail. One of the primary reasons for the popularity of container based solutions is their role in enabling hybrid multi cloud solutions. And another unrelated but equally important reason for their popularity is the role that they play in enabling microservices architectures. Let's go ahead and understand what these are and how they relate to more traditional models of app development. Traditionally, apps were usually built as monolithic structures where all components, such as the user interface, business logic, the database access layer, were all integrated into one single unified code base. This led to a tight coupling between the different components, and this tight coupling meant that any change in one part of the app required rebuilding and redeploying the entire app. It can lead to longer development cycles and difficulties in scaling specific components independently. The traditional model leads to the creation of a single deployment unit. The entire app is packaged and deployed together as one unit. While this might simplify the deployment process initially, over the long run, it makes the system less flexible. Any update, regardless of how minor, requires the entire app to be redeployed. This increases downtime as well as deployment risk. Another downside of this traditional way of doing things is the tight coupling and all of the challenges in dependency management. This tight coupling results in the creation of a domino effect. A change in one component requires changes in others. All of this makes testing, maintenance, and scaling the app much more challenging. A failure in any one part can affect the entire system. And that leads to one of the great difficulties that the cloud is trying to solve: challenges in scaling. Let's say that only one part of a traditional monolithic app is experiencing increased load. Because of the tight coupling, we have no choice but to scale the entire app, which means that additional resources will need to be deployed to all of the different parts of that app. This will lead to inefficient use of resources and higher costs. The scaling out of a monolithic application often requires more hardware than required in order to handle the load and is less efficient than scaling the specific components independently. And finally, monolithic app development leads to bottlenecks in development in addition to deployment. Multiple teams will need to work on the same code base at the same time. This causes integration issues to get more serious, it lengthens out the release cycles, and leads to difficulties in coordination between the different dev and ops teams. It limits the ability of the organization to adopt agile practices and CI CD pipelines. It is in response to all of these challenges and issues that the microservices architecture originated and gained popularity. This is an approach to software development where a large app is composed of small independent services that communicate with each other through well defined APIs. Each service is designed to handle a specific business function and can be deployed, developed, and scaled independently. Each of the different services is small and lightweight and independent from all of the other services. This architecture promotes flexibility because these services can be written in different programming languages and use different data storage technologies. The microservices architecture also enhances fault isolation because failure in one service is less likely to propagate through the entire app. Microservices enable faster development as well as deployment cycles and allow enterprises to adopt more agile and scalable approaches to building their apps. Now, the communication between these different services happens through well defined APIs, so it's worth our while understanding precisely what an API is. We can think of this as a set of rules and protocols that allows different software apps to communicate with each other. The APIs are clearly defined and specify the methods and the data formats that can be used in order to request and exchange information. APIs provide a standard way for components to interact, and in this way, they enable integration and interoperability between different systems, platforms, and services. These are essential building blocks of modern software architectures such as microservices, where the independent services need to interact seamlessly. APIs also make it a lot easier for third parties to build apps and integrate these with existing code bases, and this increases the functionality and reach of software products. We will come back to APIs in more detail. For now, let's go a little deeper into the microservices architecture. On screen now, we have a schematic block diagram where we see different components of such an architecture. Way over on the left, we have the client apps, and then on the right, we have various microservices which connect to corresponding data sources or databases. It's important to note that there is an API gateway at the center which connects or intermediates between the client apps and the microservices. Let's break this architecture down. Way over on the left, we have client apps. This diagram shows two types of client apps, web and mobile. These are both user facing, through which customers interact with the services of our organization. These apps send requests to the backend services through the API gateway, which acts as a single entry point for all client requests. That API gateway plays quite a starring role in this architecture, and on the Google Cloud, Apigee is the API gateway service. This API gateway will serve as the intermediary between client apps and the microservices. It routes requests from the clients to the appropriate microservice. The gateway handles request routing, composition, and protocol translation, and it simplifies the interaction between the client side apps and the microservices by exposing a unified API. API gateways typically also have functionality related to authentication and authorization. Behind that API gateway, we have four microservices shown here. These are the catalog, shopping cart, discount, and ordering. Each microservice corresponds to a specific business function and operates independently. The microservices are designed to handle distinct functionalities, as their names would suggest. The catalog will manage product listings and details. The shopping cart will handle the user's shopping cart operations. Discounts will have discount calculations, and ordering manages the orders and order status. Clearly, these services will require state, and that state is maintained in the form of databases way over on the right. Notice how each microservice has its own dedicated database. This ensures that the data across these microservices is decoupled and managed independently. This increases the scalability and allows for the optimization of the database solution each service needs. For instance, we might have a document database for the catalog, but we might want a traditional RDBMS for the transaction processing in the ordering. Microservices architectures have many benefits, and that's why they've become so popular. The first of these is the ability to independently develop and deploy all of the different services. The microservices architecture will break down an application into smaller and more manageable components, each of which is responsible for a specific business function. There can now be different dev teams working on the different services simultaneously without getting in each other's way. Each microservice can be developed, tested, and deployed independently. This leads to faster release cycles as well as continuous integration and delivery. This helps both with scalability and resource optimization. Each microservice can be scaled independently based on its specific load and performance requirements. The granularity of the scalability ensures that the resources are allocated efficiently and optimizes costs. For instance, a service handling user logins can be scaled independently from a different service managing product catalogs. A third benefit is fault isolation and resilience. The microservices are designed to operate independently, so a failure in one service does not necessarily impact the others. This isolation improves the overall resilience of the application. Issues can be contained and addressed within the individual services without causing system wide outages. This enhances reliability and uptime. Another benefit that accrues to us is flexibility in the tech stack. Different microservices can be built using different technologies and programming languages, each best suited for its specific needs. This allows teams to choose the most appropriate tools in order to optimize performance, and it enables the adoption of the latest advances. All of this in turn leads to easier maintenance and evolution. Each service is smaller and more manageable, and so the code base is that much easier to work with in the long run. The code base is also modular, and that makes it easier to understand and document, and also to extend individual services. Once again, this has the effect of accelerating innovation and allows enterprises to react more quickly to changing business requirements. Containers are perfectly suited to a microservices architecture. They enable this architecture to a very large extent via different properties that containers have and which fit nicely with the microservices architecture. The first of these is isolation and independence. Containers package apps with their own dependencies so that each container can run in an isolated environment. This ensures that each microservice running in a container can operate independently without interference from the other containers. Containers offer rapid deployment and scalability because they are lightweight and can be easily started or stopped. And they can also be managed in bulk via orchestration tools like Kubernetes. This capability makes them crucial for the microservices architecture, where the individual services might need to scale up or down dynamically based on demand. The orchestration tools like Kubernetes facilitate the automated scaling, load balancing, and high availability that all of this demands. Microservices architectures prize portability and consistency, for instance, in the well defined APIs that are used for communication between different components, and containers offer just this portability and consistency. They encapsulate an app as well as its dependencies, and that makes that application very portable across different environments such as dev, test, and prod, as well as across platforms, whether they are on prem or different cloud environments. So, in summary, a microservices architecture represents a great advance over traditional models of building software. Containers are a great and efficient way of building microservices architectures, and that's one of the reasons why container based solutions have become so popular in recent years. By this point, we understand why containers are so popular. It's now time for us to understand why Kubernetes is so popular. We'll now be talking about managing containers using Kubernetes. Standalone containers, despite all their benefits, also have a number of limitations, and these limitations are fixed when we use a Kubernetes like orchestration service. So let's understand those limitations of standalone containers. The first is the lack of load balancing. Standalone containers lack built in load balancing capabilities, which means that they cannot distribute incoming traffic across multiple instances of the same container. Without load balancing, a single container might end up being overwhelmed by traffic, leading to performance bottlenecks and potential downtime. Managing load distribution is quite a complex and error prone task, and it's difficult to ensure high availability and optimal resource allocation using only standalone containers. As we've discussed, standalone containers have process level isolation. This is good but not quite as robust as the hardware level isolation that VM instances provide. This is another weakness that Kubernetes helps to address. The standalone containers do not isolate resources as effectively as VMs because they share the host's operating system kernel. This can lead to potential security and stability issues. If one container is compromised, that might affect other containers or the host system. This in turn can increase the risk of security breaches. Parts of these vulnerabilities can be addressed with proper configuration and management, but even with all of these, standalone containers just do not offer enough robust isolation. Another weakness of standalone containers is their limited networking capabilities. They do not have advanced networking features such as service discovery, network segmentation, and secure communication channels. And as a result, their ability to communicate efficiently in complex network topologies may be limited. Because these advanced networking features are missing or require much additional configuration, the deployment and management of distributed applications can become more complicated if we are only using standalone containers. Standalone containers also face challenges in scaling because they do not inherently have mechanisms for automated scaling. This can be crucial for handling varying workloads and ensuring performance. Unless we are using a container orchestration technology like Kubernetes, it is difficult to adjust the number of running container instances in response to changes in demand. Manual scaling is very labor intensive and error prone and will usually end up either over provisioning, that is, wasting resources, or under provisioning, leading to performance issues and downtime. Automated orchestration tools are a must in order to effectively manage scaling. And that exactly is what Kubernetes is. Kubernetes is an orchestration technology that's designed to manage and automate the deployment, scaling, and operations of containerized apps. It transforms isolated standalone containers running on different hardware into a cohesive and unified cluster that acts as a single system. Kubernetes will handle the distribution of containers across nodes in the cluster and help ensure optimal resource utilization and high availability. Kubernetes is effectively a middle ground between IaaS, that is infra as a service, and PaaS, that is platform as a service. Kubernetes provides a high level of abstraction over the raw infra, but it still has more flexibility than traditional PaaS solutions. It will allow users to automate the deployment, scaling, and management of containerized apps. This is similar to the ease of use that we get with PaaS, but without the strict constraints on application architecture. Kubernetes based solutions typically leverage the underlying IaaS resources for compute storage and networking, and this ensures that developers retain control over their environment tools. In addition, Kubernetes mitigates vendor lock in because it's open source and works across different cloud providers as well as on prem. This enables organizations to adopt hybrid or multi cloud strategies and seamlessly run and manage apps across different cloud infrastructures. In the spectrum of compute solutions on the Google Cloud, Google Kubernetes Engine or GKE is the Kubernetes orchestration solution. As we can see here, it sits to the right of Google Compute Engine, which is the infra as a service offering, and to the left of Google App Engine, which is the platform as a service offering. And then as we get towards the right end of this continuum, we have the serverless solutions like Cloud Functions and Cloud Run. It's worth mentioning that Cloud Run also makes use of containers. However, it does not offer support for orchestration. Let's talk about the many benefits that Kubernetes has as an orchestrator. The first is fault tolerance. It detects and responds to failures within the cluster. So, if a node or a container fails, Kubernetes will automatically detect this and then reschedule the affected containers onto healthy nodes and thereby minimize downtime. This capability ensures high availability and reliability of apps. Fault tolerance mechanisms in Kubernetes help in maintaining service continuity even in the face of hardware or software failures. Kubernetes supports auto healing capabilities by monitoring the health of containers and nodes. It will automatically restart containers that fail, replace and reschedule containers when nodes die, and kill containers that do not respond to user defined health checks. This ensures that the application remains in a healthy state without manual intervention. Auto healing improves resilience and reduces the burden on operations teams, allowing them to focus on other critical tasks. Kubernetes provides a strong level of isolation using namespaces, resource quotas, and security policies. These work to isolate applications as well as teams. This enhances security by preventing apps from interfering with each other, and it ensures that resources are allocated fairly among different teams or projects. By running containers in isolated environments, Kubernetes minimizes the risk of cross contamination and enhances the overall security posture. This is especially important for multi tenant environments where multiple apps or users might share the same cluster. Kubernetes has strong support for scaling in the form of horizontal scaling as well as auto scaling. Developers can specify scaling policies, and Kubernetes will automatically adjust the number of replicas based on CPU utilization and other metrics. This helps in maintaining performance and availability during periods of peak demand and improves the user experience. Autoscaling in the context of Kubernetes refers to a specific feature known as the horizontal pod autoscaler or HPA. The term pod in Kubernetes refers to a group of one or more containers with shared storage and network resources. Essentially, a pod is the smallest deployable unit that you can create and manage. On Kubernetes, we can use scaling either in the form of HPA or with horizontal scaling based on manual or custom metrics. Autoscaling using HPA is great for simple scaling based on resource utilization. It's easy to set up and manage, and this is suitable for most common workloads. Finally, Kubernetes provides built in load balancing, which helps to distribute traffic evenly across all running instances of an app. By balancing this load, Kubernetes ensures that no single instance is overwhelmed, and this enhances application performance as well as reliability. This automatic traffic distribution helps in preventing downtime and is a big additional plus of using Kubernetes. Let's spend some time understanding the architecture of a Kubernetes cluster. The cluster architecture is based on a master worker setup. This separation of concerns ensures that the master node deals with orchestration and management, and the worker nodes execute the application workloads. And taken together, we get a scalable and efficient infrastructure for deploying containerized apps. The master node represents the control plane, and it manages the entire cluster and performs coordination and scheduling activities, maintenance of the desired state, the scaling of applications, and the rolling out of updates. The master runs critical components such as the API server, etcd, which is a distributed key value store for cluster data, the controller manager, and the scheduler. The master node also has an API server which can be used by clients who wish to connect or communicate with the cluster via either the command line interface or a user interface. The scheduler assigns pods to nodes based on resource requirements and constraints. It takes into account factors like resource availability, workload requirements, and policies to ensure the efficient placement of the pods. And the scheduler will aim to optimize resource usage as well as performance across the cluster. The controller manager runs controllers, which are background processes that manage the cluster state. There are different controllers, such as the node controller, which is responsible for detecting and responding to node failures, replication controller, which ensures that the desired number of pod replicas exist, and that pods correctly encapsulate the containers. There's also an endpoint controller to manage endpoint objects. etcd is a consistent and highly available key value store, and it stores cluster data which includes the configuration, state, and metadata. etcd ensures consistency across the cluster and serves as a reliable source of truth for the cluster state. And finally, the API server is the central management point of the cluster. It processes RESTful API calls, handles authentication, and validates and configures data for the various objects that Kubernetes controls. Within the cluster, there are also worker nodes that are responsible for running the containerized applications. Each worker node includes a number of components: the kubelet, which is responsible for communication with the master in order to ensure that containers are running as expected, and the kube proxy, which manages networking and load balancing. Then, of course, each worker node needs to support the container runtime, which could be Docker or some other container technology, above which lie the individual pods. You can see that each pod can be thought of as the logical grouping within which we have similar containers. So, containers within the pod are not highly abstracted from each other. They share many resources and state. So, again, the kubelet is the primary agent that runs on each worker node and manages the life cycle of the containers. It manages the pod abstraction within which the containers run, and it also interacts with the container runtime, such as Docker, in order to start, stop, and manage containers. Kube proxy is the network proxy. It facilitates networking and load balancing across services within the cluster. It manages IP addresses and port forwarding. The container runtime is the software that's actually responsible for running the containers. This is what will pull container images from a registry. It will start and stop containers and interact with the kubelet in order to manage the container lifecycle. Docker and Containerd are popular choices here. We've discussed Kubernetes as a middle ground between IaaS and PaaS. Let's understand why we might choose Kubernetes over either of these other options. The first is portability and multi cloud flexibility. Kubernetes is platform agnostic, and this allows apps to run consistently across various cloud providers and on prem environments. If you were to contrast this with either the IaaS or PaaS offerings on the Google Cloud, those do not have this benefit. Neither Google Compute Engine nor App Engine can claim to be portable or multi cloud. This portability allows organizations to avoid vendor lock in. It adds flexibility to the deployment solutions and simplifies migration between environments. All in all, it leads to a much more robust and resilient infra strategy. Secondly, Kubernetes supports advanced orchestration and automation, and these features compensate for many of the limitations of standalone containers. These features allow us to carry out automated deployment, scaling, load balancing, and self healing. These capabilities streamline the management of containerized apps. They greatly reduce the amount of manual effort needed to scale infra and ensure that the apps remain available and performant, automatically responding to changes in demand and automatically recovering from failures. We discussed the many benefits of the microservices architecture, and Kubernetes is designed specifically to support microservices architectures. This allows applications to be broken down into smaller, independently deployable services and allows for greater agility. Teams can now develop, test, and deploy their services independently, and we can sidestep most of the weaknesses of traditional monolithic architectures. Lastly, because of its great popularity, Kubernetes has evolved into a dynamic and thriving community and ecosystem. It has a large and active open source community, and it also has a rich ecosystem of tools and integrations. In the technology horse races of the last 5 years, Kubernetes has emerged as a big winner, and that in turn means that more and more developers and members of the community consider it worth their while adding to it. This extensive ecosystem offers a lot of extensions and plugins for monitoring, logging, security, and all of these allow organizations to customize and improve their Kubernetes deployments. Now that we have a good handle on containers and Kubernetes, let's turn our attention to the Google Cloud product, that's the Google Kubernetes Engine. This is a managed Kubernetes service offered on the Google Cloud. It simplifies the deployment, management, and scaling of containerized apps. GKE automates many of the complex tasks involved in running Kubernetes, such as cluster provisioning, node management, and software updates. It allows developers to focus more on building and deploying apps, and in this way, it's similar to all of the other managed services. GKE is probably, along with BigQuery, one of the most popular services on the Google Cloud, and this also comes down to its robust features. For instance, automatic updates, node auto repair, and integrated monitoring and logging. These will connect to Google Cloud's operations suite. GKE will support both hybrid and multi cloud environments and enables seamless integration and portability across different cloud infrastructures. Let's talk through some of the benefits of using the Google Kubernetes engine. The first of these is the benefit of getting Google Cloud's load balancing for VMs. GKE leverages Google Cloud's robust load balancing capabilities to distribute traffic across multiple VM instances. In this context, it's worth mentioning that GKE leverages Google VMs. So, in a sense, GKE primarily relies on GCE, that is Google Compute Engine, as the default and most widely used infra option. But that's not exclusively true because it is possible to run GKE on underlying infrastructure other than Google Cloud VMs, and that service, of course, is called Anthos. Coming back to the load balancing aspect, GKE will ensure high availability and reliability by automatically balancing the load and preventing any single instance from becoming a bottleneck. This leads to an improved user experience with more consistent response times, and this also makes GKE better at handling varying levels of traffic efficiently. Google's load balancing also supports global distribution so that users from different geographic locations all get consistent performance. GKE supports automatic scaling of nodes in a cluster. Again, please note that we are now not talking about the scaling of the pods which contain containers. We are talking about the nodes contained within the GKE cluster. This automatic scaling increases the number of nodes in the cluster based on current demand and workload. This dynamic scaling ensures that the apps have the required resources to handle increased load while also optimizing costs by scaling down during low demand periods. This particular feature plays very well with the scaling support available in Kubernetes. Features like HPA perform horizontal pod autoscaling, but as you might imagine, if the number of pods in the cluster is going to grow, then it probably also makes sense for the nodes available to support all of those pods to be increased or grown. GKE supports automatic upgrades for the software on the nodes. This ensures that they are running the latest, most secure and stable versions and also reduces the operational burden on administrators. They no longer need to manually track and apply updates. The automatic upgrades enhance security by ensuring that nodes are protected against the latest disclosed vulnerabilities and benefit from features as well as patches. All of this helps to maintain cluster stability and reliability without downtime or disruption. GKE has node auto repair. This helps with node health and availability. This will automatically detect and repair unhealthy nodes in order to ensure that the cluster remains operational. Finally, Google Kubernetes Engine integrates with Google Cloud's operations suite and provides strong support for logging and monitoring. This allows for real time visibility into the performance and health of the cluster and the apps. This can help identify and diagnose issues quickly, and it also ensures proactive management and maintenance. The detailed logs and metrics can also be used to better understand and optimize resource usage, as well as the efficiency and the reliability of the infra. The Google Kubernetes engine has two modes of operation, the autopilot mode and the standard mode. Let's talk about these quickly in turn. Autopilot is a fully managed mode. Here, Google Cloud will handle the operational aspects of the Kubernetes infrastructure, including provisioning and managing the cluster's control plane and nodes, applying security patches, and handling upgrades. In autopilot mode, for instance, you will have no control over the scaling, the types of the machines used for the underlying infra, or on the maintenance of node health. Autopilot simplifies cluster management because it automates many of the operational tasks completely. It allows developers to focus more on deploying and running apps rather than on managing infra. This is ideal for enterprises looking for a very hands off approach to their Kubernetes cluster management. On the other hand, if you decide that you would like more control over the configuration and management of your Kubernetes cluster, then the GKE standard mode is probably right for you. Here, the service will still manage the control plane, but the user is responsible for managing the node pools. This will include decisions around selection of machine types, scaling, and the maintenance of node health. The standard mode offers more flexibility and customization options, so users can tailor their cluster configuration to meet specific requirements and use cases. When would you pick autopilot mode? Well, Google recommends running production workloads on autopilot in most cases, so this should be your default choice. Autopilot has a default configuration and has benefits like cost efficiency. You'll only pay for the compute that your workloads use while running. You will not pay for any unused capacity on nodes, system pods, OS costs, or unscheduled workloads. You also get the benefit of automation because Google will manage the nodes, it will create new nodes for your apps, and configure automatic upgrades and repairs. Here, GKE will automatically scale nodes and workloads based on traffic. Finally, you also get an improved security posture and higher reliability. Autopilot clusters enable many GKE security settings by default, and this is also true for Kubernetes best practices. These are also implemented by default in autopilot clusters. In addition, GKE will automatically apply security patches to your nodes whenever applicable. So your default choice should be an autopilot cluster, but there are also times when it makes sense to go with the standard mode. Here, you will manage every configuration setting in your cluster and nodes. This will include managing groups of nodes called node pools. All of the instances within a node pool will share various characteristics. Under the shared responsibility model, Google will still manage the control plane, but now you must configure the nodes. So in the standard mode, the management of node pools is on us. Security is also a little more complicated in standard mode. GKE standard clusters have various default hardening measures applied, but many GKE security features are not enabled by default. You will need to enable these features manually and configure the settings. The onus of monitoring and designing our workloads so that GKE can schedule them efficiently also lies on us. We'll have to do this in a way that minimizes unused resources. This is using techniques known as bin packing. This is one strategy, there are others. Bin packing specifically refers to a strategy for efficiently utilizing node cluster resources by placing pods, that is, groups of containers, onto them. The idea is to try and pack as many items as possible into the bins. Here, each bin corresponds to a node without wasting space, that is, without wasting the resources. Configuration of autoscaling is also now dependent on the user. So the user will need to set up and configure node auto provisioning, automatic scaling settings, and make sure that the nodes don't have too many resources or too few resources. Consequently, the onus of resource management has also shifted back to the user. We've got to keep evaluating the resource needs of different workloads in order to ensure that the resource requests meet the workload requests. Version management is also now incumbent on the user. Best practices such as automatic GKE system version upgrades and release channel enrollment are off by default in standard clusters. We can configure auto upgrades and GKE versions when we create or update the cluster, but once again, the responsibility lies on us. As you can tell, there is a lot of functionality that we give up when we choose standard mode, and that's why Google's recommendation makes sense. In the vast majority of generic use cases, the autopilot clusters are a better choice. It's also important to understand the pricing implications because there are significant differences in the pricing models. In autopilot mode, we only pay for the compute resources that we consume while our workloads are running. We do not pay for unused resources on nodes, OS running costs, unscheduled workloads, or system workloads. In the standard mode, on the other hand, we pay for compute resources on each node, regardless of whether pods actually run on the node. In other words, we are paying for unused resources, so we are paying for what we allocate and not for what we use. You should manage workload scheduling in order to minimize resource wastage on nodes. Ensuring a consistent level of resource usage efficiency in standard clusters requires that you constantly monitor the state of your cluster. On the other hand, with autopilot clusters, GKE will do the monitoring and management for you. After hearing all of this, you might be like, I'm never going to use standard mode ever. But that's not a wise choice. There are clearly use cases where the standard mode makes sense. Let's say, for instance, that you want very granular control over your config settings. For instance, the ability to directly connect to your nodes using SSH. Or you might want to install or modify software that's running on the nodes themselves, such as changing the node OS. The standard mode will also allow you to customize the node system config, for instance, by using Linux syscontrols. There are actions that are restricted in autopilot, such as, for instance, running workloads in GKE managed namespaces such as kube system. Now, it's not usually recommended that you deploy workloads in these namespaces, but if for some reason you really need to do so, then standard mode is your choice. Or maybe you would like to make use of certain features that are only available in the standard mode, such as cloud TPUs. A final situation when you might go with standard mode is if you'd like to test alpha features in open source Kubernetes. As you can see, these use cases are fairly narrow. So as long as your use case is not one of these niche use cases, you are definitely better off going with an autopilot cluster. We started this course off by understanding different migration strategies such as lift and shift migration and improve and move migration. We familiarized ourselves with essential Google Cloud migration terms such as rehost, refactor, and replatform, and followed the cloud migration path. Additionally, we explored various migration tools for compute and data, which are crucial for moving workloads to the cloud efficiently. Next, we learned about the numerous benefits of running workloads on the cloud, such as scalability, cost efficiency, and enhanced performance. We delved into the pros and cons of running compute on virtual machines and explored Google Compute Engine. Finally, we explored compute on containers and the principles of the microservices architecture. We managed containers using Kubernetes and studied the architecture of a Kubernetes cluster. We also work with Google Kubernetes Engine, which is used to deploy, manage, and scale containerized applications efficiently. In conclusion, we built a strong foundation in cloud migration strategies, running compute on virtual machines and containerized environments. We are ready to move on to the next course in this journey, Modern Applications on Google Cloud. Cloud services offer a wide range of compute options, ranging from infra as a service to platform as a service offerings. Understanding serverless computing, managed instance groups, load balancing, and APIs enables organizations to combine these options effectively in order to build scalable, reliable, and integrated applications. In this course, you will learn about serverless computing, including how to use cloud functions, Cloud Run, and App Engine to deploy and manage applications without provisioning servers. These tools will provide you with the flexibility to build and scale applications effortlessly. Next, you will explore managed instance groups and load balancing. You will understand how managed instance groups automate the creation and management of identical virtual machine instances, ensuring high availability. Additionally, you will learn how load balancing distributes traffic across multiple instances, improving the reliability and performance of applications. Finally, you will evaluate uses of APIs, understanding their importance and the various API solutions available on Google Cloud. You will learn how APIs facilitate communication between different software systems, enabling integration and functionality extension. You will also cover running hybrid and multi-cloud workloads, gaining insights into managing applications across diverse cloud environments. While talking about running containerized apps on the Google Cloud, we mentioned that there are two possible choices: Google Kubernetes Engine and Cloud Run. Cloud Run is an example of something known as serverless computing. We've got to discuss Cloud Run in a lot of detail, but in order to build up to that, let's first understand precisely what serverless computing is. As its name would suggest, it's a computing model, and it really only exists in the context of the cloud and hyperscalers. So it's safe to call it a cloud computing model. This is a model of execution where a cloud provider dynamically manages the allocation and provisioning of the servers. Serverless computing takes abstraction to the next level. It allows developers to focus entirely on writing code. The cloud provider will automatically scale the application in response to demand. In serverless computing, we typically have an event-driven architecture where functions are triggered by events such as HTTP requests, database changes, or message queue activity. These models are usually pay as you go, so that users will only be charged for the actual compute time used rather than for pre provisioned resources. As you might imagine, this choice of compute greatly simplifies the development process, reduces operational overhead, and accelerates time to market. Let's quickly talk through a couple of possible use cases for a serverless computing model. Let's say, for instance, that you would like your customers to be able to upload images of their receipts. These customers might be employees in your enterprise. You would like to provide software which helps those employees manage their corporate expenses. To do this with a serverless application, we would write a serverless function that is triggered each time an image is uploaded. This function can perform tasks such as storing the image in cloud storage, extracting text from the image using OCR or a pre-trained API, and then performing automatic expense categorization and then updating the relevant expense record in the database. Here, the cloud provider will manage the scaling and the execution of this function, ensuring that it can handle varying loads without manual intervention. Consider another example where we would like to generate thumbnails for images. Let's say that this is happening in the context of a photo sharing platform where the users can upload high-res images. You want to add a feature which will automatically generate thumbnails for these images so that those thumbnails can be displayed in galleries. With the serverless approach, we create a serverless function that is triggered whenever a new image is uploaded to cloud storage. The function will process the image and create a smaller thumbnail version and save it back to cloud storage. This serverless computing model ensures that the thumbnail generation process is scalable, efficient, and cost effective. You will only pay for the compute time used during the actual image processing tasks. Let's say that nobody ends up using our platform or nobody ends up using this feature, well, we'll pay nothing or very little. Within the world of serverless computing, we can think of two broad subcategories: functions as a service and containers as a service. An example of functions as a service would be cloud functions on the GCP, and of containers as a service would be Cloud Run. Now, not all serverless technologies can be fitted into these two categories. For instance, BigQuery is a serverless enterprise data warehouse. But within the context of serverless compute, these are two broadly representative categories. Let's talk about these in turn, starting with functions as a service. Such a service is a cloud computing service which allows developers to execute code in response to events without managing the underlying infra. In functions as a service, commonly abbreviated to FaaS or FaaS, developers will write individual functions which are small single purpose code snippets. These will run only when triggered by specific events. The cloud provider automatically handles the infra scaling and execution of these functions, charging only for the compute time used during execution. Some attributes of functions as a service. This is essentially event-driven execution. The functions will be executed in response to specific events such as HTTP requests, database changes, or message queue events. The benefit of this form of execution is that the applications can be very responsive and efficient. The functions only run when needed and are only charged when needed. Fast platforms automatically scale based on demand so that the execution of the functions is backed by more compute when demand increases. This allows such services to handle varying workloads seamlessly. That also means that spikes in user traffic do not require manual intervention. A third benefit of functions as a service comes from the simplified deployment. Developers can deploy individual functions without worrying about provisioning and managing servers or containers. This accelerates development life cycles and reduces operational overhead. Next, let's talk about containers as a service. In this cloud service model, users will manage and deploy containerized apps, and they can do so with minimum infrastructure management or commitment. CaaS platforms, as they are known, provide a container runtime environment, orchestration tools, and underlying infrastructure, enabling developers to run and scale containerized applications efficiently. Users can deploy, manage, and scale containers without having to deal with the complexities of the underlying hardware or virtualization layer. Let's outline some of the common features of the containers as a service platforms. Typically, these will use orchestration tools like Kubernetes in order to automate the deployment, scaling, and management of the containerized app. These also have all of the benefits of portability. The containers encapsulate their applications and dependencies. This makes them portable across different environments from development to production. As we've discussed, containers are also very portable across different cloud environments. So that is another factor to keep in mind here. Finally, containers as a service offer security and isolation. Each app will be isolated within a container, so different applications cannot interfere with each other. The CAS platforms often include security features such as vulnerability scanning and compliance checks. Let's examine a schematic block diagram of a serverless architecture. Here, once again, over on the extreme left, we have a couple of clients, a web client and a mobile client. Then in the center, we have authentication, an API gateway, and an external database. Behind that API gateway, we have multiple functions. And then further to the right, we have yet another database layer. Let's talk about this architecture in detail. Going from left to right, users interact with our application through either web or mobile clients. These clients will send requests to the backend services via the internet. When a user performs an action such as logging in or submitting data, the client is going to effectively make an HTTP request to the application's backend. Authentication is important here. This is needed in order to verify the identity of the users so that only authorized users can access certain parts of the application. The client's request will first go to the authentication service that will verify the user's credentials. Once the credentials are found to be valid, the service will allow the request to proceed to the next step. Then we get to the API gateway, which once again plays an extremely important role. It is the single entry point for all client requests, and it's the gateway which will route those requests to the appropriate backend functions. So it's only after authentication that the request gets forwarded to the API gateway. The API gateway will then determine which of the serverless functions should handle the request based on the endpoint being accessed, and it will then route the request accordingly. To the right of the API gateway lie the individual serverless functions. Each of these is a small single-purpose piece of code used to perform a specific task. In this diagram, we have three functions, functions 1, 2, and 3. The API gateway will route the user request to the relevant serverless function based on the properties of the request. These functions will process the incoming request, and this might include operations like reading from or writing to a database, processing data, or performing calculations. Importantly, each function operates independently and scales automatically based on the load. Finally, let's talk a little bit about the database interaction in this architecture. These individual serverless functions will very likely need to interact with databases in order to store or retrieve data. Each of these functions could either access an external database, which we see towards the bottom left, or a dedicated database, which we see at the bottom right. They will execute the necessary database operations and return the results to the client through the API gateway. So once again, each of the functions is going to send its responses back to the API gateway, which will then forward these on to the web or mobile client. The client will then receive the response and update the user interface accordingly. Serverless computing has many benefits, and that's why this model has also become very popular in recent years. A primary attraction is the cost efficiency of serverless computing. Because these follow a pay-as-you-go model, we are only charged for the actual compute time when our functions are actually being invoked. This eliminates the need to pay for idle resources and reduces overall costs. The scalability of serverless platforms is also a big attraction. As discussed, these can scale applications in response to demand and handle spikes and drops in traffic seamlessly. It's worth mentioning here that scalability is a benefit both ways. So serverless compute options are great for dealing with unpredictable workloads, either which see spikes in demand or see equally sharp drops in demand. A third benefit is the greatly reduced operational complexity. Here, the cloud provider manages the infra, which includes the server maintenance, patching, and scaling. All of these lead to much faster development and deployment, which in turn improves time to market. In a fast changing market environment, this agility can allow businesses to respond quickly to changes in customer requirements and market demands. We've now discussed a couple of different types of serverless compute. Remember that we spoke about functions as a service and containers as a service. On the Google Cloud, we've got services, managed services for each of these options. Cloud Functions, that's functions as a service, and Cloud Run, which is containers as a service. Let's start by talking about Cloud Functions. The Cloud Functions service is a serverless computing service that allows developers to run code in response to specific events. It's designed for lightweight event-driven apps where individual functions will execute in response to HTTP triggers, database changes, or Google Cloud Storage events. The Google Cloud Platform will handle all aspects of the function execution, including scaling, load balancing, resource management, and thereby ensure high availability and performance. Cloud functions are ideal for use cases like real-time data processing, automated workflows, and microservices. We've now discussed a couple of different types of serverless compute. Remember that we spoke about functions as a service and containers as a service. On the Google Cloud, we've got services, managed services for each of these options. Cloud Functions, that's functions as a service, and Cloud Run, which is containers as a service. Let's start by talking about Cloud Functions. The Cloud Functions service is a serverless computing service that allows developers to run code in response to specific events. It's designed for lightweight event-driven apps where individual functions will execute in response to HTTP triggers, database changes, or Google Cloud Storage events. The Google Cloud Platform will handle all aspects of the function execution, including scaling, load balancing, resource management, and thereby ensure high availability and performance. Cloud functions are ideal for use cases like real-time data processing, automated workflows, and microservices. In terms of the continuum of compute products on the Google Cloud Platform, Cloud Functions are way over on the extreme right. These are serverless and these have the highest level of abstraction, even more than Cloud Run, because at least in the case of Cloud Run, we've got to supply the container. Now we've got Google Cloud Functions here way over on the PaaS end. PaaS is short for Platform as a Service. So the question is, what platform does the Cloud Functions service provide? And the answer? Well, it's an event-driven serverless compute platform. The chain of events here is pretty intuitive. An event occurs somewhere, for instance, someone uploads something to Google Cloud Storage, or a row gets written to a database table. The platform, that is the event-driven Cloud Functions platform, picks up that this event has occurred because it's constantly scanning the environment. And the platform then triggers the execution of the correct cloud function. The code within that cloud function is executed, and that code might interact with other services on the Google Cloud or elsewhere. Here, the next natural question is, what are the kinds of events that can trigger the execution of a cloud function? Thankfully, the Google Cloud supports a very wide range of event types. As we can see here, broadly speaking, there are two types of events: HTTP events and background events. And then under background events, we have various subtypes such as events from cloud storage, PubSub, logging, and Firestore. Let's talk about these in turn, starting with HTTP triggers. These allow cloud functions to be invoked via HTTP requests. This particular use case is perfect for webhooks, RESTful APIs, or for responding to HTTP requests from web and mobile clients. Developers can expose their functions as web endpoints that can be accessed over the internet. Next, let's turn to the background events. One important category here has to do with cloud storage. A cloud function may be triggered by events in Google Cloud Storage, such as when a file is created, deleted, or updated. This particular use case is ideal for scenarios where we'd like to process uploaded images or videos, generate thumbnails, or convert file formats. Functions can automatically react to changes in storage without manual intervention. Another important category of triggers for cloud functions come from PubSub. Google Cloud PubSub is the messaging service. It allows functions to be triggered by messages that are published on a topic. This is useful if we'd like to decouple systems and build complex event-driven architectures. For instance, maybe we'd like a function to be triggered in order to process orders, send notifications, or aggregate data from a database whenever a message is published to a specific topic. Then we have cloud logging triggers. So cloud functions can respond to events triggered by cloud logging, such as for instance when a new log entry is created. This can be used for real-time monitoring and alerting based on log data. Functions can automatically respond to specific log events such as errors or security alerts by taking predefined actions like sending notifications or triggering immediate remediation processes. Triggers might also be fired from the Firebase platform, in particular by events in Firestore, which is the document database. This is particularly useful for mobile and web apps. For instance, a function might trigger on changes to a Firestore database in order to validate data, synchronize information across systems, or handle user authentication events. Let's spend a moment understanding how the Google Cloud Function Service provides concurrency at scale. The idea is that the service will spin up function instances based on the current load. So automatically, the number of function instances will scale up or down based on the volume of incoming requests or events. This can help to deal with spikes in demand without any manual intervention, and by spinning up additional instances during peak times and then scaling down when demand decreases, the platform also optimizes resource usage, reduces costs, and thereby achieves elasticity. It's also worth noting that the functions receive event parameters from the platform. So when a function is triggered, it will get data about the triggering event. That data will come in the form of parameters from the platform into the function invocation. The Cloud Function Service is flexible enough to ensure that a wide range of different types of triggers like HTTP requests, database updates, or file uploads will all be able to send in their appropriate event parameters in the right form to our function. So our function is abstracted away from the details of each of these events, but it still gets event parameters from the platform. The functions do not share state, they do not share memory or variables, and that means that each function instance runs in isolation. This isolation ensures that each instance operates independently, avoiding issues related to concurrency and data consistency. This enhances security and reliability because the failure or misbehavior of one function instance does not affect the others. This design principle supports the stateless nature of serverless functions, which we will come back to, and this makes them easier to manage and scale. Remember that the Cloud Function Service is constantly creating instances of the function object, and that function instance is only designed to handle one request at a time. Well, actually, as an aside, there's a little bit of fine print here. First generation cloud functions work in this way, i.e., they can only handle one request at a time. Second generation cloud functions have improved concurrency, and as a result, we can have multiple requests simultaneously on a single function instance. So if you don't want to deal with any concurrency issues at all, then you go with the first generation where an instance only processes a single request. This means that the concurrency is never at the level of the individual function instance. That in turn simplifies the function's logic. There's no need to manage concurrent requests within a single instance. This ensures that each request is processed quickly and efficiently and improves response times and reliability. By processing a large number of single requests in parallel on different function instances, functions can scale more predictably and maintain consistent performance. One very important implication of all of these design choices is that functions need to be stateless. So a function should not retain any data or state between invocations. Just to be clear, this does not mean that functions cannot access databases, far from it. In fact, any data that needs to be persisted by a cloud function should be stored in external services like databases or storage systems. However, within the body of the function itself, there should not be any dependency between the current execution of that function instance and any previous execution. Cloud functions have a wide variety of use cases. Let's describe some of them. The first has to do with data processing and ETL, which is short for extract, transform, and load. Google Cloud Functions can listen and respond to cloud storage events such as file creation, modification, or deletion. This capability allows us to automate the processing of images, video transcoding, or validation and transformation of data as soon as the changes occur. Also, remember that Cloud Functions can be invoked from any service on the internet, and this makes it a particularly powerful tool for ETL pipelines where we might have unstructured data coming in from non-Google Cloud sources. That brings us to our second use case, that of webhooks. Cloud Functions can be triggered by simple HTTP requests. This makes them ideal for responding to events from third-party systems like GitHub, Slack, or Stripe. By setting up an HTTP trigger, your function can react in real time to events such as code commits, messages, or payment transactions. This allows seamless integration with various external sources and automates workflows based on these external triggers. The Cloud Function Service is great for building lightweight, loosely coupled bits of logic that can be quickly developed and scaled instantly. These functions may be event-driven or directly invoked over HTTPS. This makes them versatile for creating microservices and APIs. This approach also supports a rapid development and deployment of scalable and efficient apps. Along the same lines, Cloud Functions are great for building mobile backends. This is particularly true because of their integration with Firebase, which is Google's own mobile platform. This allows developers to write their mobile backend logic with Cloud Functions. Cloud Functions can listen and respond to various Firebase events. These could be updates from Firebase Analytics, real-time DB changes, user authentication events, and file storage operations. Finally, because of the pub/sub trigger, Cloud Functions can handle data streams from tens or hundreds of thousands of IoT devices. The serverless nature of Cloud Functions ensures that you can scale effortlessly to handle very large amounts of data from numerous devices such as sensors without interacting with or managing the underlying infrastructure at all. Let's now turn our attention to the other serverless compute offering on the Google Cloud. That's Google Cloud Run. Cloud Run is an example of a container as a service offering. This is a fully managed service that allows developers to run containerized applications in a serverless environment. Cloud Run supports any containerized workload, and this allows us to deploy apps written in any language or using any library. It automatically scales our app up or down based on traffic and ensures efficient resource utilization and cost savings in the same way as other serverless solutions. Cloud Run combines the benefits of serverless computing and container orchestration. This makes it ideal for deploying microservices, APIs, and web apps. Within the context of all of Google Cloud's compute solutions, Cloud Run is very much at the platform as a service end. In this respect, it's much more at the right than Google Kubernetes Engine. GKE is the other way to run containerized workloads on the Google Cloud, and GKE is squarely a trade-off between IaaS and PaaS. Cloud Run is much more at the serverless end. As we shall discuss in a moment, Cloud Run does involve more setup on the part of the developer than Cloud Functions, and that's why we have it represented here just to the left of Cloud Functions. Once again, this is a platform, so we can think of Cloud Run as a serverless managed platform that allows us to run containers directly atop Google's scalable architecture. Let's understand the workflow of using Cloud Run. To begin with, we write our code in any language. Cloud Run supports apps written in any programming language or framework as long as they can be packaged into a container, which for practical purposes means that you can use any language of your choice. Next, we need to package up our code in a container image. We can either create our own container image or use a source-based deployment option that Cloud Run provides. In that, Google Cloud will build the container image from the source code. This is a step where the developer might have to get their hands dirty with the containerization if they want to create the container themselves, or alternatively, if they'd prefer not to do so, they can make use of the Cloud Run source-based deployment feature. This will automatically build the container But this is limited only to certain languages. So this is something of a restriction. In any case, once we have our container image, we can then register that with the artifact registry. Google Artifact Registry is the service provided on the Google Cloud. This serves as a centralized repository for container images. Remember that individual containers are instantiated from the container image. Registering the container image ensures that it is versioned, secure, and available for use across different environments. This step is crucial in maintaining the organization and manageability of a containerized application architecture. Next, we can deploy our container directly using Cloud Run. This step is only possible once a container image is in the registry. However, from here, the deployment process is straightforward. It requires minimal config and no manual infrastructure setup. The Cloud Run platform will handle the provisioning, scaling, and management of the containerized app and allows your developers to focus on coding. This direct deployment capability is what makes Cloud Run special. Again, this is where Cloud Run is different from GKE because unlike GKE, there's no cluster creation and no infra management. Cloud Run will automatically handle the underlying infra. This includes the load balancing, scaling, and monitoring. As a result, the operational overhead is lower than with GKE. The user or developer need not worry about setting up or managing Kubernetes clusters or any other individual infra components. Cloud Run has flexible pricing models. These include both request-based and instance-based pricing. In request-based pricing, if an instance is not processing requests, then a CPU is not allocated and you are not charged. However, you do pay a per request fee. In instance-based pricing, however, you are charged for the entire lifetime of an instance and the CPU is always allocated. Here, there's no per request fee. In case you're wondering why we have instance-based pricing, there was no such feature in Cloud Functions. That was all request-based. That's because Cloud Run, unlike Cloud Functions, allow our code to run either as a service or as a job. Let's talk a bit about these two different ways to run our code. Both services and jobs run in the same environment and can use the same integrations with other Google Cloud services. Cloud Run services are designed to run code that responds to web requests or events. These are ideal for apps that need to handle HTTP requests such as APIs, web apps, or microservices. They automatically scale based on the incoming traffic, ensuring that your app remains responsive and performant under varying loads. Cloud Run jobs, on the other hand, are perfect for running code that performs a specific task, that's a job, and then quits when the work is done. These are suitable for batch processing, such as data transformation or any task that has a defined start and end. Once triggered, a Cloud Run job runs to completion and does not persist. This is a way of running batch jobs with serverless execution. The serverless execution simplifies the process of running one-off or periodic jobs because Cloud Run will still automatically handle the provisioning and the execution and will ensure that the job runs reliably and efficiently. A Cloud Run service provides you with the infrastructure required to run a reliable HTTPS endpoint. It's our responsibility to make sure that our code listens on a TCP port and can handle the incoming HTTP requests. The Cloud Run service will ensure that we rapidly scale out in order to handle all incoming requests or to handle increased CPU utilization outside of requests. The service also takes care of versioning because every deployment creates a new immutable revision. You can route incoming traffic to the latest revision, roll back to a previous revision, or split traffic to multiple revisions at the same time, in effect carrying out a gradual rollout. So for instance, if you'd like to reduce the risk of deploying a new revision, you can start by sending a small fraction, maybe 1% of the request to that revision, and then gradually increase that percentage while performing telemetry. Another feature worth noting here is known as scale to zero. If there are no incoming requests to your service, then even the last remaining instance will be removed by the platform. This behavior, which is commonly referred to as scale to zero, can adversely affect the response time when a new request comes in. Because if when that new request comes in, there are no active instances, then a new instance will be created on demand. It is possible to configure your Cloud Run to keep a minimum number of instances active and thus to disable scale to zero. Next, let's talk about Cloud Run jobs. These are particularly useful for what are known as array jobs. A job can start one instance to run our app. That's a common way to run a script or a tool. Then that one instance might have a for loop within it. However, we also could choose to start many identical and independent instances in parallel. That's the array job. Array jobs are faster in processing data that can be split into multiple independent tasks. For instance, if you are resizing and cropping 1,000 images from cloud storage, processing them consecutively is going to be far slower than processing them in parallel with many instances. Cloud Run takes care of this for us with auto scaling. Let's round this conversation off with a head-to-head comparison between Cloud Functions and Cloud Run. The Cloud Function service only supports some limited runtimes, so it's specific. Cloud Run, on the other hand, can work with any runtime that can be packed up in a container, which for practical purposes means almost everything. Cloud Functions can be triggered based on specific platform events. Cloud Run in service mode can be invoked using HTTP requests. Cloud Functions does not have any support for running jobs. It's a purely event-driven service, which is also why it only has a request-based pricing. Cloud Run, on the other hand, has both request-based and instance-based pricing, and that's because it also has support for running jobs. The subject of concurrency is a little complicated. Cloud Functions have no support for concurrency in first-generation functions because every instance can only run one function at a time. This makes coding up first-generation functions much simpler, but it can lead to some overhead in some situations. Second-generation Cloud Functions do support concurrency, and this is where coding up the Cloud Function can get slightly complicated. Cloud Run, on the other hand, has a completely different model of concurrency support because this is handled at the container level. In a nutshell, because of this support for container level concurrency, Cloud Run has better support for concurrency than Cloud Functions. In terms of when you pick these two solutions, use Cloud Functions if you primarily would like to connect to other cloud services on the Google Cloud. Pick Cloud Run if you'd like a simple way to scale and maintain services using containers. And here it's worth keeping in mind that Cloud Run is a lot simpler for containerized workloads than using GKE. There's another compute offering on the Google Cloud, that's App Engine. App Engine has lost popularity, or at least lost the limelight to a certain extent in recent years because of the popularity of containers and GKE. But it's still a very solid solution and one that you should be fully aware of. App Engine is actually one of the oldest compute options available on the Google Cloud. It's been serverless for several years now, and in today's iteration, it can be defined as a fully managed platform as a service that enables developers to build and deploy scalable web apps and services. It supports multiple programming languages including Python, Java, Go, and Node.js, amongst others. It also has a number of built-in services such as NoSQL databases, caching, and task queues to simplify app development. It automatically handles scaling by adjusting resources based on traffic and ensuring that applications can handle varying loads efficiently. It also has all of the usual robust support for monitoring, logging, and versioning. Once again, this is a solid choice for developing and running web apps with minimal operational overhead. Here's a quick look at what an App Engine application looks like. A single application resource consists of one or more services. Each service can be configured to use different runtimes and to operate with different performance settings. Within each service, you deploy versions of that service. So each version can then run one or more instances, depending on how much traffic you've configured it to handle. Let's break all of that down. The App Engine app is created under a Google Cloud project when we create an application resource. That app is a top-level container which includes the service, version, and instance resources that make up the App Engine app. When you create an App Engine app, all your resources are created in the region that you choose. For this reason, we can say that App Engine is a regional product. Services within App Engine help to refactor our large apps into logical components that can securely share the App Engine features and can also communicate with each other. Generally, App Engine services behave like microservices. So you can run your entire app in a single service, or you can design and deploy multiple services, effectively running a set of microservices. For instance, an app that handles incoming customer requests might have separate services for different types of requests. For instance, API requests from mobile devices or web frontends, services to handle internal requests, and separate services to handle add to cart and checkout functionality. Then remember that every service can have versions. Each service within the App Engine app has source code from the app as well as the corresponding App Engine config files. The set of files that we deploy to a service represent a single version of that service. Each time we deploy to that service, we are effectively creating a new version within that same service. Having multiple versions of our app within each service allows us to quickly switch between different versions of that app for rollbacks, testing, or other temporary events. The versions within our services run on one or more instances. By default, App Engine will scale our app to match the load. Our apps will scale up based on the number of instances that are running in order to provide consistent performance, or scale down in order to minimize idle instances and reduce costs. App Engine is available in a couple of different flavors, which are called environments. There's the standard environment, and then there's the flexible environment. Let's talk about each of these in turn, starting with the standard environment. In the standard environment, our app runs in a proprietary sandbox. This sandbox is secure and isolated, which means that the app's access to underlying hardware and operating system resources is limited. This increases security and stability, but of course it has its own downsides. This ensures that the app runs in a controlled environment. There's no possibility of any potential interference with or from other applications. This helps to maintain a consistent runtime environment regardless of the underlying infrastructure. Instance startup is very fast in the standard environment. The App Engine standard environment instances can start up in just a few seconds, and this helps applications scale up quickly in response to traffic spikes and provides a seamless user experience. It also allows for very efficient handling of short-lived or very spiky workloads. Resources will be allocated and deallocated quickly. This can help maintain high performance and availability even during sharp, sudden increases in demand. The standard environment only allows coding in a few specific languages and versions. No other runtimes are possible. So it's quite limiting in terms of your choices of technology. This limitation ensures a highly optimized and stable runtime environment. It provides a robust performance in those languages and runtimes which it does support, but of course it is still very restrictive. This can be a consideration when you are considering whether to use App Engine or not. Also, it's not possible to modify the runtime environment if you're using App Engine standard. So developers cannot change underlying runtime settings or configurations. This is restrictive, but it also helps to maintain security and consistency. Finally, in order to prevent the execution of potentially unsafe or incompatible binaries, the standard environment will not allow the installation of third-party binaries in certain runtimes. This is yet another restriction, but it also has the same effect of ensuring a consistent and secure runtime environment. Let's contrast the App Engine standard environment with the flexible environment, which of course, as its name would suggest, is meant to give you more control. In reality, we can think of the flexible environment as a way to run Docker containers on Google Cloud Compute Engine virtual machine instances. You can certainly see how this particular environment has been superseded by other more recent offerings which allow us to run containerized workloads. However, the flexible environment is still relevant in situations where you do not want Kubernetes. This is a key difference. App Engine Flexible will run Docker containers on an individual VM, so there's no orchestration. The other options like GKE and Cloud Run are all about orchestration. Instances in App Engine Flex environments typically start up within minutes. This is not as fast as the standard environment, but even so, it's still quite efficient. It allows for reasonably quick scaling in response to changing demands. What we get in return is flexibility in terms of choice of technology. We can code in far more languages and versions. It effectively allows developers to use their preferred languages and frameworks because they are going to package up their runtimes into a Docker container. Another benefit of App Engine Flex is that developers can create custom runtimes. So, in use cases where the app has unique or specialized requirements, or where you need specific libraries, frameworks, and tools, you have complete control over the application's execution environment. The App Engine Flexible environment also allows the installation and use of third party binaries. This again is in keeping with the idea of much greater control from the developer perspective in the flexible environment. You ought to be considering Google's App Engine in the standard environment for apps which need very fast scaling and when you're looking for a cost effective solution for dealing with very spikes in traffic, which might very quickly dissipate as well. App Engine Standard is intended to run for free or at very low cost if there is no incoming traffic. For instance, if your app has no incoming user requests, it will scale down to 0 instances. The flexible environment is suitable when you have an application that receives fairly consistent and predictable traffic, so it's not a very spiky profile, or when your app needs to make use of custom runtimes or run native code. So App Engine Flex is perfectly fine if you have normal traffic fluctuations because the parameters will allow scaling up or down gradually. But for very spiky use cases, App Engine Flex is not a good choice. It's also worth mentioning here that if you're deciding between App Engine in the flexible environment versus Cloud Run or GKE, then App Engine Flex is a good choice when you need to work with Docker containers, but when you do not need all of the complexity of Kubernetes orchestration. Next up, we are going to discuss managed instance groups. It turns out that the Google Cloud Platform actually supports both managed and unmanaged instance groups. An instance group is a collection of VM instances that we can control as one entity. Instance groups could be either managed or unmanaged, and these have very different properties. Managed instance groups, or MIGs, automate the management of identical VM instances. They are a way of ensuring high availability and scalability, and managed instance groups also support auto scaling to handle varying loads. They also support auto healing to replace unhealthy instances and rolling updates in order to update instances with minimal downtime. These are ideal for stateless applications and are a way of getting automated and consistent deployment, management, and scaling of VM instances. Instances in a managed instance group are all created together and share many properties. On the other hand, unmanaged instance groups are effectively just a logical mechanism for you to group VM instances together and, above all, to provide load balancing across a fleet of VMs that you already manage yourself. Unmanaged instance groups on the Google Cloud offer a collection of VM instances without any of the automated management features that we just mentioned, such as auto scaling, auto healing, or rolling updates. The flip side of this is that the user has complete control over the configuration and lifecycle of each instance within the unmanaged instance group. That's not true in the case of the managed instance group. This flexibility makes unmanaged instance groups quite suitable for stateful applications or for custom management scenarios where specific control over individual instances is a must. Let's talk a little bit more about managed instance groups because these are the more important. In order to create an instance group, we've got to specify an instance template. So all instances within the managed instance group are created based on an instance template which defines the VM configuration. This includes the machine type, boot disk image, network settings, and metadata. This is a way of ensuring that all of the instances within the group are identical, and this simplifies management and scaling. The instance template also gives the cloud platform a way to create new instances, and that is how the managed instance group can scale up. The service will use the instance template in order to automatically create new VM instances from that template. These instances will of course have the same configuration because they were created from the same template. Managed instance groups are a good choice for stateless serving workloads such as a website front end. They are also suitable for stateless batch jobs if these jobs have high performance or high throughput compute workloads, such as perhaps image processing from a queue. And finally, they are also appropriate for stateful applications such as databases, legacy apps, or long running batch computations with checkpointing. A managed instance group provides high availability through a combination of three different features: auto healing, the regional configuration, that is by using VM instances in different zones, and via load balancing. Let's talk about these features in turn. The managed instance group will automatically repair failed VMs. If a VM instance within the group stops, crashes, or gets preempted, or is deleted by any action not initiated by the managed instance group, the group will automatically recreate that VM based on its original configuration, i.e., with the same VM name and the same template, so that the VM can resume its work. It's also possible to make use of a feature known as application-based auto healing. Here, we can set up a health check which is application-based, which periodically verifies that our application is responding as expected on each of the instances within the managed instance group. If any application is not responding, that means there is likely a problem with the corresponding VM instance, in which case the MIG will automatically recreate that VM, again keeping the same VM name and template. Checking that an application responds is more precise than simply verifying that the virtual machine is up and running. It can also test the logic of the application, and that's why this is known as app-based auto healing. It's possible to have regional managed instance groups which spread app load across different zones. Remember that any individual VM instance resides within a zone. However, with a regional MIG, we can create instances in different zones. This will protect against zonal failures, and this form of replication can help our app to continue serving traffic from instances in the remaining available zones within the same region. Finally, managed instance groups work with load balancing services to distribute traffic across all of the instances within the group. That leads nicely into our conversation of the next feature of managed instance groups, which is scalability. One aspect of the scalability comes from the load balancing, but there's more. When our apps require additional compute resources, the managed instance group, if it has auto scaling turned on, can automatically grow the number of instances in the group to meet demand. If demand drops, then the auto scaled managed instance group will also automatically shrink in order to reduce costs. When you create an auto scaled managed instance group, you've got to specify an auto scaling policy, which will indicate to the platform when we would like to scale the group. We can set signals based on CPU utilization, load balancing capacity, and other similar metrics. In this way, managed instance groups support auto scaling that dynamically adds or removes VM instances from the group in response to increases or decreases in load. Another important feature is the support for automated updates. The automatic updater for managed instance groups allows us to safely deploy new versions of software, and it also has a range of rollout scenarios such as rolling updates and canary updates. You can control the speed and scope of deployment as well as the level of disruption to service that you are willing to countenance. Let's also talk briefly about unmanaged instance groups. These are a way to manage heterogeneous instances where we can arbitrarily add and remove instances from the group. Unmanaged instance groups do not offer any of these features we just discussed, such as auto scaling, auto healing, rolling update support, multi-zone support, or the use of instance templates. None of these features are available with unmanaged instance groups, so they are not a good fit if you are looking to deploy highly available and scalable workloads. On the other hand, if all that you really need is load balancing, and you'd like that load balancing to sit in front of a group of already existing or heterogeneous instances, then unmanaged instance groups might be a good option. Now we are going to talk about load balancing. This is the process of distributing application requests across multiple servers in order to ensure that no single server becomes overwhelmed, and this keeps performance, reliability, and availability of our application intact. Now, please note that just because we use the term server, that does not mean that load balancing is specific to any one of the compute options on the Google Cloud. In general, load balancing needs to work with all different compute backends. So this is just a general concept, because if you stop to think about it, even in serverless technologies like Cloud Run or Cloud Functions, in the backend, there still are servers which have to respond to and handle incoming client requests. So once again, load balancing works with all compute options. Here now is a schematic diagram of how load balancing works. You can see here that the load balancer sits between the client devices and the backend servers. When the incoming requests come in on the internet, those requests are routed to the most appropriate server by the load balancer. And for this, the load balancer will take into account factors like the current load, the health of the different servers, and the response times of those different servers to probes that are sent by the load balancer. In this way, the load balancer will prevent the overload of any one server, it will reduce latency and improve the overall user experience. Additionally, load balancers can perform health checks on servers to reroute traffic away from healthy or down servers, and this also ensures continuous service availability. There are many benefits to load balancers. Let's talk about some of them in turn, starting with enhanced performance. Load balancing improves overall system performance by distributing traffic evenly across multiple servers. As we've discussed, this distribution makes sure that no single server is overwhelmed and becomes a bottleneck, and in this way, each server is able to handle a manageable amount of work. Response times are quicker and users experience more consistent and reliable service. By optimizing resource utilization, load balancing helps to maintain high performance even during peak traffic times. Load balancers ensure a high level of availability and reliability. This is done by automatically redirecting traffic away from unhealthy or down servers and towards healthy ones. This redundancy prevents service interruptions and minimizes downtime. Additionally, load balancers perform continuous health checks on the servers and ensure that only properly functioning servers receive traffic. Load balancing is a way to achieve greater scalability because it allows the addition of new servers at the back end. These can be added to the compute pool without disrupting the existing system. As traffic increases, administrators can seamlessly add more servers to handle the additional load. Once again, please note that this also happens in the case of the serverless compute options like Cloud Run or Cloud Functions. It's just here that the additional compute is not added manually by user administrators, rather it's done by the platform. It's also worth mentioning here that load balancing allows for both horizontal scaling and vertical scaling. Recall that horizontal scaling involves adding more servers, vertical scaling involves upgrading existing servers. Load balancers also have a completely unrelated benefit in that they provide improved security. They mask the IP address of the backend servers and they make it much harder for attackers to target any specific server directly. They can also be configured to perform SSL termination, offloading the SSL decryption process from the backend servers and reducing their computational load. Additionally, load balancers can be set up to detect and mitigate certain types of attacks, such as DDoS attacks, by filtering out malicious traffic before it reaches the individual servers. Because this is a single point of access into the network, it's also relatively easier. It reduces the attack surface and we can harden the load balancer suitably. This gives an added layer of protection and helps safeguard the system as a whole against threats and vulnerabilities. The managed load balancing service on the Google Cloud is called Google Cloud Load Balancing. This is a fully managed service. It distributes incoming traffic across multiple backend instances and uses a variety of load balancing at different levels of the protocol stack, including HTTPS, TCP, SSL, and UDP. In this way, it caters to different types of applications and network protocols. Google Cloud Load Balancing can distribute traffic globally And in that way, it can route traffic to the nearest or the most appropriate or available backend. As this schematic diagram shows, cloud load balancing is a service that will work with any one of different backends. Those backends could be Compute Engine, VM instances, or managed instance groups, App Engine, Cloud Run, Google Kubernetes Engine, and Cloud Functions. In addition, there are a couple of points in here which might surprise you. We can use Google Cloud Load Balancing with a cloud storage backend. This is a way to direct user traffic to static content that's stored in GCS buckets. It's ideal for serving public assets like website files or images. It's also possible to use Google Cloud Load Balancing with external backends, that is, servers which could be in an on-prem data center or on another cloud provider. This requires setting up internet-facing load balancers, and we'll also need to configure network endpoints for the external resources. Let's outline some of the features of cloud load balancing. The first is the single IP address. With cloud load balancing, a single IP address is going to be the front end for all backend instances in all regions around the world. In this way, we get cross-region load balancing, including automatic multi-region failover. This moves traffic to failover backends if the primary backend becomes unhealthy. Cloud load balancing will react instantaneously to changes in users, traffic, network, backend health, and other conditions. Cloud load balancing makes auto-scaling seamless because incoming user requests do not go directly to any individual server, so those requests cannot be aware of any individual server. They all hit the single IP address, which in turn means that we can add or take away capacity as needed. So cloud load balancing can scale as users and traffic grow. It can easily handle huge, unexpected, and instantaneous spikes by diverting traffic to other regions that can take traffic. Autoscaling does not require pre-warming. You can scale from zero to full traffic in a matter of seconds. Finally, this is a type of software-defined load balancing. This is fully distributed and managed. It's not instance-based or device-based. So we don't have to go through all of the trouble of dealing with physical load balancing infrastructure or with all of the high availability, scale, and other challenges with instance-based load balancers. We can have different types of load balancing strategies. These could be internal or external. External load balancing is when your users reach your applications from the internet. However, if all of your clients are inside on the Google Cloud, then internal load balancing will suffice. Also, based on where we distribute our load balanced resources, we can have either global or regional load balancing. If it's global load balancing that we'd like, then we've got to make sure that our load balanced resources are in multiple regions. We've now covered a wide range of cloud technologies, and this has hopefully enabled us to appreciate the benefits of modern cloud application development. Once again, let's take stock of where we stand, and one good way of doing this is by seeing where we started out from. In traditional apps, we'd have a single monolithic code base where all components would be tightly coupled. This meant that the user interface, business logic, and data access layers were all interconnected and interdependent. This also meant that complexity of deployment was high. Deploying new features or updates required redeploying the entire app. Any change, even minor, necessitated the full deployment cycle. Traditionally, apps were built using a centralized architecture where all services were hosted and managed on a single server or on a closely integrated cluster of servers. Once again, we have that same theme of tightly coupled components. And once again, that led to less flexibility in updates or in replacing individual parts. The software development lifecycle also was very different. In the very good old days, there was the waterfall model, which was very linear and sequential, where each phase must be completed before the next one begins. The phases included requirement analysis, design, implementation, testing, deployment, and maintenance. Until the advent of more modern SDLC methods like DevOps and CI/CD, integration and testing was still manual. And this in turn meant that there was significant time and effort involved in ensuring the changes in one part of the app do not negatively impact the other parts. In contrast, modern apps, particularly modern cloud-based apps, can be usually modeled as a collection of microservices. Each service is designed to perform a specific function, and this gives rise to a modular approach. Developers can focus on individual components, they can improve the maintainability of their code, and reduce the overall complexity of the app. By breaking the app down into smaller and more manageable pieces, teams can develop faster, they can test more thoroughly, and deploy features independently. This architecture leads to independently deployable components. The microservices are independently deployable but also independently scalable and maintainable. Each microservice can be updated or scaled without affecting the rest of the application. This sets the stage for continuous delivery and rapid iteration. It reduces the risk of large-scale catastrophic failures and makes it easier to isolate and fix issues, and leads to a more resilient and flexible app architecture. This in turn leads to far greater speed of development, which gives accelerated time to market. Enterprises can unlock business value by coming to market faster because features can be released sooner after they have been completed without waiting for the rest of the application to be complete as well. This continuous delivery model enables faster feedback cycles, and so your enterprise can respond more quickly to changing market demands and customer feedback. It also allows the release of smaller and incremental updates rather than the high risk big bang updates that we used to see in the old traditional cycle. The use of microservices also leads to enhanced scalability and resource optimization because this architecture lends itself beautifully to cloud native features like auto scaling, load balancing, and auto healing. As a result, applications can handle varying workloads and maintain high availability even under peak conditions. And what's more, they can do this without compromising on resource allocation. They stick to an elastic pay as you go model. Let's talk about some characteristics of modern cloud hosted applications. These typically make use of managed or partially managed services to streamline operations and improve efficiency. So, for instance, such an application would tend to use Cloud SQL rather than MySQL, or Google Kubernetes Engine rather than native open source Kubernetes. Why this focus on managed services for the infrastructure management? Well, the answer is because managed services take away the burden of day to day management, such as patching, upgrades, and monitoring. The cloud platform takes the responsibility of ensuring that the underlying infra is up to date and secure. It reduces the risk of vulnerabilities and reduces downtime. As a result, enterprises can maintain high availability and performance without the need for extensive in house expertise in all of the little aspects of managing the infra. Modern apps might also make use of a hybrid approach with partially managed services. Businesses will manage some aspects of their cloud based applications themselves, while the cloud provider manages others. This model has greater flexibility, and if we look closely, we can see that this choice between fully managed and partially managed services is available across a wide range of Google Cloud offerings. Think about GKE Autopilot versus GKE Standard, App Engine Standard versus App Engine Flexible, and so on. A final aspect of the modern cloud hosted application is that it frees up staff from the enterprise for more strategic tasks. So, in summary, the cloud based approach has many benefits. We should be looking for the most highly managed service that we can go with. In specific cases where we need to retain control, we can always go with a hybrid approach and use partially managed services instead. Examples of partially managed services would include Google Cloud SQL, Cloud Dataproc, and the Google Kubernetes Engine. Examples of fully managed services would include Cloud Spanner, Cloud BigQuery, PubSub, and Cloud Functions. Let's turn our attention back to legacy applications and how there are some specific services for rehosting legacy apps. Let's quickly jog our memory. There are three types of migrations, broadly speaking: lift and shift, improve and move, and rip and replace. In terms of the Google Cloud lexicon, lift and shift is called rehost, improve and move is replatform, and rip and replace is reimagine. We are currently talking about rehosting legacy applications, and so we are going to be focused on the lift and shift options. Rehosting or lift and shift migration involves moving apps to the cloud with little to no modification. Improve and move migrations involve refactoring existing applications to better leverage cloud offerings, and rip and replace effectively involve rebuilding the apps from scratch. Let's talk a little bit more about the lift and shift and when we might choose to go with the rehosting of legacy apps. There's a very real set of use cases where a company might choose to rehost legacy apps because of incompatibility with cloud native applications. When a business decides to modernize and move its operations to the cloud, it may still be running several specialized legacy apps that are not compatible with the cloud. These legacy systems will typically have unique configurations, dependencies, or architectures that cannot easily be adopted in a cloud native environment. Instead of rewriting or refactoring these old and well tried and tested apps, businesses might just opt to rehost them. This will allow the company to quickly migrate to the cloud while maintaining functionality of the critical legacy apps. Some of the other considerations might include speed of migration, because after all, when rapid cloud adoption is required, rehosting or lift and shift is the most effective. A cost benefit analysis might also indicate that it is more cost effective to rehost the legacy application than to rewrite or refactor for the cloud. A final and very important consideration is preserving business continuity. For businesses that rely heavily on legacy apps for day to day operations, this could be a very important factor. Rehosting will allow these business critical apps to continue running without interruption and without the disruption, but they would still be hosted in the new cloud environment. In particular, there are two Google solutions for rehosting that we must talk about, both from the perspective of actually using the Google Cloud and from the Digital Cloud Leader certification perspective. The first of these is Google Cloud VMware Engine. VMware is a market leader in virtualization software. This is the technology that allows multiple virtual machines or VMs to run on a single physical machine, sharing resources such as CPU, memory, and storage. Because of VMware's dominant position here for so long, there is a very large number of legacy use cases where organizations have a large number of VMware VM instances, and these now need to be moved to the cloud. This is where Google Cloud VMware Engine comes into play. This is a fully managed service that will allow businesses to lift and shift their VMware workloads to the Google Cloud. And what's more, they can do this from any environment. So these might be on-prem VMware VM instances, or they might be VMware instances running on a different cloud platform. All of these will be managed by this particular service. The tool that we should be making use of in order to carry out the lift and shift is VMware HCX, and the destination is Google Cloud VMware Engine. We've seen now multiple times that the naming of these Google services can be rather odd, and another very plainly named service is Google's Bare Metal solution. Yes, that's right. That's the name of a service. This is the Google service that provides dedicated physical servers. These are going to be hosted in Google data centers. We can run specialized workloads on top of these bare metal servers with access to the hardware. And here we should explicitly mention Google's bare metal solution for Oracle. This is specifically designed to support Oracle databases and applications by providing dedicated high-performance hardware that meets Oracle's very stringent standards. How does the licensing work? Well, you can bring your own Oracle licenses. This reduces the licensing costs associated with running Oracle on the cloud. Let's now turn our attention to APIs, or Application Programmer Interfaces. Define them and then understand their importance. We can think of an API as a set of defined rules, a kind of shared language. This allows different apps to communicate with one another, and in this way, it helps with the building and integration of complex software systems. So the APIs define methods and data formats that the apps can use in order to request and exchange information. They act as an intermediary layer for data transfers, and in this way, companies can use APIs in order to open up their data or their code in a protected fashion for use by third parties. API includes the term interface, and like interfaces in programming languages like Java, an API is effectively a contract with documentation which represents an agreement between the parties and that then allows those parties to collaborate with each other. Broadly speaking, there are four steps involved in the working of any API call. The first is request initiation. This is from a client like a web or a mobile app that's then sent to the API endpoint. The API endpoint functions as the common front end for all incoming requests. The API gateway, which is running on the endpoint, will then authenticate the request and satisfy itself that this is a valid request. Once the individual backend server sends its response back to the gateway, that can then be forwarded on to the initiating application. Here on screen now is a schematic block diagram representing a set of API calls, including the request and then the response. Let's break this down and see what happens at each step of the way. It begins with request initiation. The process begins when the client, which could be either an individual developer writing code or another software application, initiates a request to the API. This is typically a request to access specific functionality or to get data from the API provider. The client must specify the target of the request using a specific URL or endpoint provided by the API. Each endpoint corresponds to a particular function or resource exposed by the API. For instance, a weather API might have endpoints for getting current conditions, forecasts, and historical weather data. Each of these is a separate API endpoint. Most modern APIs use HTTP, so these requests typically take the form of HTTP requests. So here, effectively, the client is constructing an HTTP request which will have components like the HTTP method, get, post, put, or delete, the endpoint URL, headers which might have metadata about the request such as authentication tokens or content types, and if it's a post or a put request, there might also be a body. This might include any data or parameters needed for the request, typically in JSON or XML. Now, when the client is making this request, they are only aware that they are accessing an API. But in reality, behind that API is an API server. This API server hosts the API functionality and it's going to receive this request and process it. This leads to the request handling phase, where the API server processes the request based on the HTTP method and the endpoint specified. This might require querying a database, performing calculations, or accessing external services. It's also very important for authentication and authorization to be carried out by the API server. Authentication involves verifying the identity, that is, where the client request came from, and authorization involves checking whether the particular operation or the data which the client is looking to perform is actually allowed. Once the API server has authenticated and authorized the request, it's time for processing and data retrieval. This is where the actual actions required to fulfill the request are taken. Then it's time to generate the response. Assuming that this is an HTTP interaction, the API server will have to generate an HTTP response. This will typically have components such as the HTTP status code, like 200 for success, 404 for not found, 401 for unauthorized, headers which will contain additional metadata such as the content type and length, and most importantly, the response body. This has the result of the requested action, which might take the form of data, and this is usually in JSON or XML. This response is then forwarded back over the internet to the client, and then the client has its own processing phase. This will involve parsing the response, displaying results to the user, or using it in further processing, and if necessary, error handling. This might occur if the API server sent back an error message. This cycle of communication does not really need to end. Clients can make additional API requests as needed to perform additional tasks or access different resources. This is at a high level how APIs work. Next, we'll understand why APIs are so important, particularly in cloud-based architectures. APIs play an extremely important role in cloud-based architectures. Let's understand why. APIs promote interoperability because different software applications written in different programming languages and running on different platforms can all interact seamlessly with each other. APIs provide a level of abstraction. They hide the internal complexities of a system and only expose the necessary functions and data. This simplifies interaction between applications, making it easier for developers to use them. APIs promote encapsulation because they wrap up all of the functionality of a system or a service, and that in turn means that developers can access specific features and data without needing to understand all of the internal workings. APIs are increasingly a form of standardization. Well designed APIs adhere to established standards and conventions, and this makes it easier for developers to understand and use APIs even if they aren't very familiar with that particular system. In order for clients to be able to invoke APIs, they must be documented. And this documentation, which has to include details about the available endpoints, request and response formats, authentication methods, and usage examples, further adds to the standardization of the APIs. Because the API server is usually a single common front end, this is a great place to put authentication and authorization functionality. And that in turn helps to maintain security and control over the data, and it ensures that there is no direct communication between a client and any specific server. APIs are often designed to be stateless, meaning that each API request from a client contains all of the information needed for that request to be understood and processed. This property also makes APIs inherently scalable and reliable because each request can be processed independently, and that in turn also means that the servers at the backend can be scaled more easily. API servers support versioning so that APIs can have multiple versions to support changes and updates over time. This is a good tool for maintaining backward compatibility. The versioning allows developers to continue using older versions of the API while also adding new ones when needed. Many APIs and API servers also implement rate limiting. This is a way to prevent abuse and ensure fair usage, as well as to potentially thwart attacks like DDoS attacks. Rate limiting involves restricting the number of API requests that a client can make within a specified time frame. All of these features of APIs in turn lead to many benefits. Improved collaboration because now it's easier for software components to talk to each other. Accelerated innovation because now different APIs can coexist with different version numbers and the cycle of development is faster. The monetization of product and data. This is an interesting one because it allows companies to start exposing aspects of their internal data or internal tools and start charging users for them. APIs have clear benefits for system security, as we've already discussed, because they serve as a convenient point for authentication and authorization. In addition, a less appreciated benefit of APIs is that they can also add to end user security. How so? Well, if during the communication process, the server requests information from the client, that client can always decide whether it wants to give up that information or not. Because this choice is made explicit at every step of the communication process, end user security and privacy benefit as well. Universal logins, IoT applications, travel booking sites, and mapping applications. These are all examples of APIs in the present day. We've discussed the technical benefits of APIs. In addition, APIs also unlock a lot of business value. Integration between different components and organizations is streamlined. The customer experience is enhanced. Innovation picks up because it's always fostered by easier communication. It becomes easier for businesses to expand to new markets, and it's also possible for enterprises to monetize parts of their data by making that data available via APIs. Finally, it also leads to improved agility and scalability of the enterprise as a whole. Google also offers a wide variety of APIs. Let's quickly mention some of them. The Google Maps API, which allows developers to integrate Google Maps into their websites and apps. It allows access to a range of mapping features, including interactive maps, geocoding, route planning, and street view imagery. Businesses can use this API to improve their location based services, customer navigation, and also to provide detailed geographic information to users. The YouTube Data API allows developers to access and work with YouTube resources like videos, playlists, and channels. This enables functionality like uploading videos, managing playlists, and retrieving video statistics and comments. Businesses can use this in order to integrate YouTube into their website and mobile apps and increase user engagement. There's a Google Sheets API. This gives you programmatic access to Google Sheets so developers can read, write, and format data. It also allows the creation and management of sheets, modifying the contents of cells, and automating data workflows. Finally, the Google Places API can be used to get information about places such as establishments, geographic locations, and prominent points of interest. Let's now talk about the API solutions available on the Google Cloud. There are three of them. Let's understand the strengths and weaknesses of each. There's Apigee, which is a comprehensive solution for building, managing, and secure APIs. It covers every use case, environment, or level of scale. Then there's API Gateway. This is a fully managed service which is tailor-made for serverless functions serving as RESTful APIs. And finally, there's Cloud Endpoints. This is a customer managed service for tactical cases like co-located gateways or private networking. Let's cycle through these one by one, starting with Apigee. Apigee is an API management platform. It's developed by Google and it allows enterprises to design, secure, deploy, monitor, and scale APIs. It has comprehensive tools for creating and managing APIs right through their lifecycle, ensuring that they are secure, reliable, and easy to use. Apigee has features like traffic management, authentication, analytics, and monitoring. It also has advanced enterprise capabilities, including security features like bot and misconfigured API detection, tools to package and monetize digital assets as APIs, flexible runtime support, a developer portal, governance policies, and more. It offers pay-as-you-go pricing, no upfront commitment, and multiple subscription tiers. Apigee works by providing an API proxy that sits between our backend services and any internal or external clients that might want to use our services. This API proxy server is very highly configurable, so Apigee has a rich array of policies for carrying out security, traffic management, data mediation. In addition to policies, you can also configure actions using custom code, conditional logic, fault handling, rate limiting, caching, and all of this so that the underlying backend services remain unchanged. Apigee is designed to benefit both API producers and consumers. API producers are the folks who build and manage the APIs and expose their backend services. API consumers are the ones that want to access the APIs in their client apps. Each of these sets has a different set of challenges. Let's talk about these in turn. API producers must focus on security because they want to make sure that there's no unauthorized access to their APIs from over the web. However, they need to balance security with discoverability. API producers want people to use their APIs, and so they want those APIs to be easily discoverable and usable by client apps. They need to be able to keep developers informed about updates and ensure that the APIs remain compatible across different versions and platforms. Producers are also always looking to measure the usage of their services to ensure that these are available and also in order to track traffic, enforce usage quotas, and gain insights into who is using their services. API consumers have a different set of considerations. For one, they prize flexibility. They would like to be able to make use of APIs from a variety of technologies, and so client apps should not be tied down to any particular technology. Consumers also prize ease of use. They'd like APIs to be well designed, easily discoverable, and well documented. Finally, API consumers care a lot about reliability. The stability of the backend services will determine the stability of their client apps. And so, a consistent API interface must allow API producers to make backend changes without disrupting services from the perspective of the API consumers. Apigee seeks to try and solve for all these challenges. It provides a developer focused portal for API producers where client app developers can discover your APIs. It offers API insights using advanced API security, monitoring, and analytics so that API producers can both secure access to their services but also analyze the usage patterns. Finally, Apigee offers a very high level of API reliability. It has a consistent interface for API management and consumption. And if you are an API producer, then the use of the Apigee proxy allows you to isolate consumers from your backend service. Apigee also has a version called Apigee Hybrid. This is a version of the Apigee API platform which allows organizations to manage APIs both on-prem and in the cloud. So your APIs might be running on your own data centers or on private clouds and still make use of Apigee's management capabilities. Apigee is the main API management platform on Google Cloud. So you should be looking to choose Apigee if you have high volumes and need for great reliability. In similar fashion, if you have high requirements in terms of scalability or performance, then Apigee should be your choice. Apigee, of course, also prides itself on enterprise grade security. Finally, you should consider Apigee if you are looking for opportunities for revenue generation or for collaborating with partners. You might be able to monetize data that you already have within your enterprise or APIs that you are internally using, and by using Apigee, you'll be able to turn those into a source of revenue. Next, let's turn to the more niche use cases for API Gateway. This is a fully managed service and it's tailor-made for services that are built on Google Cloud. It's more lightweight than Apigee and it's well suited to use cases like Cloud Functions, Cloud Run, and App Engine. So you would choose API Gateway if your use case is cloud native. Once again, that translates into serverless applications like Cloud Functions, Cloud Run, and App Engine. It does not feature a developer portal, and that might be totally fine if you are a small organization and have only simple APIs, and if your customers are mostly developers who are not looking to perform extensive discovery for end use in their client apps. The name API Gateway is well chosen. You can think of this as a gateway into the world of building APIs. If you are a first generation developer of backend services, then API Gateway is a quick and easy way for you to get up and running exposing your APIs to other users. API Gateway is lightweight and relatively inexpensive and easy to use. Finally, we also should quickly refer to cloud endpoints. This is a customer managed service and it has very niche use cases. Specifically, when you'd like to host the gateway on your own runtime with private networking, this is the most common use case for cloud endpoints. This is quite an advanced option because while it does allow developers to configure, deploy, and manage their own proxies, it requires customers to manage every detail of the API operations as well. In this video, we are going to talk about hybrid and multi-cloud workloads. Hybrid means that a part of the workload runs on an on-prem data center and another part runs on the Google Cloud. Multi-cloud here refers to a set of workloads which are distributed partly on the Google Cloud and partly on other hyperscalers. There are sound reasons why organizations might need to keep some workloads on-prem. There may be considerations of data sovereignty and compliance, particularly in highly regulated industries like healthcare, finance, and government. These might mandate that sensitive data remain within specific geographic boundaries or even on-premise in order to ensure compliance with local laws. For certain very specific use cases, there might be extremely low latency and high performance requirements which might be challenging to achieve with cloud-based solutions because of the inherent latency of the network communication between on-prem and cloud data centers. High-frequency trading is an excellent example of such a use case. Finally, it may just come down to large existing investments that have already been made in on-prem infrastructure. In all of these cases, the enterprise might want to have some workloads on-prem and others on the Google Cloud. In other words, the organization needs a hybrid setup. There might also be sound reasons why organizations need workloads on specific cloud providers. There may be specialized features, such as, for instance, the AWS IoT offerings. There might be regulatory or compliance requirements, which again might have something to do with where data is stored or processed. And finally, there are also factors of strategic partnerships and ecosystem integration. For instance, if a company relies heavily on Microsoft products like Office 365 and Dynamics, it's more likely to use Microsoft Azure. For all of these reasons, and also because a company might be wary of vendor lock in, the enterprise might decide that it requires a multi cloud solution. If we combine all of these scenarios, we end up with the need for a hybrid and multi cloud environment. For a variety of reasons, hybrid multi cloud environments have become quite popular in recent years. Here, there is a special case worth calling out, that is multi cluster management. We especially need to think about this in the context of cloud native technologies such as container orchestration and service meshes. This is a challenging use case because managing multiple clusters introduces challenges in configuration, security, and management. Those clusters might be hybrid clusters, where some of the VM instances live on prem and others live on the cloud. And it is specifically for these use cases that GKE Enterprise has come into play. The Google Cloud documentation has extensive examples of the need for hybrid multi cluster management. These include global financial institutions, pharmacy retailers, and a media and entertainment company. The common feature across all of these is the presence of multi clusters, where some of the compute resources are on prem and the remaining are on the Google Cloud. This now brings us to a term which was used extremely heavily by Google some years ago. It's still out there, but it's used less often, and that term is Anthos. The exact definition of Anthos is rather hard to understand, but one way of thinking about it is, if you have a Kubernetes cluster, and if all of the VM instances in that cluster reside on Google Compute Engine, then this is just straight regular GKE. On the other hand, if you have a Kubernetes cluster where some of the underlying infra resides on prem or on different cloud platforms, and parts of that infra also happen to be on GCE VM instances, then we are in Anthos territory. From the Google Docs as well as from various customer support interactions, it seems like the term Anthos now refers to a broad set of services, parts of which have been distributed into Google Kubernetes Engine for Enterprise, that's GKE Enterprise, as well as the Google Distributed Cloud, that's GDC. Unlike Anthos, GKE Enterprise is very clearly defined. This is an advanced version of the Google Kubernetes Engine, and it's designed to meet the needs of large organizations with complex, large-scale Kubernetes deployments. And GKE Enterprise has all of the advanced features of Anthos. These include a new logical abstraction which did not exist in GKE so far, and that's the fleet. GKE Enterprise and Anthos use the idea of a fleet in order to manage multi-cluster deployments. So we can think of a fleet as a logical grouping of similar Kubernetes resources. The multi-cluster thus has one additional level of hierarchy, and that's the fleet. Fleets and GKE Enterprise have a number of benefits while working with hybrid multi-clusters. There is an enhanced level of visibility and control because administrators can monitor, manage, and troubleshoot the entire Kubernetes ecosystem across all of the different environments from one interface. Fleets allow consistent operations because they have a single control plane across all of the elements within the multi-cluster. And finally, this gives rise to unified management. The fleet simplifies the administration of the multi-cluster and makes it easy to manage this additional level of hierarchy, where there are groups of resources on different environments which might be either on-prem or on different cloud platforms. We've discussed Firestore and how it's a part of the Firebase platform. Let's now talk a little bit more about Firebase. This is a comprehensive app development platform provided by Google with a suite of tools and services for app development on mobile as well as web. Firebase is a very specialized platform, so it focuses exclusively on mobile and web app development. It has integrated tools and services like real time databases, authentication, and analytics, which are specifically meant for these use cases. This makes it different than Google Cloud, which offers a much broader range of cloud computing in services and infrastructure. Let's talk a bit about the features and offerings of the Firebase platform. For one, it has both a real time database and Firestore, which is the document data store which we've already discussed. The real time database is a real time NoSQL database, which makes it easy for real time data syncing and offline support. It has an app authentication module, that's Firebase Authentication, which is a secure and easy way to manage user authentication. It supports different authentication methods, including email and password, phone authentication, as well as federated identity providers, including Google, Facebook, and Twitter. As discussed, Firebase has a tight integration with Cloud Functions. Firebase Cloud Functions allow developers to run backend code in response to events triggered either by Firebase features or HTTPS requests. It has support for analytics and performance monitoring and can give app developers insights into app usage and user engagement. It features its own cloud messaging service, Firebase Cloud Messaging. This is a reliable and battery efficient way to send messages and notifications to users across platforms, including iOS, Android, and the web. Let's quickly compare the Google Cloud Platform and the Firebase platform. The Google Cloud is all about making Google's infrastructure publicly available as services. Firebase, on the other hand, is focused on helping app developers to build mobile and web apps quickly and without worrying about the backend. Typically, users of the Google Cloud or of other hyperscalers tend to be server-side or backend developers. Users of Firebase are typically client-side app developers. Google Cloud Services focus on leveraging Google's core infra. Firebase services focus on building applications, engagement, and growing user base. Google Cloud Services deal with core infrastructural aspects like networking, storage, machine learning, traffic management, and scaling. Firebase services focus on real time databases, Crashlytics, performance management, and messaging. We started this course off by exploring serverless computing. We learned about serverless compute using Cloud Functions, Cloud Run, and Cloud App Engine, which allowed us to understand how to deploy and manage applications without provisioning servers. These tools provided us with the flexibility to build and scale applications effortlessly. Next, we learned about managed instance groups and load balancing. We examined how managed instance groups help in automating the creation and management of identical VM instances, ensuring high availability. Additionally, we explored load balancing to distribute traffic across multiple instances, improving the reliability and performance of applications. Finally, we explored APIs or application programming interfaces, understanding their importance and the various API solutions available on Google Cloud. These included Apigee, API Gateway, and Cloud Endpoints. We learned how APIs facilitate communication between different software systems, enabling integration and functionality extension. We also covered running hybrid and multi-cloud environments, gaining insights into managing applications across diverse cloud platforms. In conclusion, we built a strong foundation in serverless computing, managed instance groups, load balancing, and API solutions. We are ready to move on to the next course in this journey, Trust and Security on Google Cloud.